Hey Alex, how are you?
Hello, could you hear
Hi.
me? Hi,
Yeah.
over there.
Hey, how are you doing?
Hey, how's it going?
Good, man. It's been a while. Everybody's at home now. Nobody's going anywhere.
Cannot go anywhere, right?
Yeah. So
So,
how things going? How was your family?
I think it's pretty good. I think overall the Taiwan hasn't been affected so much. So,
Okay.
so I think we're in the better position than you guys in India right now. So I think,
Yeah.
yeah. So you had, probably more family time.
Yeah.
Everyone have to stay at home.
Yeah. So my wife and son, my wife got a postdoc in Switzerland. So
Oh,
she's moved there, and my son is doing school there, and I'm sort of shuttling back and forth. So it's an interesting.
oh, so so that's
Yeah.
a big change to
Yeah,
you.
yeah, 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 yeah. So I'm sort of doing a lot of shuttling now. That's it. And traveling during COVID times. Yeah,
Wow. So now you're in India or in Switzerland?
yeah. I'm in India right now.
Okay.
Yeah, yeah, yeah,
Wow. So
yeah,
then I don't know. So they are happy there, right? I guess.
yeah. They're happy. They're happy. I mean, my son loves the schooling there. Actually, that's sort of a interesting. Yeah.
That's a totally different from India.
Right. Yeah.
Wow. So how long have them been there?
So I and all of us went to this place to Switzerland on August 15th. And
Hmm.
then I came back in October on October 3rd.
Hmm.
And yeah, so it's been a little. So
Oh.
we've been sort of doing a lot of phone calls, and I'm going to go back now. So in maybe mid December, that's the plan.
Oh. So they just went basically.
Yeah. So we all went, and then it was quite nice.
Hmm. Hmm. Hmm.
Um,
Hmm. Hmm.
so, but I had to come back because my mother is here, and then
Right. But I think you haven't get used to it yet.
yeah, not yet. Yeah, but campus is fine. It's still open. There are no problems.
Uh-huh,
But
uh-huh, uh-huh.
outside Bombay, outside of the campus, it's a lot of people, and it's
Right,
interesting.
right, right. But now you're basically alone then.
Well, I think on the ground, I think there is not much of a lockdown, frankly speaking. But I mean,
Mm.
people are sort of careful, but I think we are sort of easing the lockdown significantly. That is
Oh,
that is the that is the
it's
way it is.
good. It's good. It's good.
Yeah,
I think,
I think.
yeah, I
Yeah,
think
I
it's
think.
going to
Yeah.
be
So
better.
yeah, how's your son?
He is already, I think, 12th grade, so he's preparing his, college entry exam right now.
Hmm.
So it's kind of the, pretty stressful period, I
Ah,
guess.
that's yeah,
Yeah.
yeah,
Yeah. It's a kind of, I don't know, but I think the same in India, right? So it's probably
right,
one of the
right, right.
biggest exam.
Yeah.
So
So are you stressed?
I'm okay, I guess.
You are always cool, man.
No, I'm fine. I think I think he will do his best, and that's good for
Yeah,
me. Yeah.
yeah. No, I mean, he was pretty calm and collected last time I saw him. He was very cool. He used to play
Yeah,
basketball, right?
he's okay. He's okay. Yeah.
Yeah. Great. Yeah.
All
So so
right.
you so yeah. So
So we,
you
s-
go ahead.
so
We start.
can should we?
Yeah.
Yeah,
So
as
so
well.
let me just introduce you, and then we'll take it
Yeah,
from there. Okay?
we can stick on time.
Yes. I'll give a very short introduction. So okay. So welcome everyone. So it's my pleasure to introduce a friend uh, from my grad school days, Professor Alex Howe, Tu Hong Howe. And yeah, so he did his PhD from Cornell University. And then He before that he used to work at TSMC and then Sematech, and after that, I think in 2008, he joined the Department of Electronics Engineering at National Chiao Tung University in Taiwan. Presently, he's a distinguished professor, and he's a director of the EECS International Graduate Program and the deputy director of the Microelectronics and Information Research Center at NCTU. He has published prolifically, and he has many conference presentations and about 19 US patents. He also has many awards, and one of the most interesting ones is this award of Ministry of Science and Technology Outstanding Research Award. With that, I'll welcome a friend and colleague, Professor Tu Hong Hong, to address his talk. Thank you.
Okay, thank you for the kind introduction from Professor Ganguly. So it's my great pleasure to present in the Icee 2020. So today I'm going to talk about how to realize the energy efficient in-memory computing by using the binary syntactic devices. I think the motivation is simple, right? So the binary memory device is commercially available. So being able to use them could speed up the development of the memory computing. So my outline. So I will give a brief introduction on the in-memory computing and also the quantized and binary neural network. And I will introduce our approach to use in-memory computing architectures for the binary neural network for both inference and also training. Then I will talk about some of the challenges for the in-memory computing based on the binary neural network, including the compact ADC neuron design. So you will see our approach using the STT and RAM as a neuron, and also we would talk about the development of the actual low current synaptic device by using the ferroelectric tunnel junction. So I think everyone agree AI has becoming more and more powerful every day. But according to the figure shown here by the OpenAI, the computing capability required for training AI model has increased exponentially with time. In the past, before the introduction of the AlexNet, this speed is double every 2 years. But after the introduction of the AlexNet, this has been speed up. Now it doubles every 3 to 4 months. So apparently not sustainable if relying only on the existing architecture and scaling low. So one of the remarkable examples showing the tremendous challenge facing in the AI hardware is highlighted in this so-called wafer scale engine made by the startup company called Cerebra. So they take the entire 12-inch wafer and make only one AI chip using the TSMC 16nm FinFET technology. Here shows the comparison between their chip and also the NVIDIA V100 chip. So it contains 1.2 trillion transistors, 400,000 AI cores, and a lot of SRAM, 18 gigabyte. So it's basically a supercomputer on a chip. So it consumes also the significant amount of the power, 15 kilowatt, and it actually requires spatial design water cooling system to make it running. So you can do a lot of things with 15 kilowatt, I guess. So there's a lot of water power. So for example, this powering muscle electric motorcycle can be run with only 11 kilowatt at the maximum speed of 150 kilometer per hour. So why AI chip requires such high power to operate? I think the simple answer is the data movement is very energy expensive and dominant the overall chip power consumption when handle the big data. You can see the arithmetic operations such as add and multiply require the energy around 0.1 picojoule, while the data access from the SRAM consumes 100 times more energy. If you have to access off-chip data from DRAM, I think the difference becomes even larger. So this data movement problem make people rethink the appropriate architecture in this big data era. The traditional computing-centric architecture, such as von Neumann, move data between memory and the CPU back and forth through the data bus. So on the other hand, the memory-centric architectures moves computing directly into the data in a highly distributed hardware. So it avoids energy expensive data movement. So that's why they also called it memory computing. So this plot shows the speed in terms of TOPS per second and also power of the various AI accelerators. So ideally, you would like to have the high speed and low power consumption, which is located at the upper left corner of this plot. The diagonal line represents the energy efficiency index in terms of the TOPS per watt. So typical GPU and TPU, they have the energy efficiency around 1 to 10 TOPS per watt, and in-memory computing is aimed to increase this energy efficiency index by a factor of 100 or even 1,000. Okay, so the in-memory computing is usually constructed using a very simple crossbar, the cross-point memory array, to accelerate the basically to accelerate the multiply and the accumulation, which count for over 70% of the computational load in deep learning. The input is represented using the voltage, and the memory matrix store the weight values as the cell conductance. So the conductance value ideally is represented using the analog memory to be able to present the high precision weight, and multiply of the voltage and conductance give you the current and through the Ohm's law, right? So the multiplication is done by the Moore's law. Then we can sum up the current flowing through the same column using the KCL, right? So we can perform this vector matrix multiplication across the entire array in a massively parallel fashion without moving the weight at all. So the weight update also can be done in a similar parallel fashion. So if non-volatile memory is used, the standby power can be very low. So that's going to be good for the many mobile applications. So you can think the previous example we shown for this Cerebral AI chip, they have the 400,000 AI cores. If you treat this individual memory as a tiny multiply and accumulate unit, so you can easily have a million AI cores in this tiny memory array. So that's why this approach is gaining a lot of attention, right? So if you can, here you see some of the examples of the analog memory developed using the various emerging memory technology. So as we just mentioned, the analog memory is the nature choice of the for the AI acceleration, because the weight value in the neural network is typically presented using a floating point number. So the cell conductance can be increased and decreased in an analog fashion by adjusting the programming strengths. The quantization, especially the smart quantization, is critical for saving the unnecessary computational load in AI computing. So according to this IBM analysis, we can achieve 30 to 14 point equivalent training accuracy by reducing the bit precision to the 8 bit. but the 8-bit is still a lot for today's analog memory technology. So because the commercial NAND flash can only give us 4-bit today. So also compare with the floating point number, the weight value of the this kind of an analog memory is bounded between the maxima and minima conductance value, and also the weight update is asymmetric and nonlinear. So insufficient weight precision and also the nonlinear weight update cause significant accuracy drop in training deep neural network using the in-memory computing approach. So however, for the inference, the requirement for the bit precision is less strict. So for example, in this IBM analysis, the 2-bit weight and 2-bit activation is sufficient to guarantee the very little accuracy drop in different deep neural networks. So this is the major interest to us because this is going to be useful. The inference is the major application for the edge AI at this point. So to the extreme, the quantization goes to the binary weight and binary activation, which is referred to the binary neural network. So the state-of-the-art BNN achieved less than 5% accuracy loss in very complex inference tasks. So this table shows the comparison between the performance and between the floating point 32 floating point number and 1-bit quantization. So you can see both the performance and energy efficiency can be dramatically improved by using this kind of BNN approach. So it also opens up more choices for the memory technology to be used for the in-memory computing, not restricted to only the analog memory. For example, SRAM for BNN has been widely investigated. However, the cell size of the SRAM is still pretty large, so the density is low, so it's only good for the small deep neural network model. So I think for the following, I was going to talk about our approach for the BNN, the in-memory computing implementation for the binary neural network. So we try to use only we try to use the newly available embedded memory technology in the CMOS platform, which is much smaller than the SRAM to implement the binary neural network. So for example, embedded MRAM is now available at 22 and 28 nanometer technology node. RRAM is also another choice is also available at 22 nanometer technology node today. So the main problem for inference is by using this embedded non-volatile memory technology is the inaccurate weight placement because the cycle to cycle and device to device variation are present. So when you try to write our pre-trained model into the multiple inference chips, you will find the actual written weight deviate from chip to chip. You cannot do accurate inference. So for example, the black curve here is basically the ideal for the RNN without when you training this RNN model without any variation, and but when you put into the inference chip, the inference chip has the certain variations. Then you start to see the accuracy drop significantly. So our approach to solve this problem is two-hand. One, we can train the model with the noise, and it's actually help you to tolerate more variation. Also, we can try to fine-tune some, especially the less classified layer, so which is pretty effective to allow the model to to actually tolerate more inference, to tolerate more variation in the inference chip. So here is the example. This is actually the video taken from the street of the Taiwan, and to for the object detection using the binary neural network. So the floating number, the left showing the floating number results, the right showing the binary number results. So you can see even by using the binary model, it can achieve the similar accuracy. We can also include the device variation into this kind of model, but after our fine-tuning process, it can accurate capture all the items in the video. Okay, so our conclusion is binary neural network basically is a very capable algorithm, especially for the different age the AI applications. So it's good that we can do the inference using binary device, but it can be even better if we can do the training using the binary device too. So can we do that? So when we train the binary neural network, usually we still require the floating point or analog weight. So the floating point weight is binarized, is only binarized for the vector matrix multiplication. So we basically need analog weight and also the binarize the mechanism in order for this binary synapse to perform training. So the internal weight, for example, in the RNN, the internal weight, the internal state that actually determines the final conductance can be understood by the concentration of the defects, such as oxygen vacancies. So when the oxygen vacancies connect into a continuous filament, so then you switch your device from the high resistance state to low resistance state. So we can, by applying a weak AC voltage stimuli, so it's like a self-programming process. So on the cell, so we can see the defects start to generate, but the cell remain at high resistance state because there's no conducting path formed between two electrodes. By applying more and more voltage pulse, the conductance remain at the high resistance state. But once the enough stimuli has been injected into the device, enough defects have been generated, then you start to see the device switch from the high resistance state to the low resistance state. So so here is the summary. So we have the external measurable binary weight, so which is our switchable conductance. We also have the hidden analog weight, which is your defects, right? So they can change in analog fashion. So, and we also have the binarization mechanism to binarize this analog defect information into the external weight information. But this binarization process is basically stochastic. So we can see this kind of single binary RNN devices is kind of combination of the exclusive NOR, which is used for the computing the binary multiply, and also we have the this floating point memory by using the defect concentration inside the RNN, and we have this binarized switching process in the RNN itself. So we can also show even in the other device such as MRAN. So the stochastic time-to switch in MRAN under soft programming condition can be also used as an analog weight to train the MRAN-based binary neural network as well. So this is one of the example we show. So we can achieve minimal accuracy loss less than 5% by using the and also because the sub programming condition we use, the device does not switch frequently. So the maximum switching time for each cell is less than 20 through the entire training process for the network. So it's greatly relieved the requirement on the device endurance as well. So the next, I will talk about some of the challenges for the in-memory computing based BNN. So the operation of the in-memory computing is very different from the typical the memory access, which much higher parallelism. So usually in the memory, we only access one or a few memory cells at a time. But for the in-memory computing, we try to operate this million AI cores at the same time to achieve the maximum speed and energy saving. So it creates the challenge at this peripheral circuit as well. So first, the accumulated current can be large for the in-memory computing, so it can create appreciable IR drop and imprecise MAC results in large arrays. So the array size cannot be too large usually for the in-memory computing type of applications. Second, the parallelism of the peripheral circuit is pretty limited because the big size of the SA and the ADC. So if the SA or the ADC size is too large, you cannot assign each bit line with an individual dedicated SA or ADC. So you actually negatively affect your parallelism. So to address these two issues, we think that we can try to leverage the device properties in the novel emergent memory technology. So first thing we look at is this neuron part. So usually the example showing the CMOS neuron based on the integrator. Then we convert the current to voltage, then do the comparator and reset circuit to do this integrate fire neuron design. And also because this is a CMOS circuit, usually the area is pretty large. So people looking into the other possibilities using the emergent memory devices such as PCM and RN. They still need the capacitor, but they also need the reset circuit because this is a memory. People also looking into the possibility to use the threshold switching devices. So the threshold switching devices is they can you can get rid of the reset circuit to save the error. So, but in general, the error remain to be pretty large in all the current existing approach. So in our approach, we try to use only the single STT and RAN to replace also the capacitor and this capacitor, comparator, and the reset circuit to minimize the error for the neuron circuit. So this is basically based on the backhopping phenomena in the MRAM. Backhopping phenomena in MRAM is that the bit error rate of the MRAM is actually not decrease but increase with the applied voltage. The switching of the bistable MRAM become unstable at high bias. So our research found that this backhopping behavior is actually originated from the local jaw heating effect, which reduce the energy barrier between these bistable states, and this create this stochastic oscillation between the two states. So if the applied voltage, which also reflect to the current, is low, so it acts normal bistable memory. But if applied the current is high, the barrier is reduced, and the oscillation between two states become a stochastic neuron. So the spiking frequency can be as high as 100 kilohertz, and we can achieve the 16 levels resolution for the input current. So it is equivalent to the 4-bit resolutions. So let me switch gears to talk about the low cell current FTJ. So FTJ is a new ferroelectric memory. So compared with the FERAM and FEFET, the FTJ has a simpler structure. It's a non-destructive read device with a very low current. So it's basically based on the tiny electroresistance effect, TR effect, to sense the resistance difference between two states due to the polarization direction change of this ferroelectric materials. The corresponding depolarization field is also changed. So the resistance can be either low or high. So this the TM picture shows the hafnium zirconium oxide based ferroelectric tunnel junction we made. So this pretty good interface, and also the crystalline structures we achieved, and well behaved the PV curve. So in this device, I think most noticeable is the current is very low. It's at narrow end range, so has a reasonable reliability and pretty small device to device the variations. So the FTJ is still an ongoing research topic, and there's actually in the literature about the FTJ's switching polarity. This is still quite controversial. So some of the FTJ device, you can see they can do the positive set and negative reset, or they can do negative set and positive reset. Some device they even do this double reset behaviors. So at the one of our work, we try to establish a comprehensive FTJ physical model to be able to simulate both the read-write behavior of the FTJ, and we can explain the switching mode of the FTJ, and also the interfacial layer effects, and we can consider all the current component in the FTJ, including the tunneling current, polarization switching current, and capacitive current, etc. So yes, so here is the example. Due to the position of the interfacial layer, we can actually reproduce all the 3 possible switching mode in the FTJ devices. We can use this model to optimize the FTJ performance as well, especially this TR ratio. The TR ratio usually is pretty small for the FTJ device right now. So we found the 1-to-1 ferroelectric EOT and interfacial EOT ratio is the best to achieve the maximum TR ratio, because it achieves the maximum polarization field. The narrow end low cell current actually allows the FTJ array to accumulate current through the over 1,000 cells in a large in-memory computing array. So this allows the convolution in the deep neural network to be computed in a single array in one cycle. This is our skin 1. If the cell current is too high, so to prevent the large current accumulation, we have to divide the calculation into either a single array but multiple cycles, that's skin 2, or we have to divide into the multiple arrays in a single cycle, which is the skin 3. So our analysis have been shown. So the skin 2 is actually, because you divide the calculation in time, it's pretty slow. The skin 3 is actually cost you a lot of error because of the peripheral overhead with the small array. So our analysis have been shown, if we are able to use this low cell current FTJ, we can achieve significant improvement in terms of the error power and also the error and energy efficiency. Okay, so that's my conclusion here. So basically, we believe the low precision quantized neural network and or even binary neural network are very important for the edge AI in the future. So implement QNN and BNN using the commercially available emerging memory technology is actually that's very important for the realization of the in-memory computing. So the variation is very critical, especially for the in-memory computing inference. So we can tolerate more variation through the algorithm co-design. So we can exploit the internal analog weight in the either RAN or the NRAN, which allow us to perform the online training using the binary devices. So the compact ADC or neuron design using the functional memory devices that actually you can build up your synapse and neuron or using the memory technology to realize this all memory based in memory computing. So the okay. If we have no low current memory cell, we are not going to be able to achieve the efficient in-memory computing. So we are targeting the cell current less than 100 nM, so that is going to be beneficial to achieve the high energy efficiency. Okay, so with that, thank you very much. I think if you have any questions, I'm ready to answer.
Okay, thank you very much for the really informative talk, Professor Ho. The floor is open for questions, and those who have questions may unmute and yeah, raise their questions. Thank you.
I have one question. Vinayak here from Global Foundries.
Hi, Vinay, go ahead.
Yeah, very interesting talk. I was just particularly about your back hopping.
Could
So
you
how
speak a little bit louder? Yeah.
is it better now?
Yes.
Yes.
Okay, so my question is regarding the back hopping which you are using for
Okay.
some of the spike network applications. How do you tackle the different device have different level of back hopping in a small array? Do you rely on bit level or are you relying on subarray kind of memory to have this kind of back hopping?
You mean how to design it?
Okay, let me maybe clarify the question. So when you have back hopping, so the back hopping varies with bit to bit. So how many devices do you need for this kind of spiking network?
Basically we try to use that as a neuron, right? So depend on how many node you have. So you definitely need a significant amount of the backhopping devices.
Okay.
Right. So, but I think the this backhopping devices is this really depends on the your design. So for the typical memory applications, you don't want this backhopping to occur. So that's why in the design they try to minimize this. But for our applications, we actually try to utilize that, right? You will apply the different design philosophy to achieve this, right? For example, in this case, we show actually the local jaw heating is very important. So we will try to actually and also the oscillation is what you want, right? It's not you don't want to have the bistable and RAN, right? So you can try to reduce your anisotropy and try to enhance your local jaw heating effect. That both will actually induce more apparent backhopping behavior in the devices. So that's actually so we are also working on how to actually design the desirable the backhopping practice using the MRAN devices.
Yeah, exactly. That is what I understood because we don't want to have any backhopping issue. In fact, when you have bigger array, only few devices will have this kind of issues. That's why I was just wondering. So if you design intentionally to have this kind of backhopping, so you might have some devices showing backhopping, some devices may not show backhopping, but that's why I was curious actually.
Okay. I think that's it's just like any memory technology. You have to optimize to make sure you have the pretty high yield. If you try, I think the I haven't probably didn't actually mention. So even for the back hopping device, there's only occurred at high bias range, right? So at the low bias range, it behaves like a normal stable memory. So that's why we believe we can use the same technology for both synapse and also neurons. So yeah, but I think there's of course there's a design problems. We have to carefully design it. Yeah.
Okay, thank you.
Yeah. So thanks, Vinay, for the question, and let's all thank Professor Ho for the fantastic talk. In the interest of time, though there may be many interesting questions to ask him, and get his views. We'll move on to the next speaker. Thanks,
Okay.
thanks, Alex. So
Okay.
thank
Thank
you very
you.
much. Thanks. So the next speaker, Dr. Vinayak Bharat Nayak. So Vinayak, you can share your screen. So let me introduce this next speaker. So Vinayak received his PhD from NUS in 2011, and he is currently working on MRAM devices at Global Foundries. He started working at A-Star in 2011 to 2014, and he's published 45 plus technical papers and holds 20 plus patents. And so it'll be very interesting for us to hear Dr. Nayak talk about the Global Foundries FTD RAM technology and his the scientific conclusions from that. So with that, I welcome Dr. Nayak. Dr. Nayak, stage is yours.
Thank you, Prof. Udayan. Yeah, good morning to everybody. Myself, Vinayak from GF. So this is the kind of work we developed recently. The title of my talk for today is Reflow Compatible STT RAM Technology for Industrial Grade MCU and IoT applications. Later half of the talk, I focus on our recent work we demonstrated in VLSI, that is more on MTJ endurance TDDB modeling for realizing cache-like applications. Just to give a brief background to myself and Spintronics, in fact, I started my research in Spintronics in 2007, and that is the year where we got Nobel Prize for Spintronics field, especially for giant magnetoresistance. But the memory technology, when we talk about it's more related to magnetic tunnel junction based on tunnel magnetoresistance. In fact, that time it is being heavily used for read sensors in hard disk, but parallelly there are multiple research groups where try to utilize this MTJ device for memory. In fact, that is the time which was kicking off for replacing existing non-volatile memory using MRAM. But currently, including us and a couple of our competitors, we already demonstrated and going into volume production of MRAM. So the part of the work which I show is on our 22 nanometer FTX embedded MRAM, which we recently, going into production. I will show some of our development study, what we did and how we did, and also show some of the package reliability data. And then I will talk on our next path to realize unlimited endurance. So here is the outline of my talk. So to start with, I will give a brief introduction to MRAM and also talk about what are the markets which is demanding for MRAM. We'll talk about our MRAM macro and show some of our data characterizations we did from device level all the way to macro level. As I said later, I will show some of the macro read-write performance, including the package reliability. The second half of the talk is mainly on TDDB modeling. It's a rather first of its kind model in this field, because we did carried out this model at megabit level data at sub ppm failure rate to realize this unlimited endurance which is required for cache-like applications. So I will briefly mention about our ongoing work with Professor Manan from IIT Delhi. We are trying to use embedded MRAM for AI engine applications. With that, I will summarize my talk. Okay, I think some of you already aware of STT-MRAM. Just to give a brief introduction to audience who are new to this field. So basically, MRAM is one transistor, one MTJ device. In fact, if you see, let me switch on my laser pointer. Yeah, in fact, if we see the MTJ element, we call it as magnetic tunnel junction. It is integrated in the back end of line of the CMOS process. It has primarily only three main layers. We call it as reference layer and free layer. And the magnetization direction of the free layer, it can be point up or point down, whereas the magnetization of reference layer is fixed. Depending upon the relative orientation of magnetization in the free layer, in contrast to the reference layer, so we will have a low resistance state and a high resistance state, which we can utilize to save state 0 or state 1 for memory applications. If you talk about demand for embedded MRAM, so as you know, the IoT and wearable markets are currently driving this consumer or industrial grade embedded MRAM to replace existing eFlash technology. So when you talk about eFlash technology, which is good, but which is having high power as well as it is rather slow. So people are looking for better non-volatile memory. But when it comes to MRAM, which has a feature of low power, at the same time it can have high speed. Basically, that makes a very good candidate. In fact, one of the best candidates to replace eFlash compared to other non-volatile memories. And at the same time, if you look at automotive applications, eFlash is not available below 28 nanometer technology, or rather, it becomes very expensive technology because it requires more number of mask layers if you want to optimize it for FDSOI or FinFET technology. That is why the embedded MRAM, considering the low power and high speed, it makes a very good candidate for automotive applications as well. And the last application is SRAM, like embedded MRAM. So as you know, when we scale down SRAM, so we have this leakage current, which shoots up. Since MRAM doesn't have this leakage issue, in fact, there is no zero standby leakage, if you can consider so. At the same time, it has low power and it is scalable in terms of bit cell size reduction. And it can achieve, if you fine tune the embedded MRAM, in fact, it can hit e to the power of 12 kind of endurance cycles, which makes a very good candidate to replace SRAM as well for cache applications. This is just to give you a feeling of what are the markets which is driving for new kind of memory technologies. If you talk about the growth in mobile computing or 5G technology, which is basically requires low power devices. At the same time, we have IoT computing and wearables, which are looking for new kind of memory devices, which is rather the speed is on the higher side and at low power. Currently, because of the emergence of intelligent computing and neuromorphic computation, which also requires large number of size, depending upon the application you talk about, at lower power as well as a high speed. And then, of course, we have augmented reality or mixed reality or virtual reality, whatever you call. So these kind of devices basically requires low power and high speed memory devices. If we talk about GF, we have a superior SOI logic platform, and we are master in RF technology. And on top of that, if we add our current embedded MRAM, so which makes it a powerful platform in order to serve many of these targeted market segments, to provide differentiated and optimized solutions for connected MCU or AI and AR kind of application devices. So let me go to next part of my talks, which is mainly to show you our embedded MRAM macro and some of our device results. If you see, this is the specification of our embedded macro, so which is the density is 40 megabit. and it is built on our 22 nanometer FDSOI platform. As I said, it is basically a 1 MTJ and 1 transistor device. The read access time is typically less than 25 nanosecond and write cycle time of 200 nanosecond. This macro also has a 2-bit TCC function, which is not enabled in the data which you see, but this is basically to correct whatever errors happens when the product is in the field. On the right side, you can see a snapshot of our macro. This macro also has internal generator and timing control, and automatic voltage bias control as a function of a temperature of the the product. If you can see a small TM picture here, which basically shows you a tiny magnetic tunnel junction device, which is sitting at the back end of line between 1x and 2x metal layers. So that is how the macro is designed, and the snapshot of our MTJ. Okay, so when you talk about macro, so we have to make sure we have a well-defined low resistance and high resistance states so that the macro can function very well at operating temperatures. What you see here is a probability distribution of low resistance and high resistance collected from 1 megabit subarray. As you see, there is no outlier, and then we have well-defined resistance distribution. In fact, it's a separation around 28 sigma RP, so that the sense amplifier can effectively detect a low resistance and high resistance in order to serve industrial grade applications. So this is just to show you the T0BR yield trend we achieved over the time of our technology development. In fact, we were having very low yield when we started this program, and significantly improved yield above 90%. And right now we have a very stable yield of 90% and above in the qualification process. Okay, so let me briefly talk about what I meant by this solder reflow, which was in the title. So what you see here is the data retention property. What happens is that the customers, sometimes they would like to write their secure code at wafer level before the wafer goes to packaging, because if they have to write at package level, it is a very costly process. That is why when for MRAM companies, this was new, because when we talk about energy barrier of our magnetic tunnel junctions, we always talk about operating temperature, which is from minus 40 C to 125, or if you talk about autograde, it will extend to 150 degrees Celsius. But when you talk about solder reflow, we have to make sure whatever the data which was written at wafer level, it has to retain when the wafer goes to a packaging process. The problem is that the packaging process is rather high temperature. It is 260 degrees C, and then it has multiple times of this process. It's very closer to 5 minutes, you could say. It's around 5 times. And then you need to have very high energy barrier so that the whatever content is written at wafer level, it doesn't go through. Doesn't disappear. It doesn't get disappear. That's why, as you see here, when we started, there were a lot of errors. So in fact, the y-axis is the BR after 5x solder reflow. So the target is 10 ppm level. That means only 10 bits roughly can fail out of 1 million bits. But in fact, when we started, because of the energy barrier was low, there were so many errors, and we implemented the advanced MTJ engineering stack improvement, and also other integration and etch process improvements. We lower down this BR all the way down to 10 ppm. In fact, if you see our call process, we have very superior energy barrier. In fact, this is world's best energy barrier so far reported in our process. If you see the median BR, which is around 2 e power minus 8, meaning we are talking about only 1 bit fail out of 40 million bits. And this is the process which is used for our qualification to meet the solder reflow requirement. And here is the one which shows you all the dies passing this solder reflow requirement across wafer. Okay, when you meet such a high temperature data retention, so meeting data retention at operating temperature for actual user case is not a problem for embedded MRAM with solder reflow capability. When you talk about eFlash or RRAM, people have to figure out what is the temperature they can ensure the data retention. But since we are talking about very high 260 degrees C reflow performance, if you see energy barrier, which is plotted on the y-axis as a function of temperature, which is very high if you extrapolate this, um, the error rate from high temperature. So the red line is for making sure the energy barrier of 57.1 kT for 20 years, meaning only one bit can allow to fail out of 10 million bits if you retain the content for 20 years. So that is the kind of stringent requirement people use for auto-grade. In fact, if you see 150 degrees C, we have enough margin to meet this kind of so that is the advantage of having solder reflow capable MTJ stack to have this data retention capability for industrial and automotive grade applications. Okay, so having high energy barrier is always better from the viewpoints of data retention. What happens is that as you increase energy barrier, so the switching voltage required to switch all these bits in the MRAM macro also increases. That is why but that incurs a problem of endurance. So you can't have very high voltage to switch the magnetic bits. That incurs a MTJ short from the TDDB failures. So it is really important to improve the switching voltage of the MTJ while meeting the high energy barrier. So what we implemented is because of the short learning cycle, so we together improved this parameter called switching efficiency. So what you see on the left side is the switching voltage as a function of BR after 5x solder reflow. So x-axis, you need to hit lower and lower error rate, meaning, higher data retention property. But whereas on the y-axis, the lower switching voltage is better for endurance. So we together improved from the advanced MTJ stack engineering to hit this target zone. So once we hit this target zone by improved switching efficiency, we have further trade off this the switching voltage as a function of coercive field, so that we can optimize the final stack for call process, meaning you have whatever required MTJ data retention point of view, but you lower down the switching voltage so that you can gain the endurance margin. That is the idea behind that. And this is the rectangle. What you see here is the potential MTJ stack splits we implemented in the final call process. So let me briefly show you the macro performance, which we in terms of write and read. So the pass fail criteria of T0BR is 1 ppm. And what you see here is the minus 40 degrees C on the top and 125 degrees C as the bottom. For MTJ, the switching, the magnetization, or what you call as coercive field, always you lower the temperature. That is the MTJ physics. Because of that, the writing is difficult at minus 40 C. But despite that, the improved process at a target voltage bias, we have good write margin window at minus 40 C. In fact, it is much more better at a high temperature because the voltage required to switch bits gets lower and lower as you increase the temperature. So on the right side, what you see here is just a schematic, not a schematic. It's a SHMU data to show you the illustration of the bits being written as you increase the MTJ switching voltage. In fact, if you apply lower voltage, you don't switch the bits. That's why you have very high failure rate. If you talk about 1 ppm level of failure, that is only one bit fail out of 1 million bits. So you need to overdrive the macro voltage so that you can lower down. But in fact, we with the optimized stack at the operating voltage, we have demonstrated zero failure out of 40 million bits. With the optimized process. Okay, so whereas on the other hand, on the read part, previously I showed you one chart of RP and RAP resistance distributions. So RAP, which is anti-parallel resistance, is mainly determined by the magnetoresistance. So if you have a higher tunnel magnetoresistance, you can have a wider gap between low resistance and high resistance state. But problem is for MRAM, as you increase temperature, the tunnel magnetoresistance keeps increasing because polarization of magnetic polarization, which keeps decreasing because of the thermal agitation. because of that, high temperature is worse for read, whereas at write, low temperature is worse. So as you see, with optimized SenseAmp design, as well as from the latest process which we optimized for with the highest MR and lower R mean sigma, at the typical read access time of 22 nanosecond and the read bias, we have wide window at room temperature. Even at 125 degrees C, we have good read window. In fact, this IDM next month we are going to show the macro functionality at 150 degrees C, with the more read margin demonstrated even to serve automotive applications. Let me move on to the package reliability which we carried out to qualify this whole MRAM, because showing functionality is one thing from macro level, but for to serve our technology for customers, we have to pass JEDEC level macro reliability. I am not showing the I will not be showing full JEDEC related reliability. I picked up only the few important ones just to show you the the reliability from package level. So we have extensive JEDEC level reliability study for all these packaged units, meaning you package all the wafers and then carry out all this reliability study at a package level. So what you see here is the cumulative probability distribution for solder reflow, mainly for data retention at 260C 5x reflow. All the units failure rate is well below 1 ppm for both P2AP and AP2P. That ensures the data retention is perfectly okay at a package level. Similarly, endurance, if you see, for E-flash replacement, it is around 100 K cycles. At all temperatures, all the units, the failure rate is well below 1 ppm, which is further ensuring that endurance is also perfectly okay. Okay, so this is very unique to MRAM. So if you take any other non-volatile memory, you will always have certain level of distribution in the resistance. You take RRAM, PCRAM, or even you take existing eFlash. Once you cycle it for more number of cycles, you will have this resistance drift issue. But MRAM is very unique. That is the reason people are trying to bet more on MRAM. What you see here is the resistance distribution for RP and RAP resistance before and after 1 million cycles, and this is carried out at worst endurance corner, that is minus 40 degrees C. And this data is collected from 128 kilobit. As you see, there is no drift in the resistance at all. In fact, if you see normal control plot for MR, in fact, it is overlapping one above the other without having any outliers from these 128 kilobit. Later, we also have demonstrated from megabit level data the same performance keep repeats. So this further ensures the product functionality even after you cycle it 1 million cycles. This is very unique to MRAM, which you can't have this kind of features in any other technologies. Okay, so let me move on to the second topic to realize that is the reason the one you show just now is the main boosting the main boost for utilizing this MRAM for SRAM replacement or even for low level cache applications. In fact, when you talk about TDDB, MTJ TDDB is much complex. What you see here is gate oxide TDDB, which is widely studied. In fact, people have also demonstrated the exponential law, even the power law have been verified for silicon oxide gate oxide. But when it comes to MTJ TDDB, it's rather complex because MRAM is a current-driven device, and MTJ-TDDB gets rather complex because of the Joule heating. The previous speaker nicely talked about Joule heating, because when you have operating voltage much higher to switch all the bits, and it is a current-driven device with very thin, nanometer scale, ultra-thin MGO, you always have very high current flowing through this ultra-thin barrier. And because of that, the Joule heating plays a major role. At the same time, MRAM is rather very complex process. When you talk about MTJ design, you only see 3 layers. In fact, we have more than 35, 45 layers in it. In at angstrom level accuracy, you can always have certain level of intermixing. That is why the MRAM people always consider it is a kind of art to design. because it is much more complex process if you want to make sure the overall endurance at the end of the day. Not only the MTJ stack point of view, even MTJ size and what kind of damage you have from at the sidewall from edge variability, everything matters for the extrinsic failures in terms of endurance. Previously, we demonstrated, these are some of the work which my IPP, the PhD student demonstrated in recent IRPS conferences. And we also have certain level of model framework to explain, because people can use E model, which is more underestimated. People can use 1 over E, which is kind of overestimated in terms of number of cycles which can hit at operating voltage. But what we demonstrated is, I think one should use power law model so that you don't underestimate or you don't overestimate when you talk about unlimited endurance cycles. But you can give a accurate, modeling. But this work is demonstrated from small array, 15 kilobit. It is good in terms of intrinsic TDDB point of view, but it cannot capture the extrinsic failures. That is why, in the recent VLSI conference, we showed the first of its kind of work we carried out from macro level data down to sub ppm level failure rate. That is the work which I'm, the results which I'm going to show now. If you see, as I said, the MTJ voltage always increases as you lower the temperature, because the coercive field increases, and how much percentage it increases is depending upon the stack design. So if you take a typical, MTJ stack, we are talking about around 10% higher voltage at minus 40 C compared to room temperature. And when you talk about 125 degrees C, endurance is better because we are talking about 15% lower compared to room temperature. So that is why the endurance is always worse at minus 40 C for MRAM. Unlike in case of gate oxide TDDB, the endurance is better at minus at cold temperature. So this is from a small 15 kilobit array we demonstrated. Later I will show more data from the megabit level macro. So here we wanted to show that the cold temperature again is the worst. So what you see here is the normalized voltage for 3 different parameters. The blue is the one which is the operating voltage of MTJ. That means, the writing voltage keep increasing as we lower the temperature, as I said just now. But when you talk about intrinsic TDDB point of view, because MgO also you can consider it as a oxide, right? So it also has, intrinsically speaking, the TDDB point of view, it is better as you lower temperature. But what happens is that if you take the intrinsic TDDB margin for MRAM, that is always decreases with temperature. It's primarily coming because the blue one, VOP, increases faster than the TDDB improvement as you lower the temperature. The net result is, the intrinsically speaking, the TDDB margin gets lower when you lower the temperature, meaning it gets worse at the cold temperature. So that is why the MRAM always shows a worse endurance performance at minus 40 C. And if you can, the overall, if you want to demonstrate endurance performance, we have to demonstrate at minus 40 C to make sure for actual product usage. Okay, so when we talk about SRAM for cache applications, or even the slow SRAM, even the embedded memory, we don't need to have solder reflow. So what is plotted is the energy barrier at 150 degrees C estimated from bake test as a function of normalized VMTJ for that particular stack. So the each data point you see is a different advanced MTJ stack engineering. So this point is E-flash flavor, the one which we already qualified and in the production for replacement for E-flash. You need to have solder reflow compatible performance. That's why the energy barrier is high, voltage is also high. But when you talk about SRAM replacement or slow SRAM replacement in the embedded memory, you don't need solder reflow. You can lower down the energy barrier and lower down the voltage and gain more endurance margin to realize e power 12 kind of endurance cycles. So that is what we have done. We have picked these MTJ which is having energy barrier greater than line. That is, the requirement is 0.1 ppm for 10 seconds, meaning as long as it can retain the failure rate down to 0.1 ppm level for 10 seconds, we are okay for slow SRAM replacement. So these are the stack we demonstrated, and then we measured the write performance from the macro level data. at different pulse widths. So as you see, the 1 ppm line is meaning only 1 bit fail, right, for million bits. But the thing is, as we know, if you lower down the pulse width, right pulse width from 500 nanosecond to 10 nanosecond, the operating voltage to make to switch all the bits to reach 1 ppm level keep increasing. So that is obviously given, but the question is at this operating voltage whether you can meet the endurance performance or not, because lowering pulse width also helps endurance, but the problem is the VOP is also increases faster. So the net rate is endurance is still we need to improve. So that is why the lowering the VOP comes into picture. So this is the demonstration we did from a power law model. So what you see on the y-axis is number of cycles for only 1 ppm level failure for endurance as a function of P2 AP voltage, which is worse for endurance for different right pulse width. So we have 70 nanoseconds already, all the way to 200 nanoseconds, and the 10 nanosecond is the projected using our power law model. So if you see at VOP, and if you use 10 nanosecond pulse, we can hit e power 12 cycles, provided your VOP is better, as we demonstrated from the advanced stack engineering. If you can lower down the switching voltage by having STT, much better STT efficiency and lower EB, yet meeting the data retention property, you can meet e power 12 cycles. So that is the demonstration we did using latest TDDB model. And we also carried out at these operating voltages from megabit level subarray at wafer level, we demonstrated up to 1 million cycles. There is no bit fail down to 10 nanosecond despite increased VOP. So that is kind of at least give confidence level to hit this kind of e power 12 cycles from the model framework. So let me move on to last part of the work, which is to utilize embedded MRAM for artificial intelligence. So this is in collaboration with the Prof. Manan from at IIT Delhi, as I mentioned. So this work is already demonstrated before. This is just to give you a feeling of what embedded MRAM can do. So what you see here is it's a demonstration of memory power as a event frequency for different kinds of MRAM and also from SRAM. So if you see compared to SRAM, the Everspin toggle MRAM, we could save up to 90 low. Yes.
You want to wrap up in a couple of minutes.
Yeah, 1 minute, I'm done.
Yeah,
Thanks.
thanks.
And then if you see the our global foundries STT MRAM, you can lower down by almost 3 order lower compared to SRAM. So and we are doing more work in this area to really make use of embedded MRAM. So let me summarize my talk. So first one is we, as I said, we are already in the volume production for 22 nanometer for industrial grade MCU. At the same time, there are 2 other avenues for embedded MRAM which we are exploring is for automotive embedded MRAM for 2x and 1x node. And we can also utilize some of these embedded MRAM features for AI engine applications. I would like to thank Stephen Sauce, James Su, and Martin Mason from our technology solution and business units for their support, and also Everspin Technologies for their valuable support. As you know, we have a close partnership with the Everspin. The JDA started in 2014. We have a 1 gigabit product at 28 nanometer already in production based on perpendicular STT MRAM. At the same time, we have 250 megabit also at 40 nanometer tech node is also in production since 2017. Yeah, with that, I will end my talk. Thanks for your attention.
Vinayak, thank you so much for this talk. This is really, really interesting. So with that, I think maybe we'll have one quick question from the audience. Those who may ask questions, just unmute and shoot the question. Thanks.
So I have one question.
Yeah, go ahead.
So with lowering of this voltage, like for increasing the endurance, is there any issues related to noise, read noise, or read margin and noise margin? Right error, right noise and read error noise. Have you any facing any difficulty while lowering this voltage?
Yeah, good question. So yeah, you do have read errors and write errors if you lower down the write voltage as well as read voltage. As I said, you have from the read shmo and write shmo. So we need to optimize the write voltage where you can have more read window or write window so that it won't go to the higher failure rate mode. You are right. So that we have optimized that. In fact, one has to optimize from lot to lot and wafer to wafer so that you have enough margin to cover many wafers in the foundry.
Oh, thank you, sir. Thank you for it.
Thank you.
Okay, with that, I think let's thank Vinayak. Vinayak, thank you very much for this talk.
Yeah, thank you. Have a good day.
Thank you. So we'll move on to the next speaker. I think just 1 minute. Yeah, so I think the next speaker is Mr. Arjunan MS from IIT Indore. Arjunan, please, you can start sharing us. So he's stepping in place of his advisor, Professor Anbarasu Manivannan. So Arjunan received his master's in biomedical engineering from Amrita University, and he's been working as a PhD student at IIT Indore under Professor Manivannan, and his interests are in photonic multi-level switching and phase change memory. With that, I request Arjunan to please proceed with his talk. Thank you. Arjunan, you can start. You may want to make your presentation full screen. So I think there is a problem. A, we can't hear you very well, and B, your presentation is not full screen. So if you can go to view and then maybe go to full screen mode. Yeah. Okay. Okay. Go ahead, please. Thank you. Yeah, it's coming nicely. Your voice is not very clear, so maybe you can speak a little slowly. Thank you. I think there's I am not able to hear very clearly. Maybe others, organizers can comment.
No, it's not audible, sir. Like it's not clear. We can't hear. So just can you check the speaker or microphone of yours from where are you speaking? I think there is some error. We can't hear you clearly. We can see your presentation, but we can't hear you. No, still not audible, sir.
I'm just wondering if there's a bandwidth issue. So maybe he can email you his slides and then you can present. Well, I mean, that's kind of hard. But anyway, let's try a little bit more and then maybe we can
Yes, yes.
figure out. I think your is there a way to call in from a phone?
Sir, can you check the speaker from where are you speaking? It might be an issue over there because others are, we can hear everyone, we can't
No,
hear only.
it may be his bandwidth.
Yes, 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 it might be the bandwidth.
So is it possible for him to call in from a phone line and then while and use the computer for visuals?
I'll just contact. So I'll just contact.
Alternatively, if it's a PDF, then it can be emailed to the organizer. I think Ahmad is there, right? I mean, I don't know whose email you have. Arjunan, can you try again? Can you say something now? I think your bandwidth is. I think even without sharing screen, can you? Okay, if you stop sharing your screen, then can you speak? No, I mean stop sharing your screen, and then let's see if the voice gets better, because maybe then it's a bandwidth improvement. Yeah, can you speak now? I think that it's not a bandwidth problem. Maybe it's a, or maybe bandwidth is poor. Yeah, hey, I can hear you. I can barely hear you. Yeah, okay. I can hear you, but I can't understand what you're saying. So let's do one thing. I think we are about 15 minutes past the time to start. So maybe in the interest of time, we can maybe figure out some other way to communicate the presentation. But at this point, I think there's a technical problem. So maybe we should, stop for today. Any suggestions from the people who are helping? Ahmed, do you have a suggestion? Okay. I think there is not much clarity. So Kumar, sorry, Arjunan, can you just speak again? See if we can hear you better now. Okay, I think there is no way we can hear this talk because the audio quality is very poor. So I think we apologize for that. With that, I think that was the last talk for this session. So we'll close the session. Thank you very much for attending, and thanks to the speakers for making this a very memorable session. Thank you very much.
Match to the diagnostic correctly. and we have a temperature exponent, which is basically a 0.5. These are for two different data sets, two different thickness of the platinum.
Jovan, you're on mic. Yeah. Okay. All right. Thank you very much. I think the session is closed.
Sir, I think we have an oral presentation also in this session.
Oh, there's one more. One more.
There is one oral presentation.
Really? Just one.
One paper presentation from one.
Yes, sir. Hello, sir.
Mr. Sanjay Pankaj Pathak.
Okay. Sorry.
Yes,
Let me just go through this again.
Yes, sir.
Then I think we'll wait maybe for. So this talk was at just one. Give me 1 minute.
Sir, I am here already.
Yeah, just 1 minute. I think we should not start because I think maybe people come back to your session. Just 1 minute.
Okay, sir.
It's very strange because the one I have doesn't have this talk. There are only 3 talks that's given to me in this session. So the organizers can sort of provide some clarity. I don't have this. So which session are you in, Pankaj? Just to clarify.
Sir, I am Pankaj. My oral presentation timing was actually 12:30 to 12:45.
Okay, and in which session?
Sir, it's you are the session chair is Professor Udayan Ganguly. Day 2,
Okay.
27/11/2022 day only.
Okay. Just let me just quickly confirm.
Yes, sir.
Hello, sir. Actually, in this session there were 3 invited lectures, and this is one oral presentation that we have at from 12:30.
I see. But it's not in the leaflet I got, so I'm sort of wondering what happened.
Okay.
So we'll wait for maybe we'll wait till 12:30 and then we'll start this talk. Okay.
Okay, sir.
Thank you. Because your talk was supposed to start at 12:30. Is that correct?
Yes, sir. Yes,
Okay.
sir. 12:30.
Okay. Thank you. So we'll wait. Thank you.
Okay, sir.
Okay, I think we can start the next presentation, which is by Pankaj Pathak. Pankaj, please share your screen.
Yes, sir. Sir, is it visible?
Um, Not yet.
Is it visible, sir?
Not yet.
No. Sir, is it visible right now?
Yeah.
Okay. So, good afternoon, everyone.
Yeah,
My name
just
is.
1 minute, Pankaj. Let me introduce this talk.
Yes, sir.
So welcome to the last talk. So this talk is titled Ultra Low Energy Strain Tonic Memory Using Strain-Induced Magnetization Switching in FEGA-B Elliptical Nanomagnets. The speaker is Pankaj Pathak. Pankaj, please, please start your talk.
Good afternoon, everyone. My name is Pankaj Pathak, and topic of my presentation is ultra-low energy strain-tonic memory using strain-induced magnetization switching in iron gallium boron elliptical nanomagnet. So this is the outline of my presentation. I will start with the introduction of magnetization switching, then strain-tonic devices, then external magnetic bias for in-plane magnetization switching, our proposed structure, methodology, results, conclusion, and acknowledgement. So I start with the introduction of magnetization switching. So over the years, there is a search for beyond nano CMOS nano devices because CMOS nano devices are reaching to their physical limit, and spintronic is seen as an important catalog on CMOS devices. So primarily, spintronic devices are used for the memory application in computer architecture, and their core is to modulate the magnetization. So if you see this first figure here, this is the popular hysteresis curve of a ferromagnet where the magnetization could be altered with the help of external magnetic field. So primarily in the spintronic devices, the external current is used in order to switch or the modulate the magnetization. But the problem is the joule heating that is associated with the current that we are flowing here. So the possible alternative could be the stentonic devices. So the stentonic devices primarily consist of two order parameter. One is piezoelectric and another one is magnetostrictive ferromagnet. So the device we are talking about is at nanoscale. So before that, there is a comparison between which kind of control is actually being used here. Here, the two energy scales are compared. One is magnetic field and another one is electrical field. So if you talk about in order to generate 6 Tesla of the magnetic field, which is in terms of physics is pretty much large, but in terms of device perspective, this is quite low energy. At a distance of 1 micrometer, we require a huge amount of current, around 30 amps, which is inefficient. On the other hand, suppose we require zero point 0.4 megavolt per centimeter electrical field. For a 1 mm bulk, we require 40,000 volts in order to produce this electrical field, which is also impractical. But once we start moving to the nano scale, pretty much lesser value like 4 volts can generate around at for a 100 nanometer thick thin structure. The electrical field of zero point 0.4 megavolt per centimeter could be generated. So at nano scale, this electrical field control is actually preferred, and that is primarily used in these stentonic devices. So if with the help of external electric field or voltage, the polarization could be changed that produce the stress or strain in the piezoelectric substrate, and that we can transfer to the ferromagnetic magnetorestrictive component of the material that we are using, then the magnetization could be altered even without help of the external magnetic field. Here also the switching energy and the delay time of the stentonic devices with the conventional spintronics and the CMOS semiconductor electronics is being compared. So you can see the switching energy of the stentonics devices are quite less as compared to the spintronic and the conventional CMOS semiconductor electronics, and their delay time is quite comparable to the spintronic devices. So if I talk about the already published papers for the spintronic structures, they primarily being used for the out-of-plane magnetization switching dynamics, where if the up pole encodes one bit, the down will encode the other bit. The in-plane magnetization switching is less explored because once we start reducing the elemental size, considering the memory application, then they are thermally unstable, and the larger elements they form the multi domain, and on that account they cannot be exploited. Also, the initial magnetic bias field is required in order to pole the magnetic switching to a particular direction initially. So for that, in this work, we have used the self-bias condition, voltage control self-bias magnetic random access devices that eliminates the obligation for an extrinsic magnetic field bias for the in-plane magnetization switching. So this is our proposed structure. We have used the PMN PT single crystal 011 oriented piezoelectric substrate. Its tensile stress is along 0, 1, -1 direction, and that is pulled along the 100 axis or the easy axis of this iron gallium boron magnetoelastic nanodisk. The compressive stress direction of this PMN PT is along 100 direction, which is put along the minor or the hard axis of this iron gallium boron magnetoelastic nanodisk. The thickness of this PMN PT is 500 micrometer thick. The iron gallium boron magnetoelastic disk is having the elliptical shape, and in order to understand the structural dynamics, we have changed the aspect ratio from 1:1 to 2:1. The reason for choosing this elliptical shape is because with the simulations we got to know that elliptical shape has only two easy axes, that is being quite good for the application we are talking about to store a bit. So we have used the micromagnetic simulation platform MUMAX-3. So initially we have defined the materials and geometry along with the mesh parameter. The cell size we have considered is 1 nanometer along each X, Y, and G direction. Because MUMAX do not have the ability to incorporate the stress directly, we have used the stress anisotropic magnetic field and the anisotropic field to incorporate this stress with the help of magnetorestrictive coefficient and the external stress and its direction. Once we know the initial magnetization, then the uniaxial anisotropic field is applied until the final magnetization could be reached. That acts as the initial magnetization for the next cycle. If we do not have the initial magnetization, then we have to relax to save the magnetization at the final steady state. So these are the results. In order to calculate the minimum thickness for the structures, we have calculated the in-plane energy barrier. So the typical in-plane energy barrier for the thermal stability for a magnetic random access memory that is generally used is around 1.72 electron volts. So we have scaled this in-plane energy barrier with the temperature. And that comes out that if this in-plane energy barrier scaled with temperature is less than 70, then they are thermally unstable. So in another way, we can say that at a room temperature, the magnetization switching is actually influenced by the temperature, and they are unstable. So in order to know the minimum thickness that could be used, this in-plane energy barrier is scaled with temperature is plotted against different thickness for all the nanomagnets that we have explored. So we have observed the minimum thickness for the nanodisk 1, 2, and 3 are 9.5 nanometer, 5 nanometer, and 5 nanometer respectively. This is because once we start increasing the thickness for the fixed cross-sectional area, the in-plane energy barrier starts rising. So this is corresponding to the self-biasing, which eliminates the requirement of the external magnetic field for such applications. So always the nanodisk or the ferromagnet that tries to reduce the energy. So there, at the pre-stress condition, there is a competition between the exchange and the demagnetization energy. Because this exchange energy actually tries to align magnetization, to align magnetization, local magnetization alignment. That led, if the exchange energy is pretty much larger as compared to the demagnetization energy, the local alignment led to the vortex state, which is pretty much a stable state, and that cannot be altered. So for all the nanodisks that we have used, we have calculated the maximum thickness that is corresponding to the self biasing, and these are the magnetization dynamics corresponding to the self biasing. So you can see if this thickness is less than the self biasing thickness, or equal to the self biasing thickness, initial magnetization is considered, random magnetization is considered. With the time it switches to the easy axis, there is equal probability to switch it to the 0 degree direction, like here we have shown, or 180 degree direction, which is another easy axis for the elliptical disk that we are using. But once we start increasing the thickness more than the self-biasing thickness that we have calculated already, then the exchange energy is pretty much larger at that case, and that tries for the local alignment of the magnetization dynamics, and that led to the vortex stage, which is pretty much stable and that cannot be explored. So for this particular figure A, switching magnetization dynamics, this is the magnetization versus time curve. So you can see initially the random magnetization is considered, and finally at a steady state it led to the 100 state, which is along 0 degree or easy axis. But when the D is greater than DSB, this is the B figure shows the magnetization dynamics, and this is magnetization versus time curve. Here the magnetization is actually goes to the vortex stage, which is oscillatory magnetization, and that cannot be explored. So for all the 3 nanodisks, the self-biasing maximum thickness is calculated, which is 12 nanometer, 15 nanometer, and 26 nanometer. But in order to calculate the exact value of the maximum thickness, we have calculated the maximum stress actually that can be transferred to the nanodisk that we are using, and that also limits the maximum thickness that could be used. So for the PM and PT substrate of the 011 orientation that we are using of 500 micrometer thick, the maximum stress that could be generated is around 5,000 microstrain, that is corresponding to 312 megapascal. So here if you see for the disk 100 cross 90.9 nanometer square, although up to 26 nanometer you can go, but the self biasing is the limiting factor here. So self biasing is possible only up to 12 nanometer. So the maximum thickness that could be applied to this nanomagnet is only 12 nanometer. Although you can use this 14, 22, or up to 26 nanometer thickness, because here the critical stress is less than the maximum stress that could be possible. But here we have to use the external magnetic field initially in order to pole them to the particular easy axis. But for these two structures, 100 cross 66.67 and 100 cross 50 nanometer square, the maximum thickness is actually limited by this stress requirement. Like for this particular nanomagnet, the maximum thickness corresponding to self biasing was actually 12 nanometer, but once we start increasing the thickness more than 9 nanometer, the critical stress value is pretty much larger than the stress that could be produced. So here the limiting factor is the critical stress that is actually being produced practically. So the maximum thickness here found was 9 nanometer, and for the 100 cross 50 nanometer square, it was 6 nanometer. So these are the nanometer cross-sectional areas and the corresponding thickness that we can use, which actually gives us idea about the nanomagnets are thermally stable. Also about they are having the thickness, practical thickness, where the stress is under the under the practical strain considerations. Also, here the self-biasing is possible also. So with the structure that we are using, only in plane 90-degree switching is possible. So initially we have done the 90-degree switching dynamics. So when this stress is more than or at least equal to this critical stress value for the particular nanomagnetic structure, then the complete 90-degree in-plane magnetization switching we have observed. Like you can see, initially the random magnetization is considered with the material property of the particular nanomagnets. Once we know the thickness for a particular cross-sectional area, with the self-bias, it goes to the phi equals to 0 degree. This is corresponding magnetization versus time curve. Also, it can go to the 180 degree. That is another possibility. And once we start applying the critical stress, it completes this in-plane 90-degree switching, which is also shown here in magnetization versus time curve. So here it goes from 100 mx my mz to mx my mz equals to 010 state. So there is complete 90-degree switching is possible. So we have observed that with the increase in thickness having cross-sectional area same, or with the fixed thickness and reduced cross-sectional area, the critical compressive strain value actually starts increasing. This is because in both of these cases, we have already seen that the in-plane energy barrier is actually increasing, and this is why we require a pretty much larger external stress or the voltage value in order to overcome this induced energy well. So in order to understand why this in-plane 90-degree switching was happening, we have calculated different energies associated with the iron gallium boron nanomagnet of different dimension, and that is plotted against the angle that the magnetization is making from its easy axis. So like for phi equals to 0 degree or along its easy axis to go to the 90 degree, this is energy barrier actually, that is corresponding to phi equals to 90-degree energy minus phi equals to 0 degree energy. So in order to cross this, actually demagnetization energy always rises, because the in-plane magnetization is switching from its easy axis, that is phi equals to 0 to phi equals to 90 degree. The exchange energy literally means practically they are almost zero, because if the exchange energy starts dominating, then the local alignment of the magnetization led to the vortex state. Because the storage, the application we are talking about, we require 180-degree switching. For 180-degree switching, we have used the precessional dynamics. So like for this figure, if you see, for the typical example, if the phi equals to 0 degree is achieved by the self-biasing property, and we apply the critical stress for a particular duration such that the magnetization along the x-axis direction reaches to its maximum negative value, then removal of this external stress gives another 90-degree switching to another easy axis. So it goes from phi equals to 0 to phi equals to 180 degree. Also, if this magnetization is positive only and we remove the external stress, then also the 90-degree switching is possible. But it, rather than going to the phi equals to 180 degrees, it comes back to the phi equals to 0 degree. This is because the ferromagnet always tries to decrease their total energy. So if the magnetization is switched from phi equals to 0 degree to maximum negative value, and we remove the external stress, it goes to its nearest easy axis in order to reduce the total energy. Also, in another case, if the easy axis is along phi equals to 180 degree, then removal of the stress at when the magnetization along x is positive completes removal of the stress at that condition completes the 180 degree switching to 0 degree from 180 degrees. So for every structure, we have calculated the minimum time pulse that is corresponding to the fastest in plane 180-degree switching. What we have observed this is with the increasing thickness having the cross-sectional area fixed, there is a trade-off between the switching time and the corresponding external strain, because larger strain means larger voltage we have to apply, and there is a means more energy dissipation. So there is a kind of trade-off there. But when there is a reduction in the cross-sectional area having the fixed thickness, then the switching time and corresponding strain they do not have any of the trade-off. Means suppose the thickness is fixed and we start rising the cross-sectional area, the switching time and the corresponding strain, both these starts reducing. So nanodisk of aspect ratio 1:1 gives us better results in considering the switching time and the external stress requirement. But within this cross-sectional area, once we start increasing the thickness, then there is a trade-off between its switching time and the corresponding strain values. So we have covered the switching dynamics of submicron iron gallium boron emitting nanodisk in this work, and for this we have obtained the optimum thickness ranges considering thermal stability and the practical strain requirement, along with the self-biasing random access memories. Faster switching speed and lesser switching energy, that is lesser associated strain for increasing cross-sectional area with fixed thickness is observed. Also, there is a trade-off between switching speed and switching energy with increasing thickness for the fixed cross-sectional area. Nanodisk was observed. I would like to acknowledge Interdisciplinary Microsystem Lab, IIT Delhi, and IIT Delhi and DST for the fund. Thank you very much.
Thank you, Pankaj, for the talk. Are there questions? You may unmute your mic and pose your question. Thank you. Okay. If there are no questions, then you have I have a question. So you have talked about these optimal ranges
Yes,
of
sir.
thicknesses.
Yes, sir.
So is this very material specific, or do you think that engineering the material would change this?
Yes, sir. With change in the material, actually associated energies will be different. So this means values will be different. So this is the material property somehow, and we are exploring the other materials, other nanomagnet materials also, like nickel, other soft magnetic materials also.
Okay.
For this. Yes, sir.
Okay. If there are no further questions, then let's thank the speaker. And I think with that, I declare the session to be closed. Thank you very much for participating and making it a very lively session. Thanks.
Thank you.
Hello, Mr. Rakesh, can you please unmute yourself? Mr. Rakesh Kumar Pandit. Hello. Good afternoon, everyone. Welcome to ICEE this session, second session. I think we have a couple of oral presentations followed by invited lectures right now. Right now we have a oral presentation from Dr. Arvindo Burman. Is he here? Are you there, Dr. Arvindo? Ahmad, can you just check if Dr. Arvindo is available here for the next presentation?
Yes, I cannot see him in here. Let me just check.
Should we wait for him for a couple of minutes?
The next presenter is here, Mr. Rajesh Dev, but Mr. Dr. Arabanda, I cannot see him here.
We need to
So
contact him. Any number or anything we should contact him for getting presented over here? Do you have any, or any committee ICW members, if they have the, can we contact them?
let me check. We
Just
do have their mails, but we don't have their numbers. We have their mails, so maybe we can, or we can start the presentation, second oral presentation first, because I think second presenter is already here. Can we do that?
just we'll wait for 1 minute more. If he's not there, then we'll start with the next presenter.
Sure. Let me just see if I can mail him meanwhile.
Let's check if he's there. Any response, Ahmad? I don't think he's replying to any of the emails already.
Not yet, sir. Not yet. I'm just trying to mail him. So meanwhile, I think
Just see, I gave a small few announcement right now. So after that, in that case, if he's replying okay, then otherwise we'll start with the next presenter. So I
okay.
have
Should I?
few announce. Yes,
Yeah.
yes.
Yeah. Sure. Please go ahead with the announcement.
Yeah, with a few announcements to the participants. to make the session more interactive, you have a chat box, or in your virtual mode, there is a ask questions. So you can ask to any of the queries or any doubts to the presenter, whether it's a oral presenter or it's a minute talks over there. You can ask the questions over there, and it would be nice to have interaction with all the participants over there. Moreover, after 3:30 at hall 6, we have invited talk followed by a knowledgeable poster presentation at hall number 6. So kindly join hall number. It will be over here. It will be in hall 6. So all the participants are requested to join the poster sessions and have an interaction with all the presenters over there. So these are the announcements. So yeah, Ahmed, you can now tell me if anything is progress, or we'll start with the next presenter.
I think we can start with the next presenter, sir. So meanwhile, I'm just mailing him and letting him know that if he can join by 2:15 or 2:20, so maybe after this presentation we can have his presentation.
Okay, okay.
So
Okay,
if he
so our
responds, then fine. I think
we'll start with next presentation. Okay. So our next, in Minor, we start our next presentation with Mr. Rajesh Dev from
Yes,
United
sir.
States, Assam. He is there, right?
Yes, sir.
So you can share your slides
Okay, okay.
and you just start sharing your slides. Can you make it to full? Yeah, yeah.
Yes, sir. Is it visible, sir?
Yeah, yeah, this is visible now.
Okay, okay.
Okay, so all the participants are oral presenter now is Mr. Rajesh Dev from NIT Silchar, Assam. This topic of presentation is polarity independent resistive switching in MOS2 nanosheets and PO based nanocomposite films. Okay, Rajesh, the floor is yours now. You can start.
Okay, okay. So good afternoon to everyone. Myself Rajesh Dev. The topic of my presentation is polarity independent resistive switching in MOS2 nanosheets and PO based nanocomposite films. So the outline of my presentation is introduction, the experimental methods, results and discussion, and summary. So let us start with introduction. Transition metal dichalcogenides are generally MX2 type compounds, where M is a transition metal element and X is a chalcogen. TMDCs can be either semiconductors, metals, or insulators. So some of the examples of TMDCs are MOS2, MOSE2, WS2, etc. So among various TMDCs, MOS2 is gaining a lot of attention due to its tunable band gap and charge confinement effect. But recently, MOS2 in its two-dimensional form, such as monolayer or few layer nanosheets, has drawn tremendous interest due to its nanoelectronic applications such as resistive switching memory, transient electronics, bioelectronics, neuromorphic computing, operations, etc. Also, MOS2 with different polymer hoods shows application in flexible and wearable electronics. So resistive switching memory is mainly classified as volatile and non-volatile memory. The non-volatile memory can be again classified as unipolar and bipolar. So unipolar, in case of unipolar, the set and reset process occurs with the same voltage polarity. But in case of bipolar, if set is occurs in the positive side, then reset occurs in the negative side, and or vice versa. So non-polar resistive switching offers advantages in flexibility in peripheral circuit design and in some cases high storage density in comparison to conventional bipolar resistive switching memories. There are several materials that showing non-polar resistive switching and such as hexagonal boron nitride, MOS2, ZnFe2O4, magnesium oxide, etc. But there are no such reports of non-polar resistive switching in MOS2 polymer components. So for the first time here, we are reporting the observation of non-polar resistive switching in MOS2 based polymer nanocomposite films. This is the process of our exfoliation. So for this, what I did, we took a few amount of MOS2 and grinded it in a mortar-based cell for 30 minutes. Then we transferred the grinded MOS2 in a probe sanigation, and finally we collect the exfoliation MOS2 after centrifugation. These are the some pictures that we took after. This is after freshly prepared. This picture is after 1 month, and this picture is taken after 2 months. So from these pictures, we can conclude that there is neither any significant change in color or no settlement. There is no settlement for the storing period up to 2 months. Also, we calculate the yield of exfoliation, and we found that there is 14 milligram of MOS2 in 10 ml of DMF. In device fabrication, what we did, the composite solution, spin coated at 4000 rpm for 1 minute on ITO coated PET substrate, then dried in vacuum oven for 6 hours at 50 degrees centigrade, and then by taking aluminum as the top electrode was deposited by thermal evaporation method. This is the prepared. This is the picture of our prepared device. So for the composite formation, what we did, the structural characterization of the composite. This blue marks indicate the X-ray diffraction peaks of MOS2, exfoliated MOS2, and these are the X-ray diffraction peak of PO. So from this XRD graph, we confirm about the composite formation of PO and MOS2. Separately, we investigated the 002 peak of MOS2, and we found the crystalloid size of 002 peak of MOS2 by using this device CRR formula, and it is found to be nearly 8 nanometer. So roughly, we estimated there is 12 to 14 layers of MOS2 in the nanosheets by taking D spacing as 0.6 nanometer. So next, we did the this is the same image of exfoliated MOS2. So you can clearly see the layer structure, layer structure, the restacked layer structure of exfoliated MOS2. This is the optical microscopy image of composite, and you can see the spherulites with some interfacial amorphous region, and the inset shows the radial lamellar structure of a single spherulite. And this is the same images of composite, and it is clearly visible that the lamellar structures with some micropores. These are the some micropores with some lamellar structures of the MOS2PO composite. So next we did the atomic force microscopy. For AFM, the exfoliated MOS2 was drop casted on a glass substrate. During the drying stage, some of the MOS2 nanosheets agglomerates to form bigger particles. So here, this is not uniform. So from the height profile, we calculated the average layer thickness of MOS2 nanosheets, and it is found to be 12 to 5 nanometer. The surface roughness of the composite is calculated to be about 15 nanometer, and the big spikes in the height profile is due to MOS2 agglomerates present in the surface. And this is the differential scanning calorimetry of PO and nanocomposite. This is the crystalline temperature of PO and crystalline temperature of nanocomposite. So the percentage of crystallinity is calculated by using this formula, where delta HM is the change in melting enthalpy, and this can be calculated by taking area under the curve from these peaks. And delta HM, it is theoretically melting enthalpy of 100% in crystalline PO. So yeah, so from this we can find that the percentage of crystallinity increases up to 60% in PO MOS2 nanocomposites in comparison to PO. and this may be due to nucleation and confinement effect. So these are the electrical characterization of our prepared device. This shows the bipolar switching. This is positive bipolar, where set occurs in the when a positive bias is applied to the aluminum top electrode. The set occurs at nearly 3.44 volt, and by changing the polarity, reset occurs at minus 2.04 volt. Similarly, this is the negative bipolar when positive voltage is applied to the ITO bottom electrode. So from these two figure, we can see that the set and reset process is very sharp, and this is the schematic diagram of our prepared device, where aluminum is the top electrode, then PO MOS2 nanocomposites, and ITO is the bottom electrode. And this is the positive unipolar and negative unipolar switchings of our device. And from these two graph, we can see that the reset process is not sharp. It is a staggered and stepwise process. So now let us discuss about the conduction mechanism. So this is the positive bipolar set. For the conduction mechanism, what we did, this is the log plot of current versus voltage, and the inset of ln I versus root over b shows the slope is linear and suggests that the conduction is due to emission or Schottky or thermionic emission. Then in the high resistance state, the slope increases slowly up from 2.24 to 3.77, and which is greater than 2. So it suggests that during the set process, the conduction mechanism is due to trap controlled phase charge limited conduction, and then the cell reaches to the low resistance state. In the low resistance state, the slope is nearly 1, indicating the ohmic type conduction. Then in the reset process of positive bipolar, the slope is nearly 1 due to ohmic conduction, and as the reset process occurs, the maximum slope observed is 1.29, indicating the detrapping of MOS2 nanosheets from the trap side. Similarly, in case of negative bipolar set, the conduction in the high resistance is due to trap control SCLC, and in the low resistance state, this is not ohmic like this positive bipolar set. So in this here, the slope is decreasing from 2.36 to 1.56, which suggests that the conduction mechanism in low resistance state is phase charge limited conduction. Similarly, similar to the bipolar set, the conduction mechanism is similar in case of unipolar, and in case of negative bipolar set. So when positive voltage is applied to the aluminum top electrode, the conduction is mainly due to the trap control SCLC, and when negative voltage is applied to the ITO bottom electrode, the conduction mechanism is either ohmic or space charge limited control mechanism. So we can conclude that we have successfully exfoliated the bulk MOS2 powders into few layer nanosheets. Also, we found a very good yield of 14 milligram per 10 ml of MOS2 by this exfoliation method. Further, a two-terminal device was prepared with ITO and aluminum as bottom and top electrode. Also, we have observed a polarity independent of non-polar resistive switching in ITO MOS2 PEO aluminum memory cells. The reset process in bipolar is very sharp, but in case of unipolar, it is a stepwise staggered process. The current in high resistance stage, both in bipolar or unipolar, is governed by trap control SCLC. But in low resistance state, it is either ohmic when positive voltage is applied to the aluminum top electrode and space charge limited when positive voltage is applied to the ITO bottom electrode. We are thankful to Center of Nanotechnology Department, IIT Guwahati, for SEM, AFM, and optical microscopy measurements. And we also acknowledge Mr. Ujjal Das and IT Silchar for helping us during IV characteristics. Thank you for your attention.
That's a nice presentation, Rajesh.
Thank you, sir.
Any questions from the participants? They can unmute themselves and ask a question, or if you want, they can type it in the chat. Feel free to interact with Mr. Rajesh.
So, hello, yeah.
Yes, sir.
So I think we have some extra time for questions for this talk because we are running ahead of schedule. So we can we will start the because the next talk is an invited talk, so we will start it at 2:30. So we have some extra time in case you want to take a 5-minute break or you want to have some extra discussion with the speakers. All are welcome. So, but we will start the next talk only at 2:30 because it's an invited talk and many people are looking forward to it.
I have one question to Mr. Rajesh. Mr. Rajesh.
Yes, sir.
You have shown in the graph the temperature difference for crystalline and amorphous, a very small, like 0.6 degrees Celsius, I think. When there is a 67.2 to 60, there is a huge change in the conductivity from amorphous to crystallinity. PO and
Yes, yes. PO, there is a very small difference in melting temperature, but crystallinity increases up to 60% when we add 1 weight percent of MOS2 to the PO.
So for your for this resistive based switching application, you are basically using PO MOS2 for your application.
Yes, PO and MOS2 nanocomposite.
So any idea why that small change, and how are you going to differentiate in case both the material needs to be used, or any idea, any focus on that?
I am not getting the question, sir. Can you repeat, sir?
Yeah, you have a very small temperature difference between these two materials, like both the two composite materials.
Yes, yes.
Like one is 67.2 degrees Celsius and the 67.8 degrees Celsius.
Yes, yes.
Now, in case you are going to use it for the RM-based resistive switching based devices,
yes, yes.
How are you ensuring that it has already been transformed for this resistive switching? Like the small, is there any variation for the small change? Like suppose there is a change, is there any yield variation which I want to ask?
Yield variation.
Like if there is small change in temperature.
Yes, yes.
So will that device get affected, or that, like if we again back to 67.2 degrees, will the temperature stop behaving resistive based memory?
I think it will not affect the device.
Okay, that's nice. One participant have asked a question. Karuna Kumari, what is the thickness of these devices?
Thickness of the this film.
Devices, yes, I guess that what you want to ask.
Yeah, basically
it is in the micrometer range. Very small. Thickness is very small.
So any figure or any number you want to specify like this?
Actually, we actually don't measure the thickness of this composite.
Rajesh, so which technique you have used to deposit this MOS2 layer?
Thermal evaporation.
Thermal evaporation.
No, MOS2 or top electrode, sir.
No, top electrode is aluminum is a top electrode, right?
Yes. We deposited aluminum by using thermal evaporation, and we deposit this nanocomposite POMOS to nanocomposite by using spin coating.
Spin coating.
Spin coating, yes, sir.
Okay. So what is the effective thickness of this MOS to PET thickness?
This is not we don't measure this thickness of the this composite.
Okay.
So
Okay.
Any questions from the participants? Any further queries? We have sufficient time for the interaction.
So do you have measure the retention and endurance measurement for this
no.
fixtures?
Retention and endurance measurement was not done.
Okay, so only the resistive switching characteristics, right?
Only resistive switching characteristics, and it's showing non-polar switching, and the conduction mechanism is given. So we did not measure the retention and endurance.
Okay.
One more question is from IIT Palakkad. What is the thickness of MOS2 layer, and what is the effect of switching layer thickness on the IV characteristics? Rajesh, can you answer this question?
Yes. So actually, we didn't measure the thickness, but for IV characteristics, the thickness should be very small.
No, but in the case of the resistive switching devices, in the case of the resistive switching devices, the effective thickness of the this MOS2 is very important for the all these measurements.
All these measurements, yes.
So
If the
it must
thickness
be
is
like
thickness, yes. Okay.
Hello participants, there is an important announcement from the ICW 2020 team. Actually, this neuromorphic symposium will be going here in hall 5 till 3:30, and after 3:30 to 5 p.m. we will have to shift in hall 6. Then at 5 p.m. again we will come back to hall 5. Thank you.
So Manoj, maybe you can write that instruction also in the text box for all the so that there is no confusion. Everybody can read it from there. So.
Yes, sir. Sure.
One more question from Mr. Vishal Sharma to Mr. Rajesh.
Yes,
what
sir.
is responsible for filament formation? Can you explain how trapped charge SCLC responsible for your set process?
So from literature survey, we get that when the slope is greater than 2, the conduction mechanism is mainly due to trap controlled SCLC mechanism. So when positive bias is applied to the aluminum top electrode, the aluminum is oxidizable and it may diffuse through as ions. So it may diffuse through as ions and conduction filament may form. So in case of positive bipolar set, the conduction mechanism may be mainly due to both electronic and ionic. So further characterization is needed. Suppose say that is so that we can see the conduction filament formation. Suppose from same image or there. After that, we can clearly say that how the conduction is actually formed.
Okay. Thank you, Yusuf. Once again, thanks, Mr. Rajesh, for his nice talk presentation and the hard work. Thanks for giving us a
Thank you, sir.
talk. So I will now request our next couple of inventory presentations. Next, it will be session chair. I introduce Professor Manan Suri to take the chair and invite our next session.
Mr. Supriya?
Yes, sir.
There is a one question actually. There's one question from this participant.
Yes. I think he's still there.
Yeah, wait.
Can you speak a bit loud?
So I'm saying just last question.
Yes.
Participants ask. Just wait. I'll send it.
So I request that in the interest of time, we take this question at the end or in the particular session. So because it's already 2:30 now. So
okay. Just a last question from Mrs. Karuna Kumari.
Yeah, so please hold this question for later. We already had a lot of Q&A, and we would like to thank the speaker, Mr. Rajiv Deb, for an extended Q&A session. I think he had to face more brunt of questions because the speaker before him was missing. So I really thank him for answering so many questions patiently. And now let's move on further with our first invited talk for today's session. So I would like to welcome Dr. Melika, who is a research scientist at the Institute of Neuroinformatics, University of Zurich and ETH Zurich. She has received her MS and PhD in electrical and computer engineering from the University of California, Santa Barbara in 2012 and 2016, respectively. Her research activities and interest is in the area of exploiting physics for computational substrate, for online learning, and for sensory processing. She is a part of the scientific committee of the Capocasia Workshop for Neuromorphic Intelligence, and is serving as a technical member of Neural Systems, Applications, and Technologies in Circuits and Systems Society, and as a technical program committee member for International Symposium on Circuits and Systems, which is ISCAS. And she is also the guest editor of Frontiers in Neuroscience and is the winner of the Best Neuromorph Award for 2019 Telluride Neuromorphic Workshop. So we are really honored to have Dr. Melika speak among us for the ICEE conference. So welcome, Dr. Melika. So please, we look forward to hear from you on your exciting research.
Thank you so much, Manan, for the invitation and for the great introduction. Thank you so much. May I share my screen? Okay, perfect.
Yes, please.
Do you see my screen?
Yes, it is visible.
Okay, perfect. Yes, so thank you everyone for coming to the talk, and thank you for inviting me. It's a pleasure to be here. I actually changed the title just a little bit to kind of reflect the latest thoughts that I have had. So I'm going to be talking about the algorithm circuits device co-design for neuromorphic intelligence. So I would first like to define some of these terms. So for example, neuromorphic intelligence, it sounds like a big word, but maybe we should kind of first define what these mean. So intelligence is something that a lot of people think about how to define, but I particularly liked a definition that François Chollet has on this recent paper on the measure of intelligence, which he defines as the ability to adapt to the environment and the general ability to acquire new skills through learning. So intelligence is basically the efficiency by which you learn new tasks that you did not know before, and on this intelligence on this is on display whenever you see a creature that adapts to a new environment. So learning seems to be at the core of intelligence. However, is expensive. So with the current deep learning models, there are lots of power, like kilowatts of power, and lots of memory, like terabytes of memory, that is being used to train these kind of models. So neuromorphic computing or hardware, we want to see if it can be used basically to reduce this kind of cost. And neuromorphic computing, in my opinion, this is just the way I define it myself, is just using the computational principles of the brain to build more efficient, intelligent machines. And by efficient, I mean in terms of power and in terms of memory. So how can we achieve this? So building neuromorphic hardware, basically this is kind of the recipe that I think about. So by trying to let time represent itself, so we're talking about being in an environment and defining intelligence by interacting with the environment. So and a real-time interaction is at the core of that. Also, kind of exploiting real time, continuous time, without having to do time step computation. So just letting the data come in continuous time and be data driven, and to do it more efficiently, sparsify this data in time, aka using spikes or using events. And these events or spikes will help to have less communication, and as a result, to have less power consumption. Also, another key another key component is basically having dynamics. So we're talking about having agents again in an environment that receive sensory information and natural signals, and then behaving. So these are all happening in multiple timescales. So dynamics is also at the core of that. And then also, space is also another dimension that we can use by co-localizing memory and computation also, which is, famously known as in-memory computing for, lower power, since the memory and the computation are co-located, the power to access the memory is lower. And then kind of use and exploit this massive parallelism for real time and for higher throughput, and also using multiple instances of these different computational units to basically do the same type of computation in parallel. So this is how we can use like time and space for building neuromorphic hardware, and these are the key computational principles that I care about when I want to think about building neuromorphic hardware. So an example architecture of how these things can come together is something, to put it simply, something like that. So we have always spikes in, spikes out. So we have spikes in doing some kind of computation, and then sending spikes out. And when we have, so these are basically our decoders and encoders. Whenever the spikes come in, we read from the memory that is sitting next to the processor. So at the onset of the spike, we read the memory. It could be any type of memory, and then we sum the values of the output of these memory, and we feed that into some kind of dynamic, some kind of block that generates some kind of dynamic, and then feed that into a nonlinearity or a neuron that integrates these and generates spikes for the next layer. And of course, this loop can also close if we want to do a recurrent computation. So now that we have talked about this architecture and these principles, let's try to see how can we apply them to real problems. So the thing is that we have a set of applications that we want to deploy, and then at the bottom of the hierarchy we have a substrate which has a certain physics, and we could either think about this problem from a bottom-up approach, so basically looking at the physics of the substrate and then see how from the substrate we can derive algorithms and then reach to the applications, or we can think about it from a top-down approach and look at the application we want to do, develop algorithms, and then map that to the substrate. And the question is, can we do both? Can we somehow meet somewhere in between? And I'm particularly in this talk, I'm going to talk about this part of the hierarchy. So basically going from the substrate to the algorithms, and also algorithms to the substrate. So first, in the first part of the talk, I will talk about this bottom-up approach, and then I will also tell you about some algorithms that can be mapped into the substrate. So first, how can the physics of the substrate guide us for building neuromorphic hardware? So I'm going to give you different substrate characteristics, and then I kind of explain how have we used that for for building these key principles of neuromorphic hardware. So, for example, the first thing is CMOS fully depleted silicon on insulator process, which has so this is a bulk CMOS, and in the FDSOI you have this this box, this ultra thin buried oxide layer, which kind of confines the channel, and as a result of that, it lowers the leakage, and also it has lower parasitic capacitance. And another nice thing is that you can use body biasing, so you can bias the body, change the threshold of the transistor, and change the minimum current that can pass through the device, or dark current. So you can have very low power processing with this kind of technology. So how can we use that for some of these key principles? So for example, I told you about the multiple timescale dynamics, which is very important. So, you know, if we want to interact with the environment with signals that are changing with tens of hertz or hundreds of hertz, or acting on it with like behavioral timescales in the order of seconds, we need to have all of these timescales on a chip. And it's not very easy to get these kind of large timescales because you would need large capacitors to do that. So there is this this DPI circuit, which is a differential pair integrator. It implements this differential equation, which is a first order differential equation, which takes spikes as an input and generate exponentially decaying signals at the output. And the height and the time constant of the signal can be changed by changing this the biases of the tail current, and also the biases in the of this transistor, which changes how much this with what speed this capacitor is discharged. So by doing by exploiting these features of body biasing, we can achieve we can change basically this I tau, and going from all the way from 6 seconds of time scale to tens of milliseconds, which is a very large range. So this is a very nice building block that we can use, for example, to generate one of these key principles that I told you about. Also, we could use this FDSI feature for very low power nonlinear neurons. So as I said, this body biasing kind of reduces the minimum current that can pass through the device, and then we can generate spikes that are we can generate spikes with an energy that is very low, 16 picojoule in this case. I can quickly explain how this neuron works. So it implements the exponential adaptive exponential neuron, which is defined by these differential equations. So we have an input stage, which is the leak of the neuron. So it's just basically the integrated time constant. And that when it gets integrated, it just gets compared with a threshold, and when it passes the threshold, it generates spikes and does handshaking, asynchronous handshaking with request and acknowledge for the entire network. And there's also this adaptation, which is a feedback, which is basically implementing this this adaptation. The key principle is the key thing that I want to get across here is that you can use the FDSOI features for doing very low power neuron also. The other technology that is also very promising for neuromorphic, as I'm sure a lot of people know here, is, for example, ReRAM. And just in case there's someone in the audience who doesn't know about resistive switching, basically resistive switching happens as a result of a formation of or a rupture of a filament, and the final resistance is a function of the geometry of the filament. And currently, we can control this filament through pulse train, pulse width modulation, pulse height. But there are some particular characteristics about RRAM, for example, and there's a cycle-to-cycle variability, which has been studied by actually many people. For example, by Luskub, also Manan, and other people. That basically it shows that the switching time of the devices when you apply a voltage across it it follows a Poisson process, which means that it's a random process, and the probability of switching follows a Boltzmann distribution, in which it's an exponential function. So we wanted to kind of use this also for learning. So we have done some also measurements in Leti on a 4 kilobit array of half-neon oxide based devices, and as you can see, indeed, even in a large array, you can see that the set probability can be controlled by the voltage that is applied across the device. So how can we use this for learning? We can, for example, use the simplest as a first step, the simplest form of learning, which is simplest form of supervised learning, which is known as delta rule. So it's a simplest form of gradient descent for single layer networks that minimizes the least mean square of a network, and the update is a function of the error of the network and the input. So we can treat the devices in a binary form and then try to map this weight update into them by switching them stochastically. So we know that the probability of switching is an exponential function of the voltage. If we apply a voltage that is a log of the error, and then we can get a probability of switching, which is a linear function of the error that is in the system. So basically, we have a binary device, but we switch it probabilistically with a linear function of the error that is there. But then this voltage that is here could be a very precise value because it's a log of some error. So how can we generate that? The solution that we propose is to use apply a ramp voltage whose slope is a function of the error, basically. So whenever the error is higher, we have a higher slope, and whenever the error is lower, we have a lower slope. And in the time of programming, basically the final voltage will be the voltage that will be the maximum voltage that could or could not switch the device. There are some circuits that implement that compares the iNeuron with iTarget. If they're similar, it will generate a flag that the learning should stop. Otherwise, it normalizes the neuron and the target, so compares them. And then the difference of, and also generates a direction of which one is higher or lower through this amplifier around. And then depending on the direction, it will either push current into this capacitor or take current off of this capacitor to generate the ramp voltage that we would like. And at the end, you see that the voltage that is applied across the memristor is it becomes a log function of the error like we wanted. We just to put this in an architecture, we can, as I said, this is similar to the architecture that I explained before. So we receive spikes, give out spikes, goes through this memristor array as synapses, goes through dynamics to the neuron, and then also we have a learning block that compares the neuron's output with a target and generates this up and down voltages stochastically with this ramp voltage that is basically inside this learning block now. We modeled these in a system level simulation and benchmarked it on MNIST, and you can see that even for a 1-bit device, so you just have, if you have just one synapse that is binary, but you are switching it probabilistically, you can get maybe up to 85% of accuracy. This is the error plot. Another feature of ReRAM that we have used is the cycle-to-cycle variability in reset operation. So the final high resistive state is also a function of the V reset, and it's log normally distributed. So every time you set and reset the device, depending on the reset, you have a mean value of high resistive state, and then you sample from a high log normal distribution every time you reset. If we plug these devices as a high resistive state into the neuron, so we basically get here a time constant, so an RC that is building the time constant, and here another RC that is, for example, building the refractory period of the neuron. And incorporating ReRAM into the neuron has many advantages. One is that, for example, we know if it's a high resistive state, we can get this long time constants that we desire. And also they're individually programmable, so you don't have to share biases between all the neurons. It also overcomes the von Neumann bottleneck because you actually literally have the memory and the processor co-localized exactly in the same block. And also it doesn't, because each neuron is calibratable, you can calibrate each neuron by itself, it also doesn't suffer from mismatch. And the cool thing is that since now each neuron can change its properties, then you can even use it for learning. So each neuron can self-organize its resistance to implement some kind of plasticity, for example, intrinsic plasticity, to keep the firing rate of itself within some healthy range, so not being overactive and not being underactive. So the algorithm is basically that if the firing rate of the neuron is much higher than it should be, then with a certain probability we set the device and we reset it and sample from a log normal distribution to make sure that it stays within this range. And if we can, by doing that, we can, for example, in a recurrent network, make sure that the population dynamics of this basically population of neurons stays in the firing range that we desire in a long time scale. So here, for example, you see that in the beginning, the neurons are very active, or some of them could be non-active actually. So then the number of set and reset cycles are a lot, but then the neuron the neuron self-organizes its conductance, so that the firing rate drops, and then and the number of set and reset also converges to 0. Another property which is also interesting to use is the compliance current of a ReRAM. So we have collected some data from again this 4 kilobit array of hafnium oxide, which is integrated between the 4th and 5th metal layer of a 130 nanometer technology. We have made each device go through 100 set and reset cycles, and we measured the conductance of the device by changing the compliance current from 10 microamp to 400 microamp. And as you can see, this is a log-log plot. It has a monotonic relationship, the final conductance to the compliance current. And what we have done is that we have also tried to implement this delta rule, which is again the simplest form of gradient descent, by using this physical property. So what we can do, for example, is that we can first randomize these devices, and what we can do is to first read from the devices, calculate what the error is, and then sum the error with the current value of the device, and come up with the next what the compliance current should be to arrive to the conductance that is desirable. So when doing that, if you want to put it in an architecture, you can have the similar architecture that I was talking about. You can get a firing rate from the neuron compared to the target, and generate this compliance current. So whenever there's a read signal, we apply a read across the device by putting the appropriate voltages on the bit line and the source line. Then we always have to reset the device and then set it with the compliance current that the learning block has generated. And in this way, we have really realized that although we are treating this device like a binary device, because we're always basically just either setting it or resetting it completely, by just putting this limit of compliance current, although we're really treating it like as if it's binary and we're not really trying to control exactly the conductance, we end up with a uniform distribution of conductances when, for example, applied to a problem like MNIS. So we are going to apply it to the first 5 digits of MNIS. And by taking the model into account, after 3 epochs, we achieve something like 93%. And as you can see, the final resistance is very uniformly distributed. So this was kind of the first part, which was more of a bottom-up approach to use the cycle-to-cycle variability of set, cycle-to-cycle variability of reset, and also compliance current for implementing learning. Also, there's some top-down approach that there are some new algorithms that are being developed, because the challenges has always been that for spiky neural networks, the right algorithms are not there, and the success of deep learning is as a result of gradient descent, but we don't have gradient descent for SNNs. But and also the implementation of them, needs local information and analog memory. But these problems are now kind of being solved by these interesting methods such as surrogate gradient learning. So what we can do is to define the network, define the equations of the neuron by these following equations. So basically, we have the membrane potential of the neuron, which is a weight times the synaptic times the dynamical state that is being integrated. So P is the neuron's filter output. Q is the synaptic dynamics. So basically, the neuron is receiving the synaptic dynamics as an input. It's integrating it, and then the membrane potential is basically the output of that integration times a weight. And then there's the refractory period, which for now we can ignore. So if we assume a global cost function that we want to minimize, this global cost function, basically you can define it by chain rule as a derivative of the loss as a function of with respect to the output, the derivative of the output with respect to the membrane potential, and the derivative of the membrane potential with respect to the weight. So this is basically the error. This is the postsynaptic. You can call it the postsynaptic part, and this part is really the kind of the presynaptic part. So the du, the derivative of the membrane potential with respect to the weight is this P, which is the neuron's filter output. So basically, we have a pre, we have a post, and we have an error. So this is called a family of basically 3-factor rules that can approximate that are actually equal to back propagation. But the problem is that this second term is non-differentiable. So this is like the derivative of the spike with respect to a membrane potential. And but although it's non-differentiable, well, you can assume that it's kind of a sigmoid. So it's instead of a jump, you kind of think that it's a smooth function, and then you can define the second term as a box function. So basically, whenever the membrane potential is between some minimum and maximum value, you assume that the box function is 1, and otherwise is 0. So then then the weight updates kind of becomes the error times the synaptic the neuron integration state, and then also what you can do times this box function. And then what we can do is to also encode these errors into events. So now we can say that we want to do an update whenever there is an error, and whenever the box function is 1, we just read this p and we get our weight update. So you can implement this by some simple architecture like this. So we have the Q, which is the synaptic dynamics. We have P, which is the neural dynamics, that they can go into a vector matrix multiplication, go to just the spiking state, just to see if it's higher or lower than the threshold. And then we feed this output of the spikes into an error generation unit, which then encodes these into error events. And these error events can either be propagated or not, given that this box function is 1 or not. And we have used this mechanism of encoding error into events on 2 benchmarks of devious gesture and NMness, which is a neuromorphic MNess. And depending on the number of how much the bound you put on the error event, you can get more or less errors. So if you want lower events for lower powers, so lower programming, then you will tolerate more errors, but you can increase this error event to achieve also lower errors. And you can also implement it in a neuromorphic architecture, like I was saying before. So this is kind of the same concept, it's just more detailed. So again, the spikes propagate through this Q and P, go to the VMM, and go to the spike generation block, and they get communicated through the to a spike encoder. And then we can have like an error calculation block that can implement any kind of cost function and encode this into errors. And then these error events can be communicated back to the neuromorphic core through an arbiter. And whenever there's an event, we look to see which neuron it belongs to, and then update the synapses of that block. This is a recent work that we did, is just published. If you're interested, you can go look at more details. But I think my time is up, so I'm just going to conclude. So neuromorphic hardware basically provides a power and memory efficient platform for building intelligent machines. And the solution really has to come by combining all levels of abstraction. So going from application to algorithms to circuits and to devices, and doing a code design. And with that, I would like to acknowledge all my colleagues, all my collaborators, and I'm happy to answer any questions. But before that, I'd just like to do also one announcement about a monthly series that we are organizing under the European project Neurotech. It's a webinar series, and the next one is coming up. It's next Tuesday, with the title "What are the hardware opportunities for neuromorphic engineering?" It's free. You can sign up here if you like. And yeah, and that concludes my talk. I'm happy to take any questions.
Okay, thank you, Dr. Melika, for the nice, entertaining talk. And we are open for questions now. So please, if there are any questions, kindly post them in the chat box. Yeah, Manoj, I think you are collecting the questions, right? So can you please forward them? So.
Yeah, so far there is no question from participant side, sir.
Okay, okay. So because for some reason in my panel, I'm not getting the questions from the participants directly. So
Okay, okay.
okay, so let's thank the speaker once again. And Dr. Malika, thank you for the talk. And we would now move on to the next speaker. So next we have
Thank you.
Professor Daniele Elmini with us. So I would introduce Professor Elmini. So Professor Elmini works at the Department of Electronics and Information Technology in Politecnico di Milano. He received his laurea cum laude and PhD in nuclear engineering from Polytechnic di Milano in 95 and 2000 respectively. He held visiting positions at Intel, Stanford, and UIUC. His research interests include the modeling and characterization of NBM, such as nanocrystal memory, charge trap memory, phase change memory, resistive switching memory, RRAM, STT, MRAM, and so on. In 2016, he co-edited the book Resistive Switching from Fundamental Redox Processes to Device Applications for Wiley. He has co-authored 15 book chapters, more than 250 papers published in international journals, and presented at international conferences, and has 8 patents. His works received more than 10,000 citations with an H index of 58. He has served in several technical subcommittees of international conferences such as IDM, IRPS, SISC, Infos, ISCAS, and so on. He is associate editor of IEEE Transactions on Nanotechnology and Semiconductor Science and Technology, IOP SST. He has also received the Intel Outstanding Researcher Award in 2013, the ERC Consolidator Grant in 2014, and the IEEE EDS Paul Repo Award in 2015. And he is a fellow of IEEE. So let's welcome Professor Elmini, and it's really great, and I must say it's actually inspiring to have you here, because everyone or all the students and the young researchers who have been reading about RRAM, there is no way that they can skip reading about your works, some of the seminal and foundational works. So it's really inspiring to have someone like you in between us and enlighten us with your highly anticipated talk. So the floor is yours now, please, Professor Elmini.
Thank you, Manan. Thank you for your introduction. Too kind. You're too kind. And thank you for inviting me to Icee. It's a real pleasure for me to be here today and give my talk. And thank you, Melika, for also very nice presentation before me. And I really enjoyed the presentation. And she actually anticipated some of the concepts that I want to share with you today. I will try to share my screen now. I hope you can see. I hope you can see my slides. So the title of the talk is Neuromorphic Computing via Device Physics in Resistive Switching Memories. And today I'd like to follow this outline, which is first of all I will start with an introduction and then talk about the long-term plasticity using non-volatile RRAM, resistive switching memory, and related computing networks. And then I will move on to discuss the short-term plasticity, including using volatile resistive switching memories. And then I will also present some of the computing networks that we have implemented using this volatile RRAM. And then I will conclude my talk. So first introduction, you might be familiar with this very famous plot where this is the True North paper by IBM showing that if you look at the power density and clock frequency for the microprocessor CPUs, the central processing unit in conventional computers, since 1971, due to Moore's law, Moore's scaling law, there has been an increase, a relentless increase of both power density and clock frequency. But at the end, we are facing a major challenge now because the power density is so large that the heat dissipated within the chip cannot be sustained anymore. The temperature is too too large. So we have to face this so-called heat wall due to more scaling load. But at the same time, the human brain is sitting on a very unique place here at a very low power density and very low clock frequency. The total power consumed by our brain is in the range of 20 watts, which is really amazing in terms of what the functionality of the human brain is. Instead, we can recognize objects, we can learn a lot, we can make abstraction, we can make decision, and so on. So what is the secret of the human brain, and what are the problems regarding the conventional computers? Well, one of the problems is the phenomenon architecture, which you can see here. Generally, the central processing unit and the memory are separate one from each other. And this causes a major memory wall or memory bottleneck because of the data always continuously going back and forth between the CPU and the memory. And at the same time, the human brain, there's no such kind of memory wall because the neurons and synapses are actually co-located within the brain. And this has inspired the in-memory computing as a concept for running the computation, executing the computation directly within the memory, within the data, in situ. So in-memory computing has become a really popular concept and popular research topic nowadays. There has been mainly three trends in memory computing, which I'm summarizing here. One is the artificial neural networks, ANN, including deep neural networks, CNN, LSTM, based on supervised training. This, I think, is the major trend nowadays. Most of the research groups and companies are actually working on this topic. And the second one, which is the topic of my talk, is the brain-inspired neuromorphic neural networks. And then finally, there is a most recent trend, which is the algebra accelerators, how you can use in-memory computing to accelerate algebra algorithms such as the matrix vector multiplication, linear system solver, inverting matrices, doing regression, eigenvector problems, and so on. So now, for today, I'm going to focus on this part, which is related to unsupervised learning, continual learning, and spatiotemporal networks especially. But the main emphasis in my talk today will be about the how we can implement neuromorphic computing or accelerate or make neuromorphic computing more energy efficient and more space efficient and cost effective by using device physics. So if you look at the typical neural network, biological neural network, here it can be summarized like this schematic where you have several neurons, presynaptic neurons here and postsynaptic neuron here, with neuron soma, axon, synapse, dendrites. And it turns out that each of these individual pieces of the neural networks can actually be implemented in hardware in a very effective way. For instance, the soma, neuron soma here, one of the functions of the soma is to actually collect all these spiking inputs, which are multiplied by a synaptic weight and then collected or summed within the soma. And this can be very effectively, very efficiently implemented by matrix vector multiplication in cross-point arrays, because here the multiplication is done physically by Ohm's law and the summation is done physically by Kirchhoff's law in a circuit. Another example is the integrate and fire neuron. This is a very popular model for neurons where if you apply spikes to the neuron input, the membrane potential will accumulate all these spikes. And this can be very effectively implemented by pulse accumulation in phase change memory, for instance, where if you apply spikes at the input of a phase change memory, these will lead to incremental crystallization within the phase change volume. Also, resistive switching memory is capable of such integrating function. Dendrites also. Dendrites are known to have a role in filtering the input spikes, and this has been very recently demonstrated by using switching and relaxation in uniform switching RRAM. But the topic of my talk will actually focus on the synapse here. Synapse is responsible for learning. And we have several examples of, for instance, long-term synaptic plasticity, where we For instance, STDP is the spike time independent plasticity, which is a learning rule, one of the learning rules in the brain, where we can learn in a permanent way based on the spikes. And this can be implemented by set-reset transition in non-volatile RRAM and PCM. And another function of the synapse is the short-term synaptic excitation, where if we apply spikes to the synapse, this will respond with the so-called EPSCD, excitatory postsynaptic current, which is a transient current, exponentially decaying current, which can be implemented using set transition in volatile RRAM. So I'm going to focus on these last two aspects, the long-term plasticity and short-term plasticity. Let's start with the long-term plasticity first, that can be implemented using non-volatile RRAM. So Melika has already shown a very nice introduction about this concept. I'm not going to spend too much words. This shows a bipolar switching characteristics for our device, which is titanium hafnium oxide carbon stack, showing set transition, reset transition. You can use a compliance current, and that will allow you to tune the conductance in a very analog way, continuous way. But the problem here is how you can implement learning in this resistive switching memory, in non-volatile resistive switching memory. One example is STDP. STDP is summarized here. Assume that you have a presynaptic neuron, or pre, and a postsynaptic neuron, which are connected by a synapse. And let's assume that the presynaptic neuron it delivers spikes first and then followed by the postsynaptic neuron. In this case, the synaptic weights is expected to increase based on the STDP rule, which is summarized in this chart. You can see the delta G, or the change of the conductance of the synaptic conductance, is increasing by long-term potentiation for positive delay. And if the opposite sequence takes place, which means the postsynaptic neuron spikes first and then followed by the presynaptic neuron, then in this case, you will the synaptic weight will instead decrease by long-term depression. And this has been observed in the brain, in the hippocampus. This shows some experiments by BM back in more than 20 years ago. So now we have realized a way, RRAM structure, which is based on 1T1R structure. This is the RRAM device connected to a transistor. This is a very popular structure of the RRAM device. And this is the synapse, basically, very, very simple synapse. And this is connected to the presynaptic neuron here, where the spike is applied to the gate terminal here. So whenever a presynaptic spike is applied to the transistor, this will induce a current spike, which is fed to the postsynaptic neuron, which is modeled as an integrated fire neuron. So every time a spike arrives, is being integrated, and spike after spike, the membrane potential will eventually reach the threshold, at which point the postsynaptic neuron will also send a spike. But at the time of the postsynaptic neuron spike, we also send a feedback spike back to the top electrode. And based on this feedback spike actually includes a positive pulse followed by negative pulse. So now if there is any overlap between the presynaptic spike and postsynaptic spike, which means that the delay between pre and post is actually very, very short, you might end up with two situations. The first one is the positive delay results in overlap between the pre-spike and the post-spike, the positive pulse of the post-spike. And this will lead to set transition across the RRAM and potentiation. On the other hand, if the delay is negative, the overlap will take place over the negative pulse, and this will lead to reset of the device. And we have demonstrated this experimentally using one analytical RRAM device, where this summarizes the experimental results. This is the change of the conductance as a function of the time delay between the spikes. And you can notice that for positive delay, delta t, between 0 and 10 milliseconds, there is an increase of the conductance, which means potentiation, and for negative delay, there is depression instead. And this is very accurately reproduced by model simulation. And this once again shows the comparison with the biological STDP rule. There is a major difference in the shape because the biological data seems to suggest an exponential or hyperbolic shape of the STDP, whereas In this case, we have rectangular shape. It really doesn't matter what's the shape of the SDP. The most important fact is that you have potentiation for positive delay and depression for negative delay. And we have used exactly this concept to demonstrate learning. So we implemented this one layer, very simple neural network where you have 16 presynaptic neurons which are stimulated by spikes. And these are all connected, fully connected to just one single postsynaptic neuron by 1T1R synapses. This is the schematic of the hardware that we implemented. So we have all the synapses, 1T1R synapses, and then we have the Arduino Due was used to serve as both the input neurons, sending all the input spikes to stimulate the gates of the 1T1R synapses. Then the current was collected at this node, converted to voltage, and integrated by Arduino. And then fire is also represented by Arduino in the form of a feedback spike applied to the top electrodes here. So this was aimed at demonstrating self-learning neural network, where basically if we stimulate our neural network with some input, some spiking input, the synapses will adapt or will adjust to the input pattern in a spontaneous way with no need for any external supervision or any external feedback. And this is demonstrated here by this animation. I'm going to show you now. The input pattern is shown here. We apply a diagonal in this case. We initialize all the synaptic weights in a high resistance state, which corresponds to red or black. And you will notice as I start the animation that by submitting this input pattern, the synaptic weights immediately adjust to the shape of the input pattern. And we also try to complicate the situation for the network, initializing the weights in a random way initially. So here you might have high resistance states in black or low resistance state in white. And now, once again, if you run the experiment, if all the diagonal synapses will increase their conductance, all the other synapses will decrease their conductance based on long-term depression, as you can notice by these blue lines. And this was actually thanks to the presence of some noisy spikes, which you might have noticed in the pattern. So now one application, real-world application of this unsupervised learning is continual learning. Continual learning is very important. We as human beings are capable of learning each and every day, so we can accumulate knowledge. And this is what is actually creating our person, our intelligence, our conscience. Whereas the AI, artificial intelligence systems so far are not capable generally of this continual learning. For instance, if you take a deep neural network, this is trained initially by some knowledge. For instance, let's assume a data set of animals, for instance. And if you want to add, after this initial supervised training, if you want to add some more knowledge, you to retrain your network with this new knowledge, you will lose all the previous information. This is so-called catastrophic forgetting. So we try to combine the high accuracy of the supervised training, which is shown here, including a CNN, convolutional neural network, and a combinational logic, with the flexibility and plasticity of the unsupervised learning, thanks to this concept of the STDP. And we demonstrated that by using this combination of a supervised and unsupervised learning, we could actually achieve continual learning by adding more information after the initial supervised training. And we achieved up to 50% of additional information that can be classified and can be clusterized by the and subsequently recognized by the network. Okay, so let me change gears now to go to the short-term plasticity part of the talk. Now, we implemented short-term plasticity by using volatile RRAM. So volatile RRAM is basically similar, or actually the same concept as resistive switching memory that I showed you before, but this time the top electrode is silver, and this leads to a unique feature, which is that if I apply a positive sweep like this, positive voltage sweep, I can switch on the device. which means that I can form a conductive filament across the switching layer, in this case, the silicon oxide. But if I remove now the bias, go back to 0, I observe switching off of the device. So the device does not want to remain in the on state because the filament spontaneously dissolves across the silicon oxide. I can repeat the same switching across the negative voltage, which means that the device is actually bidirectional switching device. And I can repeat the switching on and switching off over and over in the device, but every time the filament dissolves spontaneously. And this kind of switching dynamics can be better observed by a time-dependent experiment where I apply a switching poles or spike across the device. And then I monitor the current. And during the writing spikes, I can see a writing current. And then during the read phase, instead, I can see a persistent current, which means that the filament is actually on for some time. And then eventually the device switches off. And this is the so-called retention time, which takes about, in this particular experiment, is around 300 microseconds. That can be even longer, can be up to 1 second or several seconds. And this was modeled by using this numerical simulation model, which describes the surface diffusion of silver. So if you start with a conductive, continuous cylindrical filament, then you notice that over time the filament collapses in several spheres, and this is actually has been observed also by TM observation, where you start with a continuous filament and then you end up with some clusters or droplets of silver. Now, a nice thing to link this volatile iron device with the neuromorphic computing is that this device actually resembles quite nicely the synapse, the biological synapse. Because in a biological synapse, the excitation of the presynaptic end of the synapse will result in the release of a neurotransmitter, such as this L-glutamate, which is one of the many neurotransmitters in the brain. And this neurotransmitter is actually collected by the receptor, which ends up in the opening of the ionic channel. And it is this opening of the ionic channel that actually leads to the collection of calcium and sodium and the so-called excitatory postsynaptic current. And this is exactly the same or very similar to the operation of the device, volatile device, where you first form the conductive filament thanks to the ionic migration of silver, and this is equivalent to the neurotransmitter activating the ionic conduction opening. And then once you have this channel in place, then you can collect electrons. So the electrons can flow across the filament. And this is the same as the calcium ions flowing across the synaptic membrane. And if you look at the individual ionic channels, they show kind of stochastic time-dependent behavior. And this is very similar to the R-RAN device. They show, which show conductive filament, which is active for some time, and then they switch off in a stochastic, displaying a stochastic retention time. But the nice thing is that if you collect many of these ionic channels, which in fact you have many of these in the synaptic cleft, eventually you have the EPSC, excitatory postsynaptic current, which is very nice exponentially decaying current. And you can do the same using volatile R-RAN by collecting many of these stochastic current response. You end up with exponentially decaying current. So what do you do with this volatile R-RAN? You can actually achieve spatiotemporal recognition. So assume that you have two branches. One is the excitatory synapses, okay, with some of these volatile R-RAN devices, and then you have an inhibitory branch. And now you're collecting the two currents, excitatory current and inhibitory currents, and you're subtracting the two of them, resulting in the EPSC. Now assume that you submit a certain sequence, A and B, And you might submit the pre-first sequence, which is first A and then B, and the two currents will subtract in a way that the resulting EPSC shows a positive current peak, like this. And in the case of the non-pre-first sequence instead, if you have B followed by A, the EPSC will actually be negative, which means that you can actually, by placing a threshold current like this, okay, 3 microamp, for instance, you can discriminate the pre-first sequence over the non-pre-first sequence, which means that you are able actually to reproduce partial temporal recognition, which is able to recognize not only which neuron fires, but also when it fires. Okay, you can extend this concept to the so-called direction selectivity in the human retina. What happens here is that you have in the retina, in our eye, basically, you have the direction selective ganglion cell, which is a special neuron with a receptive field that can collect excitatory branches and inhibitory branches, all being excited by the photoreceptors within the retina. So let's assume that you have these receptive fields with excitatory branches and inhibitory branches, and you have something moving, okay, in front of your eye. You see an object like a bird moving. And depending on the direction of this object, okay, assume that it is moving toward the right. And so in this case, you are exciting first the excitatory branches, then the inhibitory branches, which result in a positive current. And in case of the opposite movement, instead, you will see a negative current. Sorry, now I have, sorry, my Skype started. In case of the non-prefer or the opposite direction, like B to A, moving, the object is moving toward the left this time. Now you have a negative current, which means that you can actually recognize and select the direction. 0 degree will be characterized by a large current, and 180, which means moving toward the left, will be characterized by a low current. And this can be extended once again, by looking at the retina. If you look at the retina, actually, there is a very nice architecture of the ganglia, which have 4 receptive fields, and they are organized in a crossway with north, east, south, west direction. And they are arranged more or less like this. This might be a hardware implementation of this direction selective ganglion with the 4 receptive fields. And now assume that you have certain direction of the object, like moving from toward the west. Okay, so moving toward the right. In this case, each of these 4 receptive fields will respond in a different way. For instance, the east will have a positive EPSC, followed by the west showing negative EPSC, whereas the north and south, they just remain more or less silent. It's just some noise. In the case of the opposite direction, the west will respond with positive poles and the east will respond with negative poles. And again, north and south will not respond. And you can repeat the same idea, same concept by moving toward the south or toward the east. And for any direction, you will have a special and unique configuration of all these 4 receptive fields responding in a different way. And by using this concept, you can actually, at the very device level, at the very level of the sensor, using this unique physics of the volatile RAM, you can recognize the direction in a very quick, very fast way. So this concludes my talk. I want to draw my conclusion now. The purpose is to show that neuromorphic computing can actually be matched by emerging memory device and emerging memory physics. And you can implement several of these functions like synapse, dendrites, neuron soma, and many others, I'm sure, by using the very unique physics of these devices. So I've shown a couple of examples. One is non-volatile RAM. implementing STDP for unsupervised learning and continual learning. And the other one is the volatile run, which is capable of stochastic timing, spatio-temporal recognition. And one of the nice thing actually is the time constant that you can achieve with using these devices is in the range of like microsecond and millisecond and even few seconds, which by using the conventional CMOS architecture or CMOS technology might need very large capacitors. So this is a very important aspect to minimize the area and cost of your circuit. And also, as I have shown, this volatile RNA physics enables the direction selectivity directly at the level of the sensor and memory device. And by that, I want to acknowledge my fantastic group of people, PhD students and postdoc fellows, and acknowledge also the sponsors of my research. And thank you very much for your attention.
Thank you, Professor Elmini, for the nice talk. So I think we have time for quick one question, and then we will move to the next hall. So I think we have one question here regarding the test validation accuracy values for resolving the MNIST. So if you can just briefly touch upon that. So.
Okay, I wonder if this is a question to my talk, because I actually did not mention the MNIST. This is most relevant to the, because we haven't really touched the problem of MNIST accuracy for unsupervised, using unsupervised learning. Yes, so the MNIST recognition, actually, we have done some other works related to the artificial neural networks, which was not covered by my presentation, like this. Sorry, let me move on. Yes, this concept is artificial neural networks. We have implemented MNIST recognition by extensive array of RNs. We have achieved like in the range of 85%, I guess, using a real devices, 4,000 synapses, but using supervised training and multi-level weights in the RRAM. If you are referring to the brain-inspired neural networks, well, MNIST is, I think, kind of now we are actually, you need to, unsupervised training of the MNIST is actually a very tricky task for hardware, and even for simulation. You might use the surrogate gradient descent technique that Melika has shown. We have done some attempt to recognize the MNIST using this continual learning concept. But once again, this continual learning concept, let me show you the slide. This continual learning concept also includes continual supervised training. So you need some supervised training first to recognize the MNIST, and then you might add some more numbers. Okay, like you train your network by supervised training of 7 numbers, and then you can add 3 more numbers, like the 8, 9, and 0, for instance, and then you can check if the system is capable of recognizing these 3 additional digits. And the answer is yes. We have demonstrated that the system can actually recognize these additional new digits, which were not presented during the supervised training. The accuracy, I don't really have the number on the top of my head. I can look up the paper.
Okay, I think that should be fine. So once again, let's thank the speaker. And I think I have an announcement for the remaining session. We have to move to hall number. We have to change the hall for the neuromorphic because there will be a poster session here. So that is. So is that hall 6 or hall 4? Manoj or Ahmed, can you please?
It's hall 6, sir. It's
hall 6. So we have to move to hall 6, right? Okay. Okay, so I request all the attendees for the neuromorphic session that further for neuromorphic related talks, memory or emerging devices, they should move to hall 6. And once again, let's thank all the speakers for this session. Thank you.
All the participants for emerging logic, memories, and neuromorphic devices, please shift to hall number 6. There will be one invited talk followed by poster presentation. We'll be back here again at 5 o'clock in the same hall number 5. For the time being, you please shift to hall number 6.
Hello, Icee EE 2020 co-host or host. Can you just put on the slide which says this is now the poster session?
Yes, sir. Sure, sir.
Yeah. Hello, Professor Ananjan. You are there?
Hello, sir. I think
Okay,
Professor
so
Ananjan is
welcome all the participants who are now about to present their posters. Probably if the bandwidth is not too limited, you can switch on your videos. Yeah, Professor Ananjan is here.
Yes.
So in this session, we have 12 posters. And I think, we asked the presenters to display their posters and discuss for about 5 minutes. Following that, we will have 1 or 2 questions by the audience for 1 or 2 minutes. And then we move to the next poster. There is a sequence that we have got from the organizer side. We will go by that sequence. Okay, so the idea is that you basically display your one slide poster of, or if somebody wants to go through 3 or 4 slides to discuss the entire poster, that is also fine with us. Okay, we are a little bit late because of the earlier thing that was going on in the same hall. But I think let's get started. So the idea is that each participant gets 5 minutes to present, to discuss the poster, and then for 1 minute we basically take up the question. Is it okay? Yeah,
Yes.
Professor Ananjan, shall we get started or?
Yes, just one piece of advice for the presenters. When you present, you have really very few minutes. So please discuss right away the essential part of your presentation. What exactly are you saying? Don't waste time on background information and historical things and all that. Okay. So please quickly come to the crux of the matter. What exactly is it that you have done? What are you trying to say? What is it new that you have contributed, and why is it important, and how is it useful? Okay. So please keep in mind we have very little time. Okay. So I think we should get started right away. So
Okay, perfect. So the first poster, the poster number is P232, is by Mr. Sandeep Kumar. The title of the poster is Metallic Spintronic Ultrafast Terahertz Emitters, Tunability through Bi and Tri Layers for Intense Broadband Terahertz Pulses. So Mr. Sandeep Kumar, you can get started.
Yes. Screen visible?
Not yet. Yeah, now we can see. You can basically zoom in that portion which you want to discuss first and then go on like that. Okay.
Okay. Start.
Yeah.
Good afternoon, everyone. I am Sandeep Kumar. The title of my poster is Metallic Spin Ultrafast Emitter, Tunability through Bi and Tri-Layer and Broadband Terahertz Pulses. The terahertz radiations are the part of electromagnetic spectrum situated between infrared and microwave region and are important because of their unique application in the field of science and technology. There are various mechanisms and sources of the generation, but currently spintonic terahertz emitters got profound interest as it utilizes the spin degree of electron also and have several advantages over conventional test terahertz emitters. So spintonic terahertz emitters are the multi-layer combination of ferromagnetic and non-magnetic metal, material under the femtosecond laser excitation generate the terahertz electromagnetic radiation, where the inverse spin Hall effect play a crucial role in the generation process. To realize terahertz generation from these heterostructure, we have fabricated FEPT bilayer TA FEPT trilayer heterostructure on the substrate using ultra high vacuum R magnetron sputtering system. The good quality of the deposited samples were confirmed by the preliminary measurements on them. For example, X-ray diffraction, XRR, magnetic hysteresis measurement, etc. So after that, the samples were tested terahertz generation using the home-built terahertz time domain spectrometer, which is schematically shown here, where the terahertz is generated by the femtosecond NIR excitation of the spin heterostructure and detect electro-optic sampling scheme. The excitation and other meters used during the terahertz measurement are given here. The terahertz time domain signal generated from the bilayer and trilayer heterostructure, as shown in figure A and B, is plotted in figure C, and figure D represents the corresponding Fourier spectrum. The dips in the Fourier spectrum different frequencies to the terahertz absorption in air, and limited bandwidth is basically due to the pulse duration of the excitation beam and the detection crystal. Here in figure C clearly shows a odd enhancement that is around 40%, we have calculated, and in case of trilayer to their trilayer counterpart. The enhancement is attributed to the additional flow of the spin current to the second non-magnetic layer in case, and the conversion of that spin current into the charge current due to the inverse spin Hall effect. So in conclusion, we can say that tri-layer are more efficient for terahertz generation in comparison to the bi-layer, which is the one aspect. There are several other aspects also by which the terahertz emission can be tuned in such type of image. So with that, I would like to acknowledge my funding agencies and research facilities at IIT Delhi. So any type of questions and they are most welcome.
Okay. Thank you, Sandeep. So if there is any question, one question we can take from the audience, but he is available. You can put up the question. His email ID is given there. If you have more questions, you can write to him. Yes. So if there is any question from the audience, we can take it up now.
Sandeep, I have one question.
Yes.
I have one question. Here is because I am just wanting to ask what is the dependence on this bandwidth basically on the thickness of this particular these interfaces basically the device.
For the optimum bandwidth, we have to vary the thickness of ferromagnetic as well as non-magnetic layer. For a optimum thickness, we will get efficient good terahertz signal and corresponding bandwidth.
Okay, thank you. Yeah.
Okay. So thank you, Mr. Sandeep. So you can stop sharing the poster. Now we move to the second poster. The second poster is by Professor Priyanka Das. The title of the poster is Multiband Reflection and Transmission Mode Linear to Circular Polarizer Integrated Microstrip Patch Antenna. Poster number is 233. Yes, Professor Priyanka Das, please share your poster.
Sir, poster number P30 233
Sir, I
is
think she is not available here.
Oh, 233 is not there? Okay.
Yes, sir. 234 is.
Okay, so 234, the presenter is Mr. Rakesh Kumar Pandey, and the title of the poster is Silicon Ion Fluence Dependence Study of Surface Chemical Composition and Electrical Characteristics on Epitaxial Gallium Antimide. Poster number 234. Please, Ankit. Yeah, you can share your poster.
Yeah, hello. Good afternoon, everyone. This is Rakesh here.
Okay, so Rakesh is presenting. Okay. Yeah, please share the poster.
My screen is visible to everyone.
Yes.
Working on a group of indium arsenide based type 2 superlattices for IR detector in solid state physics laboratory, DRDO Delhi. And in fact, we are working on some contact processing after processing for contexts like doping we were looking at. I found that if I want to do doping through implantation, I checked two species, sulfur and silicon, and found an amphibic dopant, but it has much better behavior in terms of looking the doping characteristics. Also published a paper here in SP, and then checked the surface basically characteristics after implantation of silicon. So we looked at AFM and XPS and some electrical characteristics also we have I am showing here. The detailed analysis we have sent it to publication in Applied Surface Science and it is under review. So the results I am presenting here. Basically, gallium antimonide is one of the important semiconductors in 6.1 angstrom family of semiconductors, which we can see here. Then as I told that I used silicon because already I have done some work on sulfur and silicon for implantation. So silicon was proved to be better as a dopant, N-type dopant. So silicon I used with different fluences. So here I am showing two fluences. So one into 10 power 12 ions per centimeter square, and there is higher fluence 1 into 10 power 15 ions per centimeter square. And the other, the film which basically I used for implantation was grown in molecular beam epitaxy system on gallium arsenide substrate. So we looked at atomic force microscopy images and optical images. It was perfectly smooth film. The roughness was 0.82 angstrom, 0.82 nanometer, and then after implantation for lower fluences, the roughness changed very little. It was almost 0.9 nanometer, which we can see here in image, and it rose to 2.6 nanometer for 1 into 10 power 15 ions per centimeter square. Raman spectroscopy and HRXRD, high resolution X-ray diffraction, omega scan images are shown for pristine film, and these are very low FWHMs in both the films, both the characterizations, which shows that film is epitaxial. Hall measurement, which we can see, it's the and mobility is 880 centimeter square volt into second, and this seed carrier concentration. So after this one implantation, the resistivity at lower fluences are not much changed, but at high fluences, it is changing to higher doping concentration. I looked at XPS characteristics of we did XPS, and we found that actually I have forgot to mention here. The lowest one image is for pristine, and the topmost is for highest fluence. So what we found that antimony oxide peak is reducing at large amount, which basically has been reported that antimony oxide compared to gallium oxide is more detrimental in electrical characteristics. So we found that with higher silicon fluences, we are getting high doping carrier concentration as well as low antimony oxide peaks. So
Hello.
Something went wrong. Rakesh, are you there? Your link broke, I think.
Yeah, the link.
I think his voice is not coming. His internet is not working.
cleaning the surface also.
Yeah, he's back. Okay. Oops. Rakesh, your presentation disappeared. Can you hear me?
Yeah, okay. Actually, I could not see the main screen, so I stopped sharing it. I will again do that. Yeah.
Yes, again, we are back.
Yeah.
So
Conclude
you can
quickly,
probably,
please.
yeah. Can you please conclude now?
Yeah,
You can tell us the highlights and then.
yeah. So basically, silicon implantation in gallium antimonide had with two different fluences which I have shown here. That at higher fluences, when we are increasing fluence, we found that higher concentration in gallium antimonide is increasing. What we basically are expecting that if we are increasing the fluence, carrier concentration is increasing, so that way we can control the doping concentration. At the same time, we found that antimony oxide is basically reducing, and people have used so many other techniques like hydrogen plasma and all techniques to clean the surface, and they have achieved lower antimony oxide and the gallium antimonide. And we found that the silicon implantation is also helping out in reducing the antimony oxide at the surface. So that is basically useful for electrical application of the gallium antimonide, doped gallium antimonide films. So that is we achieved in this work.
Okay, thank you.
Yes.
Thank you, Mr. Rakesh. So we can probably take a quick question from the participants if there is any. Okay, so but you are most welcome to write to the speaker, Mr. Rakesh. His email ID is given in the poster. Okay, if there is anything further clarification or some more information is needed. Okay, thank you, Mr. Rakesh. So
Thank you.
now we move to the next presenter. So the next poster is by Mr. Subhajit Karmakar. Poster number is 235. And the title of the poster is Polarization in Sensitive Phanoresonant Symmetric Terahertz Meta Cavity. Yes, Mr. Subhajit, you can
Yes,
now
sir.
share the poster, please.
Yes, sir. Okay. Sir, is it visible?
Yes, we can see
Hello.
it. Yes.
Okay, so good afternoon, everyone. Myself Shubhajit, and the topic of my presentation is polarization insensitive phanoresonant symmetric terahertz metacavity. So, as you know, that metamaterials are artificially engineered suborbital structure which has attracted tremendous interest due to its enormous ability to realize some unusual properties which are not viable in nature. Now, one of the interesting phenomena which has been exploited in metamaterials is phanoresonances. So, phanoresonance is basically characterized by the asymmetric line-shape resonance, which is generated due to destructive interference between subaradiant and subradiant modes. Now, to excite phanoresonance, we always need structural asymmetry along applied polarization. And also, phanoresonance is very sensitive towards the applied polarization. So, in order to achieve these limitations in our work, we have demonstrated a novel scheme where we have excited phanoresonance without having structural asymmetry, and also which is also polarization insensitive. Excuse me. So our proposed device will look like this. So this is a vertically stacked plus shape resonating structure. So it has been fabricated by two-step process. So first we will deposit the lower resonator array. On the top of it, we will then basically spin coated the polyamide layer, and on the polyamide layer we will basically mask align and then deposit the upper resonator layer. So as we can see that when terahertz we do the terahertz characterization, we have shown the two resonance tips in the transmission spectra. The left one at zero point 0.5 to terahertz is broad and symmetric, and the right one at 0.8 to terahertz is narrow and asymmetric, and it is called as a phanodip. So to characterize the resonances, we have investigated the surface current distribution. So in around 0.5 to terahertz, there is a symmetric current distribution between the resonators, which shows the constructive interference and signifies dipole resonance tip. And the right one around 0.8 to terahertz shows the anti-symmetric current distribution, which is basically the signature of the phanoresonance tip. Now, we have also shown that at the phanoresonance tip there is a very high energy confinement inside the polyamide spatial or cavity region. So we have used this high energy confinement ability for sensing technique, and our sensing and shows a very superior sensitivity of 1.1 terahertz per refractive index unit, which is possibly the highest terahertz sensitivity reported so far. Now we have also exploited our concept towards the chemical sensing, and one important point in the sensing technique is that our sensitivity shows a negative slope with the thickness and refractive index of the cavity. That means that how the lower or the lesser material you put in the sensor, the more sensitivity you can achieve. Furthermore, we have also demonstrated the effect of polymorphic hybridization with the metasurface cavity. So basically, what we have did that we have changed the refractive index of the material of the cavity, and as we can see that for refractive index of 2.1, we observed the hybridized modes where the left hybridized mode is basically behaves as a dipole mode and right one is the Fano mode. But when we just tune the refractive index to 2.5, the both hybridized mode behaves as a dipole mode. But again, when we further increase the refractive index, we show a dramatic change of the nature of the hybridized mode, and the dipole resonance behaves as a Fano mode, and Fano mode behaves as a dipole resonance. So this is, and moreover, this scheme is polarization insensitive. That means that you can change the polarization. There is no effect so far. So in conclusion, we have realized Fano resonance in symmetric terahertz metastructure, and this doesn't depend on the applied polarization. Also, in the cavity region, we have confined very high electromagnetic energy, by which we have shown a very high sensitivity of 1.1 terahertz per refractive index unit. And moreover, we have shown a polymorphic hybridization where we can basically tune the nature of the device to behave as a radiative device or non-radiative device, either electric device or magnetic device, and vice versa. So this is the reference and this is the publications, recent publication. And I would like to thank my supervisor, Professor R.K. Bhashne of IIT Delhi and Professor Dibakar Rai Chaudhary from Mahindra University for my supervision. Thank you very much.
Thank you, Mr. Subhajit. So probably one quick question from the audience, if there is any. But you are most welcome to contact the speaker.
Shubhajit, just one clarification, Shubhajit.
Yes,
Can
sir.
you hear me? These
Yes, sir.
results
Yes,
that
sir.
you showed, are these simulated or measured?
Sir, this one which I showed, this one is simulated, but the paper which I have shown here in the references, these are all means experimental characterized.
It's okay, but whatever results you are showing here, these are simulated results, right?
These are simulated results, yes, sir. I have not shown the experimental results here.
Okay. Thank you.
Okay, sir.
Thank you, Mr. Subhajit. So I think now time is up. So we should now move to the next poster. Yeah, thank you, Mr. Subhajit. Yeah. So now we move to the next poster. It is poster number 236 by Mr. Sandeep Sarma, K. Sandeep Sarma, and the title of the poster is Sandeep Sarma here?
Yes, sir.
Yes, okay. Yeah, so the title of the poster is High Coupling Coefficient and High Q Switchable High Overtone Bulk Acoustic Resonator based on Helium Strontium Titanate Films. Yes, Mr. Sandeep, go ahead.
Good afternoon, everyone. Today, I would like to present my work on high overtone bulk acoustic wave resonator, which is based on BST thin films, so making it switchable and making some parameters of the H bar tunable as well. So in this, this work was carried out in University of Hyderabad under Center for Advanced Studies in Electronic Science and Technology. And I would like the organizers of the conference to giving me a chance for presenting my work here. So I'll discuss about regarding the high overtone bulk acoustic wave resonator, which gives an excellent, exceptional, good quality properties, as in giving high coupling coefficient, which is as high as 7.4%. And achievable Q factor of the resonators are more than 20,000, up around the 2.5 gigahertz range. So H bar is basically a bulk acoustic wave resonator. As a bulk acoustic wave resonators, like popular ones are SMR and F bar, but in the case of H bar, instead of reflecting or confining the energy inside the bulk of the inside the transducer material, H-bar uses or utilizes the substrate, which is usually a low acoustic loss substrate like sapphire, YAG, and like recently diamond has been used for getting very high Q. So ideally, in such kind of a configuration of device, the achievable Q is it can ideally be the Q factor of the mechanical Q of the substrate being used. So the advantages being high Q and ease for fabrication because of like it can be a single mass process or can be a simple structure. But the disadvantage, especially in application in communication, is the presence of numerous resonance mode. So as we can see in figure figure C in the spectra, figure 2 in the spectra of H-bar, we can see an envelope kind of a response, and we can see inside that it is actually made up of multiple resonance peaks, which are because of the standing waves created inside the substrate. So the basic fabrication technique would be to sputter a bottom electrode on a substrate, then use PLD deposition. So the PLD deposition and the development of material was carried out by one of my co-author, who is von Drickum, and work on BST. His work mostly confines on improving the quality of BST and reducing the deposition of deposition temperature of BST to bring it down to as low as room temperature. So, but for this one, we have used a normal 700 degrees Celsius deposition technique. So for probing, we use a CPW probe, and we use a very simple single mass process where we use a circular path capacitor. And when we simulate the H-bar structure, we can see thickness extensional mode, and the simulation in figure A of 2 is using COMSOL simulation. So coming to the result part, so in normal conventional H-bar or F-bar, which uses zinc oxide or other piezoelectric material, it cannot be switched on and off because of the use of piezoelectricity. But in case of using paraelectric thin films like BST, we have the capability of like switching it on or off depending on the applied voltage. So if we apply a voltage, then it starts resonating. So the another interesting part is the bias dependence of BST-based H-bar. So certain parameters such as the coupling coefficient of the H-bar is heavily dependent on the voltage being applied or the field being applied. This is basically due to the dependence of the dielectric permittivity relation between the dielectric permittivity and the coupling coefficient of the material. So we can see that there is an increase in the coupling coefficient when we increase the voltage being biased to across the device as well. So we have achieved almost 7.4% of coupling coefficient of the BST material when under bias. Then there is the dependence of Q factor on the coupling coefficient on the DC bias as well. So one interesting aspect of the importance of being able to increase or decrease the Q factor of a resonator is in recent development in fields like quantum acoustodynamics and so on, where they use diamond or other very high Q material. So if we have the capability to increase the Q factor further to make it closer to the mechanical material Q as much as possible, even by application of a voltage, would give a very big advantage.
Okay, thank you, Mr. Sandeep. So
yes.
The time has got over now.
Okay.
I think we can take a quick question.
Okay.
So probably I would like to question, ask this question. In your title, you have selected a particular, very specific doping concentration. If you go to the material that you are using,
yes, sir.
Can you go to the title? So what was the reason, like, that you have this 50-50 of barium and strontium in this?
The combination for choosing barium 50-50 was the temperature where the phase transition happens. So 50-50, it happens somewhere around room temperature, like 30 degrees Celsius. So it can easily be, it will be in the para phase, which we want for utilization in as a resonator instead of using in the ferro state, which will be in the memory devices.
Okay. Thank you. Thank you, Mr. Sandeep. Thank you for presenting.
Yes.
Yeah, so you can now unshare it.
Okay. Thank you.
Yeah, so now the next presenter is Mr. Sarath, poster number 237. And the title of the poster is An Accurate Inductor Model by Incorporating Negative Mutual Inductance Effect for High Density SOC. So Sarath, you have 5 minutes, please. So who is presenting? Suraj, you are presenting or Sarath is presenting? Hello?
But basically, this was the case. Sarath has told me to, like, Suraj will present this presentation.
Okay.
So Suraj is present here. Yes, sir.
Okay. Yeah. Please go ahead, Suraj. Sarath.
Yes, good afternoon, everybody. And the topic of my poster today is an accurate inductor model for incorporating negative mutual inductance effect for high density system on chip. So basically, in today's modern day electronic circuits, the component density has been constantly increasing and therefore limiting the flexibility of designing a guard ring around the inductor component. So due to which there have been a lot of limitations in the theoretical modeling of inductors for today's high density circuits. So basically the objective for our research was to provide an accurate theoretical model for on-chips planar inductors and also study the effect of the negative mutual inductance caused by the guard ring at distances as small as 5 micron. The prior literature has done some study of negative mutual inductance only up till 20 microns. So we've been trying to further analyze this effect at much more smaller distances as circuits and components are getting much smaller these days, and it's really necessary for us to analyze the importance of the negative mutual inductance in order to get an accurate and a well efficient performing inductor. Because if we fail to do so, this might lead to inaccuracies. So the major objective for us is to basically try to formulate a theoretical model as well as study the dependence of the negative mutual inductance on inductance as well as distance. So basically, there have been two different research groups that have focused on this. And one of them is Grover, who has laid the foundations for inductance calculations, and they are only accurate about distances of anything more than 200 micron. The second group is the Shiramizu, who were the first ones to kind of report this negative mutual inductance, but their model is only satisfactory after 70 micron, and anything below 70 micron, they return a huge error. So our major intention was to correct this error and provide an accurate model. So how we have kind of structured our experiments is we have simulated our inductor model on simulation software called high frequency structure simulation, which is HFSS. So here I have also given the specifications of our test inductor as well as the guard ring, what we have designed around it. The reason why we chose for simulations is because we only wanted to study this single parameter into, we just wanted to take this single parameter into account, and we wanted to neglect all the other effects such as the oxide layer effects as well as the substrates effects. So due to this, the reason why we chose a simulation method to understand this was only because we wanted to study the effect of negative mutual inductance caused by the guard ring. So how we have kind of tried to approach this negative mutual inductance effect is basically by providing a modification to the existing Grover as we can see in this formula, we have provided a negative mutual inductance coefficient as a modification. The modification basically takes into account for the negative mutual inductance caused by the card ring at distances as small as 5 micron, and this extends up to 100 micron. And this equation has also been adapted from one of the books from 1988, but the equation has also been modified by us based on today's high density circuit requirements. And the rest of the inductance calculations have been done as per the Grover's inductance calculation as well. So in the results, we can see that the black curve is the curve which uses the negative mutual inductance coefficient, and the red curve is without the negative mutual inductance coefficient. So at 5 micron, we can see about 75% variation in the self-inductance of the inductor. And at 50 micron, we can see about 61% of variation in the negative mutual inductance. So this is kind of evident that the negative mutual inductance effect is undeniable at distances as small as 5 micron, and this can deviate up to 75%. And there is also another plot which provides a comparison between the existing literature by calculating the total inductance using their formulations. And the red curve is the formulation which is used by using the negative mutual inductance coefficient. And this is the proposed model. So we can see that in the error bar that the proposed method up to 100 micron provides a satisfactory error rate of less than 5% up to 70 micron. And above 70 micron, there's a constant error of 7% for the proposed model. And the Grover's model at 5 micron provides about 47% of error rate. So this can also be seen in the above graph, where the black line is the Grover's model, and this kind of predicts a constant inductance throughout any range of distances, proving that it does not take into account of the negative mutual inductance at smaller distances at all. And the Shiramizu's model, although it predicts, what it does is basically it underestimates these values at smaller distances, and this can also be observed at distances up to 50 micron, that the error rate is almost up to 10%. So as the distance increases, their model provides a better accuracy, and above 70 micron, their model is providing 5% error rate, where our model provides about 7% error rate. So there is still scope of improvement in our proposed model.
Yeah, I will have to interrupt Mr. Suraj.
Yes.
You have already taken 6 minutes, more than 6 minutes. So probably quickly, in 1 or 2 sentences, can you conclude?
Yes, sure, absolutely. So basically, the future work can include about by improving the accuracy at higher distances. But nonetheless, for smaller distances, the proposed method can be used for accurate inductance calculations. Also, I would like to thank my supervisor, Professor Ranajit Sai from the Science Department, IISc, as well as my peers, Sarath Arakal also. Thank you.
Thank you, Mr. Suraj. Thank you. Yeah, so if there are any doubts and other clarifications, the participants can contact you on this email. Okay, so thank you. So I think now we move to the next poster. So the next poster is by Dr. Suprabodh Ghosh, poster number 238, and the title of the poster is On-Chip High-Speed Integrated Slot Waveguide Based Electrically Tunable Graphene Terahertz Modulator.
Sir, poster number 238 is not there, sir. We have to go.
That is what you wanted. Okay, fine. So we move to 239. Ramesh Raja is there?
Yes, sir.
Yes, sir. I'm there, sir. I'm present, sir.
Okay, good. So Ramesh Raja is going to present on linearity behavior of a pocket doped type ground plane FDSOI impact of back biasing. Poster number 239. Yeah, please go ahead. Share your poster, please.
So can you see my screen, sir?
Not yet.
Sorry, 1 second.
Probably, yeah. Is there any what is the technical problem from your side?
Ramesh, are you
Sir,
using
not.
a mobile phone?
I'm using tablet, sir. So can
Okay,
you?
yeah, it's coming. Fine.
Yeah,
Okay,
Good,
something is
it's
coming.
working now.
sir. Thank you, sir. So good
Okay, go
evening,
ahead,
everyone.
please.
So shall I start, sir?
Please.
So good evening, everyone. This is Ramesh. So I'm going to discuss about linearity behavior of a pocket doped P-type ground plane FDSY. So under the influence of back biasing. So basically, what we have done in this work is we have taken FDSY MOSFET with a channel length of 22 nanometers, and we have added two pockets on the source side and the drain side. This can effectively reduce peak electric field at the junctions, and then it improves the mobility, which can also help in reducing the impact ionization, and which can drastically improve the self-heating effects. Which can drastically reduce the self-heating effects of the FDSY MOSFET, which is a drawback for FDSY MOSFET. So the GP is added. GP is the ground plane. Ground plane is it reduces the depletion region formation under the box, which is also a case where if the depletion region is formed under the box, then the mobility is seriously affected in the channel. So the GP is added for the device. This is the architecture that we have chosen. So the pockets are placed on the either sides of the channel. As you can see, the channel is incorporated with two pockets, source side and drain side. So what we have done is we have investigated for linearity figure of merits using integral function method. So the integral function method is a method of calculating the linearity by taking output characteristics and from the Taylor series output equation of transistor, which is mentioned here, where drain current is equal to gm1 VGS of t plus gm2 VGS square of t plus gm3 VGS cube of t, and so on. So where gm1 is a fundamental or transconductance parameter, where gm2 is a second order transconductance coefficient, and gm3 is a third order transconductance coefficient. So we have calibrated device. We have calibrated the device. Sorry, all the investigations are carried out using simulation approach through Silvaco Atlas TCAD. The physical model selected are shown here. So this is the calibration that we have done. Which is the acceptance is very high with the experiment. This is the transfer characteristics of the device, proposed device. So we can clearly understand that when we are varying the back bias from where minus VB is minus 1 volt, positive plus VB is 1 volt. So with a step of 0.5 volts, we have increased the step size of back biasing. So we can clearly see the shift in subthreshold slope and threshold voltage, which is a practice obtained from the literature that the implementation of back biasing without causing any structural changes to the device, we can modulate the performance by using back bias. So here we have investigated linearity figure of merits. So linearity figure of merits are performed in the device level. At the device level, if we perform a linearity figure of merits investigation, we can drastically reduce the cost for the need of complex circuitry needed for increasing the reliability of the device. So here the figure of merits are we have investigated are HD2, which translates to second order harmonic distortion. HD3 is third order harmonic distortion. IM3 is the intermodulation distortion of third order. VIP2, VIP3, IIP3 are voltage and input intercept points with second, third orders. So we have taken the fundamental that is transconductance coefficient GM and plotted against the gate voltage. Generally we get transconductance by differentiating drain current with VGS. So we have for similar to transconductance coefficients or the fundamental, we get GM3 or GM2 by partial differentiating it with again with VGS. So if it is GM2, it is partial differentiate 2 times with VGS. So if it is GM3, it is 3 times VGS. So it is there in literature. If you have any queries, you can go into literature and search. No problem. So
Yes, yeah.
GM3.
Thank you, Mr. Ramesh. I will have to stop because time you have taken your time. So probably we can ask a quick question. Professor Anjan, you would like to ask a quick question?
Yes, sir.
No, it's fine. That's fine.
Yeah. Okay. Thank you, Mr. Ramesh.
Yes, sir.
So thank you for presenting. Okay.
Okay, sir.
So we have now the next presenter, Mr. Ankit Kumar Pandey, poster number 240. The title of the poster is Substrate Integrated Waveguide Step Type Cavity Backed Slot Antenna for Dual Frequency Applications. So Mr. Ankit, are you there? Yeah.
Yes, sir.
Yes. So your text seems to be very small, so you will have to zoom in, on those areas which you are presenting.
Okay, this is my structure. Actually, I made a SIW cavity first to make this back antenna, and I use a step type I make the step type cavity for making a cavity first. So what I did now, I make a step type cavity, and as we know from the transmission line, if we provide matching multiple times, so that must be increase the bandwidth, and that was the idea behind that, to just make the cavity like that. And then there are very conventional technique which I use to get a multiple frequencies. The first is everybody can see now, that is the conventional rectangular slot here, and as we know, it's the frequency of that slot is the wavelength is almost equal to half of the length of this slot. And I also use this ring slot for another frequency which is there now. And actually, what I did now, first I did made this rectangular ring slot for this, and then when I made this conventional rectangular slot in that SIW cavity, then I got this complete bandwidth and this multi-band, and the enhancement of the bandwidth, as I mentioned, why that happened actually. Now, what is SIW and why I use SIW for making all the things? Because conventionally, when you use the patch, my idea is to inherit some property from waveguide, and at the same time, it inherits the properties of patch antenna also, and both it's a mixture of both patch and waveguide. So this all. These are the I would say holes which connected from the this layer to the upper layer, and this is known as cavity back. Why this is back? Because this is the back side of the antenna. This is the feeding line. Normally, what we did in the antenna, we use we use for improving a gain or whatever, because what we get from the slot antenna in the patch, we got a backside radiation, and for removing that, what we use mostly use a metallic reflector from λ/4 behind that. But this is the benefit of this cavity back. If you just cut the slot in the backside, which is very famous in SIW, to making but what new I did now is just making this step type to inherit the waveguide. And the next procedure is very conventional to the people. This is the mode for the only this I add that frequency, and for that frequency I get the fields like that. And as we can see, this is what this is a magnetic field. So we have seen 2 cycles in that side for that particular frequency. So this is TE20. There is no TM mode because as you can see now, there is a discontinuity in that side. So there will be no TM modes in that case because there is a discontinuity. So if there is TM mode, we cannot get TM mode because this line is discontinuous. This line is discontinuous. And then there's a very these are my major antenna, and I didn't use the plating through hole technique to just shorted these wires. These are known as a wires, so I didn't use that. And but eventually I did manage to do this. And this is my S11. I getting 2 frequencies, 6 and 11. There is a big high 11.98% fractional bandwidth, which you mostly when you use this conventional slot SIW, then you didn't get that bandwidth like that, which I get here now. And I just make another thing that I use this table now for comparing my proposed antenna with the others. So
okay,
what about the gain, bandwidth, and FDR? I just put that comparison that yes, it is much better than some other antennas, very conventional in SIW. So that is all about for this first paper that I put here.
okay, okay.
And
Thank
I
you,
use
Mr. Ankit.
grounded coplanar waveguide technique to just feed that waveguide.
Okay, okay. Thank you, Mr. Ankit. So probably, Professor Anjan, you have a question to ask?
Yes, Ankit, just one small question.
Yes,
what do you mean by front to back ratio in this antenna? Which is the front and which is the back?
Front to back ratio.
No, which side are you calling front and which is back? Front is pointing vertically upward?
Vertically downward. Front is vertically downward in this.
Downwards, and back is. And you are getting very large front to back ratio, correct?
Yes.
Even though this is a slot antenna, this is measured?
This is measured.
Okay, thank you.
Okay. Thank you, Mr. Ankit, for presenting. So
Sir,
now
I would
we
like to
move
mention that the next is a presentation for Alok Kumar Saxena, and this is also my paper from that.
Okay.
He is my co-author, and he'll not available right now. So I'm now going to present the second one. This is, I think, 242.
Yeah,
So
poster number 242 by
exactly.
Alok Kumar Saxena, and you are saying he is not present, so you will present on
He
his
is my
behalf.
co-author. Okay.
Okay, fine. Please share that poster.
So this is a 2-element cavity back hexagonal patch antenna array. So there is very multiple things now. So what I did here new in this section, we have seen patch antenna most of the time in our applications, in antenna application. What I did now, I just realized that patch with this square cavity, SIW square cavity, and what I get now from just providing this square cavity for this hexagonal patch is very so many papers are there for hexagonal patch and microstrip patch antenna. But what I did, I just use this SIW square cavity, and what does it make? You can see here in this S11 characteristic what happened after. This is a simple patch antenna, hexagonal patch, and you get S11 like that. And when I realize that patch with this cavity, I'm making just a cavity with the I use this patch inside that cavity, so I get my S11 like that. Why I get my S11 like that? This square cavity reduces the surface wave actually. As we know, we have a problem with mostly when you use the patch antenna. Just excite that patch coaxial probe I used to excite that patch. When you excite that patch normally, So what you get, you find that surface wave that causes the it causes the loss now. So it's using that square cavity that actually what it does, just confine the waves, and it reduces the surface wave effect in patch. So this is the this is the advantage of SIW cavity when you use to realize the patch, normal patch. So that's why I get this bandwidth, and the gain is like that. So what this is a very simple SIW patch antenna. It's nothing so much, not too much new in this section. But what I need to, what I try to realize with this, I just try to make this antenna array for latter application. And actually, this is their radiation pattern of this single element antenna. This is gain, and this is the radiation pattern. All these are the radiation pattern. So what I did now, I just realized for this reduction of surface wave, and then I get this. But this is not a big thing in this antenna. But the big thing that I try to do is try to make an array. And what we get the advantage of this SIW, I can show here. I use this basic power divider, T section power divider, and for this particular bandwidth range. And as we know how we just try to maintain S21 is equal to S31 to get this half power in that port and that port, because I just make two elements, so I need to feed same power, and my target was to just increase the directivity to so I use the two element. First, this paper is going. I'm working on this paper still now, but currently I just made two. So what we get advantage of this? This is the main point of this. You know, when we use SIW antenna array, patch antenna array. So you can see here. You can see here there is no mutual coupling. There is no mutual coupling, though the distance between these two is 23 mm, 0 point something 7 or something lambda. But you know the mutual coupling isolation is very good. So this is the reason behind that I am using the array, and I just try to try to increase the number of elements for their applications. But the array I used, and the bottom of this array, I use this T-type power divider and just give the microstrip feed to this. Though before that, I used the coaxial probe to excite that, but right now I'm doing that. And I use this bottom conductor. This is the up part of the conductor, two element, and these things are for my feeding process, and I get this S11 almost similar to the previous one. My radiation pattern is like that, but what I get now, I can say here.
Yeah, so you may now please conclude.
Half power beamwidth is 67 degree, which is 13 degree lesser than the single element. So as we know, half power bandwidth is lesser, then definitely the directivity is much. I'm not plotting directivity. I'm just using the gain now. When we compare gain, then almost obviously gain is much higher. But I'm just using this half power beamwidth to compare both. So my beam is slightly, I would say, narrow. So this is getting a good.
Okay, I think you can conclude here.
Yeah,
we're really running out of time. Thank you.
Yes.
Yeah. Thank you, Mr. Ankit. Yeah, so the questions can be addressed directly to him through email, probably, because the time is already over.
Okay, sir.
Thank you, Mr. Ankit, for participating and presenting your paper through poster presentation in this conference. Thank you very much.
Thank you, sir.
Yeah, so now we move to the next poster, which is poster number 243. by Ms. Shweta Agrawal, and the title of the poster is Spice-Based Compact Modeling of a Spiral Inductor and MIM Capacitor for RF Circuit Simulations. So, Ms. Shweta, you are there? Yes, very good. Please, yeah, get started. Yes.
Good evening, everyone. So I'll walk you through my paper, which is spice-based compact modeling of a spiral inductor and a MIM capacitor. So here we had the results. We had already the measurement results of a spiral inductor and MIM capacitor, which were fabricated in SCL 180 nanometer technology. So. We did the de-embedding of the extracted of the measured S parameter results, and after that, using those S parameter results, we tried to make a model, SPICE model, for the inductor and for the MIM capacitor. So I'll just walk you through the model which we used for the spiral inductor. So as you can see on the left side, the spiral inductor, the circuit diagram. So here we have, we use the pi model. Hello.
Just go ahead, please go ahead.
Yeah.
Ankit Kumar Pandey, can you kindly switch off your microphone because I think noise is coming from there. Yeah.
Okay, thank you. So we use the pi model for spiral inductor. So here, this L main is the main inductance value, and R is basically it accounts for the losses in the inductor. So and the other parameters are basically accounts for other parasitic losses. So, and the substrate losses are taken by this L sub and the R sub, and these are CR10 and all these all these capacitance and resistances. So what we first from the S parameters, the de-embedded S parameters, we sorry. So from the de-embedded S parameters, we extracted a pi model, so converted the S to Y parameters, and then after that we tried to calculate roughly to get the values of these L and C. So from the Y parameters, we equated the imaginary part directly to the L main. For the C part, let's say I got the extracted C. From that, I got the L, and from the real part, I got the R main and some R main, which also contained the ROX component of ROX. So the further tuning was done using Icee cap simulator, which is the agent simulator. So then we had the tuning was so while tuning, we were plotting both the measured data as well as the simulated data. So the S parameter, this is basically the this is basically the Smith chart. The A, B, C, D. These are S11, S12, S21, and S22 parameters. And the measured and the simulated results were matching well. So then there itself, we fixed those values of L, R, and C's, all those things. And the E plot, which you can see here, this is basically the L plot, the inductance plot. So the inductance is plotted for the inductance plot. It is the measured as well as the simulated plot. So the blue one is the simulated and red is the measured plot. So for the range of 2 gigahertz to 6 gigahertz, they were in good agreement with each other within the range of 2.5%. Then we had the F plot is basically this is basically the Q factor, which again shows that the simulated and the measured, they are in good agreement. The similar approach was done for the MEM capacitor. So we use the T model for MEM capacitor, where this C main is the main capacitance value, and this resistance R accounts for the losses, and this C substrate, these account for the substrate losses. For the MEM capacitor, we had the measured data and the de-embedded measured data. So from the S parameters, we got the Z parameters, and then we equated the real and the imaginary components to roughly get the values of these C's and R's. And further, we use the Icee cap tool to tune these values. So again, on the right hand side, you can see the S parameter plot for S11, S12, S21, S22. All those 4 parameters are plotted here, and the measured and the simulated results, they match.
Yeah, please conclude now.
Okay. So finally, the modeled spiral and the MEM capacitor, they can be used for RF applications, which are in the range of 2 to 6 gigahertz, because I mean it is the percentage it is within 2.5% of the measurement results. So they can be used for oscillator design or LNA design. Thank you.
Okay, great. Thank you. Thank you. Professor Anandan, is there any question?
Yeah, just Shweta, one quick question. Don't you
Yes,
think in the inductor especially the number of unknowns are too many? Just with a few S parameter measurements, how can you fit in like 15, 16 unknowns?
So we are showing not all the all the plots. We are actually not. We have not shown you the other plots which we have done. So we did this tuning for independent tuning for this auxiliary inductances and the capacitances. All these were independently tuned as well.
Okay.
So we haven't shown all the plots, all the plots, only the major plots.
Okay, thank you.
Okay, thank you, Miss Shweta. So you can now unshare the screen. So we move to the next poster now. Yes, it is by Miss Mamta, poster number P244. And the title is Surface Morphology of Step Edge on MgO Single Crystal Substrate for Josephson Junction. Yes, Mamta, go ahead.
Yes, sir. Is it visible, sir?
Not yet.
Oh, just a second. मैम ये शेयर नहीं हो रहा, एक मिनट देखना, शेयर नहीं हो रहा, आई डोंट, पता नहीं, कनेक्ट अभी कनेक्ट हो रहा है ना, कनेक्टिंग
Professor Anandan, shall we move to the next one? By the time this they can get ready.
आवाज तो जा रही है.
Mamta, can you hear me?
Yes, sir. Yes, sir.
We will just move on to the next poster, and in the meantime, you can get your thing ready. Okay?
Okay, sir. Okay, sir.
Okay. So next, please.
Okay. Yeah. So the next one is by Miss Rekha, poster number 245. Title is a sub-terahertz spin Hall nano oscillator using synthetic antiferromagnet. Rekha, you can go ahead.
Hello.
Yeah, please. We are able to see.
Okay.
Yeah, please go ahead.
Hello.
Here I will talk about a sub-terahertz spin-hole nano oscillators using synthetic antiferromagnetic material. Basically, first I will talk about synthetic antiferromagnet. When two ferromagnetic materials coupled antiferromagnetically, this is called synthetic antiferromagnet. They are using instead of antiferromagnet material because their magnetization is easily manipulated compared to antiferromagnet. And it's a well-known fact when antiferromagnetic material based spin-hole nano oscillators used, they can generate auto oscillations in the terahertz region. That's why I'm using synthetic antiferromagnetic materials. Here I'm using micromagnetic study to simulate this synthetic antiferromagnetic based spin-hole nano oscillators. Basically, here I use Mumex 3 software to do all these simulations. In the second part, I have shown the device structure. Here I use permalloy as an ferromagnetic layers, two permalloy layers coupled antiferromagnetically, and platinum is used as heavy metal to inject spin current in this synthetic antiferromagnetic materials. Now we can proceed into the result and discussion part. In the first part of result and discussion, here I have shown the auto oscillations with different current. Like in this part I have shown 35 milliampere and in this part with 50 milliampere. And we can see in this both parts sustained auto oscillations in the terahertz region. And also when we increase the current, there is the increase in terahertz frequency as well. In the next part we will see the systematic study, the auto oscillations with current density, and we can see as we increase the current, the auto oscillations also increases in the red and black both curve respectively. We also see the thickness dependent study. In this black part, we have using the bottom layer synthetic antiferromagnetic layer is 2 nanometer, and in this red curve, this bottom layer thickness is 4 nanometer, and as we decrease this bottom layer thickness, the auto oscillation frequency also increases. Here we can achieve auto oscillations up to 0.5 terahertz with a tunability of 21.1 gigahertz per milliampere. Here we also shown current dependence of line width as well as amplitude of auto oscillations in the red and black curve respectively, and in this black and green curve respectively. And we can see at a particular current 35 milliampere, we can see narrowest line width 5.45 and highest amplitude. So now I conclude this. We demonstrated auto oscillations up to 0.5 terahertz in synthetic antiferromagnet based SHNO using permalloy materials. We also discussed their current dependence. We also discussed the thickness dependence auto oscillations, and we also show that the synthetic antiferromagnetic spin-hole nano oscillators generate frequency in terahertz region without applying any external field. We acknowledge IIT Delhi supercomputing facility and our professor. Thank you very much.
What happened? Your poster just vanished. But I have a quick question to ask.
Yes, sir.
So, you can tune the frequency of the radiation that comes out by changing the current value. But can you somehow control the magnitude of the radiation that comes out by doing something? How do you change the magnitude?
Yes, sir. This magnitude also depend on the current density, as we can see, as you see already. The amplitude of the auto oscillations also depend on this current density. In a pattern.
That will change the frequency of oscillation also, right? When you
Yes,
change
sir.
the current.
Yes, sir. Yes, sir. There are other things that we can do to control this, like magnitude, like this changing this thickness of the materials with the same, or changing the material parameter will also change this.
Okay. Thank you, Rekha, for presenting and participating. So now we move to the next poster. It is by Mr. Vikas Kumar, poster number 246, and this happens to be the. Okay, so we have to go back to Mamta also. That will come back at the end. But now Vikas can present poster number 246. Title is Terahertz Polarization Splitters based on dual core photonic crystal fiber? Vikas.
Sir, I am just sharing my screen. Sir, it is visible now?
Not yet.
Okay, it is coming.
Yeah, we can see now.
Okay, sir, fine. There is some technical glitch. I think it should be clear, but anyway. So here we have, I am presenting my recent research work basically based on terahertz polarization splitters based on dual core photonic crystal fiber. Basically, terahertz radiations is now an emerging field, and we have different applications like imaging, spectroscopy, and communication. So in these applications, researchers are now they are needing basically the property of polarization to be controlled basically. So polarization is a property in which electric field is oriented basically in different directions or orientations basically. So it can be in x direction, it can be in y direction, it can also be circular polarization, but we are not dealing with it. We are dealing with x and y polarization here, and basically one can need basically the separation of two polarization in the input. So people are designing different types of configurations, and they have designed the crystal structures also there to have the polarization separation. But nowadays photonic crystals is now an emerging field where we can have different types of flexibility basically in the beam characteristics as well, and attaining model area and different dispersion characteristics can also be tuned with the help of these types of photonic crystals. So in this paper I am going to describe about my design, basically the photonic crystal fiber one. And there are two types of fibers present basically. There is index guiding fiber and there is also photonic band gap fiber. But photonic band gap fiber is only applicable to a particular bandwidth only. But the solid core index guiding fiber, photonic crystal fiber, is used for large varieties of applications. So the basic need for them is basically the large bandwidth they can guide. So therefore we design with the help of index guiding photonic crystal fibers. So people basically prefer the dual core configuration for polarization splitting. There will be two cores A and B here, but in the previous paper by Icee, basically they have designed the rectangular structure for the dual cores, and the rectangular structures were like that. There were different types of pitches, XY pitches in both cores, but we have changed the arrangement of the air holes, and we have also added some Teflon rods in the dual core designs. And due to this, what happens, basically what we want to achieve the polarization splitting, we want to basically we have two polarization at the input end. So the separation between two polarization should be done with the help of one particular thing, like degeneration should be maintained for particular polarization, and other polarization should be completely non-degenerate, means the refractive index effective indices between the two polarization should be very close to each other for a particular polarization, and for the other polarization the refractive effective indices should be different, very different from each other. So this type of configuration, basically this type of configuration is gradient arrangement of the air holes, such that it provides the effective indices, where we have also calculated the effective indices here. But before that, I am going to tell that full vector beam propagation method I have used, and finite element method was also used to verify the results of full vector beam propagation as well. This basically depends on the creating difference equation, and by from Helmholtz equation, and from there we find transcendental system of equations, and solving these transcendental system of equations provides us model configurations. So here are the model profiles of the dual core configuration for the combined fiber, and these are shown for 0.6 terahertz, 0.7 terahertz, and 0.8 terahertz. So these are I'm going to tell about them also, but first we see the ineffective curves. Basically these are for individual curves and these are for combined curves. For individual curves, you can see that the difference between the effective indices of x polarization modes is very far, very large, and for Y polarization it is very close to each other. So what will happen? Y polarization will couple to each other in the both cores, but X polarization will not couple with each other. So for that it will get polarization splitting characteristics. So we have also evaluated the model characteristics of the combined fiber, and this is basically needed because it evaluates the splitting length. Splitting length is basically described by this formula, the where the difference comes in the denominator. Less will be the difference, more will be the length. So our aim was to shorten the device length. And how we can shorten the device length? We can increase the refractive effective indices difference between the two Y polarization modes, basically of the combined fiber. And what was achieved with this type of structure, the specialty was basically the effective indices difference was was very large compared to the previous structures for the higher frequencies range. And due to this we are able to achieve a short device length, basically 2 cm, first achieved in this field, basically with the help of the fibers. Also previous paper there was Ashley paper, and the length was increasing up to 1 meter at higher frequencies like 1 terahertz, and it is mostly used terahertz frequency. So by help of this design we were able to reduce the length at higher frequency. And also we have calculated the extinction ratio, where extinction ratio is the measure of the unwanted polarization extractions, means we are not wanting the unwanted polarization. So it is very high at higher frequencies, and therefore we can conclude that we are able to achieve a very short device length, and extinction ratio was very high. Thank you very much.
Thank you, Vikas. So yeah, probably we can take one question.
Hello, sir.
Yes.
Yes.
Sir, actually, the team is asking to finish this session, and they want us
Okay.
to continue after 7:30 because there is another session in this hall, and the invited speaker is already here.
Yes, we have almost done our part. Yeah. So thank you all the participants who
No,
were here today.
Sunil,
Yes.
one presentation is still left, that Mamta.
Oh yes, Mamta, correct. So I think we should finish that. Yes.
Yes,
Mamta,
Mamta,
can you
do
quickly?
it?
Hello,
Yes, sir. Yes.
Sunil sir. Actually, we are running very short of time. Actually, neuromorphic symposium session is going to be here. So can you reschedule the talk accordingly?
So there is only we need only 5 minutes basically now.
Professor Ananjan, shall we take it at 7:30? I mean afterwards.
I think we can spare 5 minutes because we started also 10 minutes late.
Because one of the invited speaker here is waiting since last 15-20 minutes, and
Oh, okay. Then let's. Mamta, sorry, we have to.
So sorry.
do this.
Your poster to take up later, Mamta. Okay.
We will do your poster later, and all the attendees, please do attend again for Mamta's last poster. Okay, please do not leave. Sorry, Mamta, can you hear me? Sorry, we have
Yes,
to
sir.
cut it
Yes.
short. We'll have to reschedule your talk.
Okay, sir.
Okay. Bye.
Bye, sir.
So Professor Nihar, can you hear me?
Yes, I am here, Manoj.
Sir, I think we can start now. We can invite to our presenter. Now the floor is for our symposium.
Okay, so I think we should start. So welcome all of you for the evening session. So I will invite.
Sir, just a second. Participants, please keep your mic on mute. Participants, please keep your mic on mute so that we can hear very clearly. Thank you. Yes, sir. Please continue.
So welcome all of you to the evening session of Icee 2020. So today means in this session we have we'll have three presentations, one invited talk and two oral presentations. So for the invited talk, I want to invite Professor Adrian Ionescu from EPFL Switzerland. Professor Ionescu, are you there?
Hello, can you hear me?
Yes, I could hear you.
Hello, everyone.
Okay, so let me invite Professor Ionescu to give the invited talk. The title of the talk is Energy Efficient Electronic Technologies for Edge AI Computation and Sensing. So before he starts his talk, let me introduce Professor Ionescu. So Professor Ionescu is a full professor at EPFL Switzerland. He received the BS and MS in Electronics and Telecommunication in 1989 from University of Politehnica Bucharest, Romania. He holds 2 PhDs in microelectronics from UPB in 1994 and in physics of semiconductors from National Polytechnic Institute of Grenoble, 1997. So he is director of Nanoelectronic Device Laboratory of EPFL. His group pioneered steep slope devices and MEMS resonators for energy efficient AI computation applications. He published more than 600 articles and conference papers. He is recipient of IBM Faculty Award 2013 and of Andre Blondel Medal in 2009. In 2015, he was elected member of Swiss Academy of Technical Sciences. He was awarded an ERC Advanced Grant in 2015, the most prestigious individual research funding in Europe. So together with his PhD students, he has received the ideal IEEE Ger Smith Award in 2017. He is an IEEE fellow and served as an editor of IEEE TD and a member of P. So with this, it is my pleasure to invite Professor Ionescu again for this invited talk. So Professor Ionescu, the floor is yours now.
Hello, let me say hello again to everyone. Thank you very much. It's a pleasure and honor to be here with you. And I will stop my video and try to share the slide. Let me see if this is working. Okay. Can you see now my screen? It's okay?
Yes, it's very clear, Professor Ionescu.
Thank you. Thank you very much. I will try to address in this talk within the, let me look at the timing, 30 minutes roughly, this topic of energy efficient electronic technology for edge AI, computation and sensing. As you may imagine, this is a broad topic, and certainly I cannot address all the interesting subtopics there. But I will start by mentioning a few things. First, how we relate today technologies to global challenges. This is very important. It's very important for the student that we have, for the way that the research is going to help into practical thing, important thing. Second thing that is somehow related to global challenges is about the energy efficiency, the definition that we have in different domains, how we can address this better. And then I choose just 2 topics I will talk a bit today. I will talk about devices based on functional device, in particular on devices that exploit the phase transition in vanadium oxide. And then I will try to go to this field of edge AI biosensor and explain you something that is of interest for our days, including in a COVID year, how we can build a human digital twin based on technology and big data, and how this can serve addressing some of the important problems of healthcare. You know, this year I was looking at some moment and I saved this image. You know, I saved it months ago, and it was a moment in time when, you know, in CNN, it was an article where addressing the very hot weather you had in India, right? And you see the title, Too Hot for Humans. And this is experienced on our planet in different regions. So climate change is a global challenge, and everyone tries to think at this moment how we can address that, how we can make the Earth easy to live and more comfortable, and let's say adapt the way we behave to be more sustainable. So I will cite you 3 human challenges here, all needing technology implications. So first is this climate change. So all these forecasts that you see based on different scenarios, and these different scenarios are taking into account implementation of policies at global level by different countries, but also in the same time, different contribution of technology. And one goal here is really to keep under the control the global temperature increase within a certain number of degrees C by the end of this century. This is very, very important, and it's very timely to take action on it and be supported by technology. Second, the generation of engineers we are preparing now, they will experience in this 21st century this inflection point that you see here, right? This inflection point started already, and this is a transition to sustainable sources of energy. So replacing the traditional sources of energy, oil, gas, coal here, by solar cell, by biomass, by wind power, by geothermal energy, whatever is the balance of this by the end of this century, is a massive change at technological level as well. So we have to think about this. Third, we see from more than 50 years let's say, a repeatable difference and consistent difference between the increase in the cost of healthcare and the increase of GDP. Whatever countries you take in the world, you will see that. In US, this is even more visible, right? Is a healthcare cost increase by 2.5% more than the GDP for more than 50 years. And now they are just a bit below 20% of the cost dedicated to healthcare. But if this continues like that, just in US, the prediction is that by the end of the 21st century, healthcare will demand 97% of the total GDP of US, and this is simply non-sustainable, which means that in healthcare, and this is the reason I want to address in the last part of the talk today, we need a completely different model, and not the model that is called today reactive, which means we are going to the doctor or we are taken into charge where we are sick, but we have to do something that is called preventive and personalized healthcare, and another piece, the participatory, and try to rebalance the model of healthcare. So these are things technology should address, but how nanotechnology can help here? Well, first, we have a lot of problems coming, as I mentioned. There is new evidence every day about unsustainable impact on environment. So environment is one thing to address, is related to climate change. There are action taken, and there are some action that are resulting in good things, as you see here. After monitoring, understanding what is happening in an ecosystem, how you can bring back wild animal life at the same level as in the past. Second important thing is that the window of opportunities to address that is very critical. So which means we have to take this action very quickly. And the third thing that I think is very important today for all of us is to think on a technology in a different way. How this technology, that in this case is the digital technology, can decouple the development from the environmental degradation, because you still want to live in a world that is growing. So you need development, but we have to think how to decouple this from the environmental degradation. I want to show you an example. This is an example from Europe. I am very proud of this example if you look at it, and it was planned, right? It was planned in Europe. In Europe, it was a political action with huge investment to limit the gas emission and to bring them by the end of the century practically at the level that you have at the level of pre-industrial era. And what does it mean? It means that different scenarios, you see here more in the more optimistic, less optimistic scenario, we want to have this action by a combination, let's say like that, of both political action and incentive, but also on the technology taking a role. So having green energy, having electric car, having wind energy, having greenhouses in which they are more efficient, having green transportation, having solar cell deployed, all of this will contribute. If you look at the general level, how much technology will contribute based on policies and regulation, is up to 60, 70%. So technology is able to contribute. How you convince people to come with this? Of course, first electrical, let's say car manufacturer will not be happy because at short term, this will not pay back. But then if at long term, they have the right incentive and you invest money into that, it can turn back into an advantage in technology. Like in Europe, there is a huge investment to go to an electrical car development. And we see here now, because there are huge investments into this domain, it's expected that Europe will be, after China, probably the second in the world in producing electrical car. So this type of mindset should be somehow a part of the game. Now, coming to electronics, we know very well that we are living in a world in which technology is democratized. What does it mean, a democratized technology? It means that everyone can use a technological object without knowing what is inside this object. So people do not care what is inside the object. They care about the function. And the best example is the smartphone, right? What is the iPhone? Why the importance of iPhone, a smart system in 2007 is so important for democratization? This, by the way, was the first wireless computer with sensor, right? You put all this function together. And you see, if you look here at the desktop of Steve Jobs, he was just saying that I want to put together an iPod, an iPhone, and have some extra function, a camera together. It's as simple as that. We have to think system level, right? Technology is enabling certain type of system. In Europe, we were looking at this idea in 2011, when it was very early. You find the first trillion of planet for edge worldwide in 2012, 2013. 2011, we are proposing in Europe this project. We called it, a bit naively, Guardian Angels, because we are thinking of devices that will form, and we call it at that time edge technologies, new function with smart autonomous system, like healthy aging manager, system that will help in managing metabolic disorder, smarter quality companion, telling you exactly what is the exposome, what you are getting from your environment, and how important this could be for your health, and so on and so forth, right? We are living now exactly this thing. Edge is something that is contributing to a lot of innovation at system level, including taking on board artificial intelligence. Why this is possible? This is possible because we have also the technology to do that. And by the way, the transistor became the most abundant artificial object on Earth created by humankind. I don't have to tell you today this, but I want to repeat, however, for maybe there are people that are not directly in this domain. We can put on millimeter square today 100 million transistors, all working without error, right? These are three-dimensional objects in which you can count the atoms. There are tens, let's say 100 to 1,000 of atoms in a FinFET device. And you see here at the left-hand side, each white dot practically that you see here, it's showing you a silicon atom in the crystalline structure of silicon. So human-made objects that are smaller in size than a typical virus size, right? A typical influenza virus size is 80 to 150 nanometer. So we are making object of 10 nanometer scale, which means this object made essentially for computation can also maybe serve other purposes, can maybe serve also to sense this world, can also be used to make more intelligent system. And if you are looking in the coming year on the projection made by Gardner, what will be the technology that will come in our use, according again to projection, you will find that first IoT and edge computing are expected to be deployed in the next 5 years. In an horizon of 10 years, we'll see the generalization of digital twin technology and the cognitive computing. And then in horizontal longer term, more than 10 years, long term, human augmentation through AI, which means system that can analyze and decide by themselves, that would be into play. And then quantum computing essentially addressing paradigms of computing as today may be specialized in certain type of computation task or hybridized with the computing that we have today, right? It's not necessarily a replacement of the computing we are doing today. And why it was possible again? It was possible because of the effort of a certain engineering community over more than half century, and bringing practically to the ultimate scaling, because we cannot go smaller. You may know that Professor Hiroshi Iwai from Japan is always saying there will be never a pico technology. There is only nanotechnology, because then you are at atomic scale, right? And you know very well that this brought the scaling of dimension for performance. We have today this idea, which is bringing the question mark of switching of energy efficiency, because of the leakage power, because of the power density issues. We have now practically the scaling not following in switching energy the same exponential law. This was slowed down. You cannot reduce the voltage in the same way it was reduced in the past, right? We are somewhere at 0.7 volt. And ideally, we can go to 0.1 volt, right? In all, if you look at articles analyzing bit distinguishability in digital computing, they will tell you that you can go down to around 5 kT by Q. So this is the idea. Can we go, and how we can go better to get energy efficiency? And energy efficiency means how many computation you can do with 1 watt of power. In the past, Kumis was saying per kilowatt. Now we are talking per watt, because we have smartphone of 5 watt in our hands. Now, another important thing is that more and more people, and we see that in university, they do not want anymore to do hardware. They want to go essentially to do more data analytics, or to work on more on the computer science in the part of cloud technology. Now, I always say this is a consequence of the fact that in 2010 we entered the zettabyte era. And we have now so huge amount of data to store, to communicate, to compute, all measured in zettabytes. And the edge is going to add even more, which means a factor of 1 million times of digital information compared practically with late 80s. Now, of course, data and data analytics is very important. In the same time, hardware is strategic. Even in the business, you will find, and we are telling this to the students now more and more in Europe, even if, again, the margin in business is probably now and will be less than 10%, this is so strategic that people that create the data and the cloud ecosystem, they are the people that are part of hardware innovation. Think only about of Samsung, think of Apple, think of the people that are making hardware. They are creating the ecosystem for the data. It's very, very strategic to keep a hand on. Now, what is happening now is that we do observe this redistribution of the way we think about computation. So computation is happening from edge to cloud, is not anymore just based on data center in the cloud. And the fact that you have more and more devices on edge is triggered by the idea of having them more intelligent and to have them taking decision in real time. And for instance, you'd be surprised, but cars of the future are part and are considered as edge devices. I am saying all the time, take a high-end car like Audi, they make projection after 2050, 60% of the value of the car will be in the electronics. The equivalent of 4 high-performance computer, more than 200 sensor and transducer, a number of system of radar, lidar, sensor for night vision, and so on the car. So it becomes a very smart object. Now, such an object that should be autonomous cannot afford the latency of the communication to the cloud. If you take the latency of today and we take order of magnitude 100 milliseconds, sending information back and forth to the cloud has 2 main disadvantages. One is the fact that in the real-time decision, like driving a car on a highway, you cannot afford this latency. Second, it's very, very expensive as energy to move data from edge to the cloud and back. So this we have really to be very careful. And then we observe also, if we want to do computing in our days, another thing that has been changed is the fact that depending on the application, the figures of merit or the features or the specification that you require for certain computation tasks are completely different. And I will not go through all this, but take, for instance, these 5 or 6 verticals that I show here horizontally, autonomous driving, and compare it, for instance, I don't know, with face detection. And you will find that processing speed, processing per watt, the flexibility of the design, the cost are completely different, which means practically you have to think now end to end. You have, when you design, you have to think decentralized type of computing, and you have to think it as a vertical end to end and customize your solution. And this is what edge computing is bringing. Now, different people said how we address energy efficiently here. One solution is to bring the computation near memory and do computation immersed in memory with fine-grained connectivity. This is one direction, and this is what, for instance, this work from Stanford is showing here. In fact, they use this fine-grained connectivity, but they do more than that here. I think for each type of layer, they use kind of optimal possible technology. If they need high speed, high performance tasks, they are going to use silicon based nanowire or FinFET devices. If they want to use other type of processing that could be low speed, they are going to move and process it in a top layer with a layer of carbon nanotubes type of devices. If they want to use quick access memory, they are going to use STT-MRAM that will be also energy efficient. If they want to use massive storage, they are going to use VRAM. And of course, you can also imagine you putting on top of it a RF analog communication layer, and you can imagine putting sensor on top of it. It's very nice. They run this type of architecture. If you can make it today, this will give you up to 1,000 energy delay product. Problems, very expensive. Problems, thermal problems. You have really to do the thermal management. So it's maybe not a best solution for every type of application. Now, I am saying as well, we have to look at energy efficiency also in the bio world. How we can take bio inspiration there to make bio-inspired devices, circuit, and system. And in this direction, I want just to mention one thing. Of course, here we are talking of energy efficiency measured in energy per useful bit. If you go into the biological world, you will find that biology is not encoding information in level of voltage. So we should be worried by that, because it means that the way that we decided to have digital information in 0 and 1, that is 0 and 1 volt, is not the most efficient way to do. That nature is encoding the information in spike frequency, in the time domain. When you increase the stimulus strength here, what neuron will have, of course, they will have a threshold for which it starts to generate spikes, but you modulate the frequency of spike. You do not modulate the level of a voltage, which means we may think about how to make an artificial neuron technology that may finally be able to consume less than 1 picojoule per spike, right? In a footprint that should be comparable, maybe a bit relaxed compared to the one of neuron. So this is the way we have to think the edge. And now, of course, when you go there, another aspect of an energy autonomous system is the challenge related to putting into a budget of power different function, because you want to do the sensing, you don't have to do the local computation, you want to do the communication, and you want to put all this finally in a local node here, and this local node will have to listen to this and to function under this constrained power budget. So you have really to think again at each level what type of technology you choose and how you combine this node, and maybe become also more energy more efficient in the way you can harvest and store energy. It's not about only harvesting, but it's also about storage and storing energy, and it's also about energy management. And of course, this is a bit more relaxed in the smart hub, like in a smartphone or handheld device, in which you can operate for 100 of milliwatt to 10 watts, so you can put more function for the computation and for the sensor. We see it now that it's coming, it's happening. You have more and more sensor and more smart function. And coming back again to my node on the left, there are some specific challenges related especially to the communication and to the multiple sensor and their readouts and their conversion from analog to digital, in which we have to work hard. Now, I want to give you just a very short summary. What are the main requirements that we put today on edge AI data generator? If these devices at the edge, you foresee them as smart data generation with processing information on the edge. Of course, first people will tell you first, there are 3 steps to think that in the future. First, put on them digital accelerators. Second, think about in-memory operation. And at last, do everything in sensor. But what are the requirements? First, and what is distinguishing what we did in the past, is first, we need real-time closed-loop operation, right? Think about latency, adaptivity, accuracy. Second is the energy efficiency we just discussed. Third, you should have a footprint of this that adapts to the type of the devices. It's different if I do a wearable type of AGI device or I do an in-car type of AGI device or an implantable AGI device, right? It's completely different as footprint. The robustness should be there. We should be fault tolerant. Maybe we have to have self-reparation features. And last but not least, people want security and privacy, authentication with local operation, trust. Trust is the keyword here to mention. It's very difficult, but it's a big challenge for us. Now, I want to go, and I will speed up a bit to show 2 examples. First, it's about how functional oxide can become enablers of such edge sensing in the future. So imagine now devices that are not working in the traditional way. We are doing a digital computation when we perform a task on a given number of inputs, and then we expect an output that is the result based on which we take action. Let's imagine we have now devices that operate more like a brain, which means they may improve the function by learning over time. A filter that sharpens the filtering function and becomes more adapt its feature to the frequency range in which we want to operate. Same for a sensor that is non-ideal but improves selectivity and drift correction over time. And artificial neural network with adjustable weights are another way of thinking about this, and why not using spiking, sensing, and processing. Now, the example I want to show you is in the range of mote insulator. Mote insulator is a particular class of materials that are different from insulator semiconductor of metal and metals, right? In the band theory, you do predict and categorize the material in these 2 classes. We are teaching that to students. But what we neglect in this is the interaction between electrons, right? There are correlation and Coulomb force interaction in the motion of different electrons, which means that in a certain material, and read this paper, is beautiful, When is a Metal Not a Metal by Stephen Irwin in Nature 2006. And it's showing how you can play with confining potential to tune the correlation between the electron. So in some cases, some materials in which this correlation that we call highly correlated oxide, you can, with an external stimulus, let's say with an electric field, switch them between an insulating and a conductive feature. And this is the amazing thing of this insulator, metal insulator, reversible transition. You can apply an external excitation that you see here on the horizontal axis, and this can be of many kinds: thermal, electrical, optical, mechanical, like strain and other. And very interestingly, you can get here a ratio in resistivity of the order of 10 to 4 order of magnitude. And you have this unique feature coming with a hysteresis. I will not enter now into the detail. Why is a hysteresis there? In which you are modulating a band gap and you are modulating phase in the material. Now, this material being very sensitive to an external stimulus, you can imagine them also very sensitive candidates for making sensor, or for making memristive devices, or for making steep slope devices, right? Now, the model of today they cannot explain that just by the pure mode transition model, just based on correlation between electrons. In fact, you have to consider now what is called the cooperative lattice electronic phase change model, in which you consider that the lattice has a structural change. There can be a change of lattice, the atoms are reordering, and in the same time, you do take into consideration the correlation. This is the only way you can explain today by a collaborative mode structural transition. And this was in this paper by Zhu and Ramanathan. Now, the example that I want is vanadium dioxide. Vanadium dioxide is a material of choice here because it has this temperature phase transition at around 68 degrees C, which it's a bit higher than room temperature, right, than 300 Kelvin, which let us operate devices in system, like take a smartphone with the specification, it has to work up to 50 to 60 degrees C from minus 10 degrees. If this is the specification, it means that I can modulate as I want this material within this temperature range. Of course, I have application in which I want to go 100, 125. So I will have to modulate the transition temperature of this material by doping, bringing it higher. But if we take it in a pure phase like the VO2, you will observe that what we call insulator, it's something that in reality is more like a semiconductor with a 0.6 eV band gap. And here the band gap is really collapsing and it goes to have the conductivity as a highly doped silicon, right? Degenerated. So it's very interesting material. And people, you see here different type of stoichiometry in the oxide of vanadium and other type of metal oxide. It looks, surprisingly, this is the most interesting from the point of view being higher than the room temperature with very interesting properties here that can be modulated, right? 4 of the magnitudes contrast in on-off, and being capable of modulating this electrically, optically, also in the terahertz, magnetically, and by mechanical strain. Lot of potential application. I want to show you one, in 3 slides, an example here. Let's imagine we fabricate such a very simple structure of vanadium oxide island on a silicon oxide, insulated from a substrate with 2 gold contact. And we do not take a great technology in scaling. Let's take a micrometer technology. We make a structure with nanograin average size of around 100 nanometer. And then we are going to measure the curve that I showed before in IV, current, like a diode, right? Current versus voltage. So what you will see first, material being in insulating phase, and then going up. This is a very sharp transition. It's very sharp. It happens practically in few nanoseconds. And then you observe this current increase. You limit this because you don't want to burn these devices. And then you reduce the voltage. It goes back at a different voltage, transition back. It has a hysteretic. First, you observe it can be very steep. This transition has the limit of your measurement. It's practically a current increase at 0.5 millivolt per decade. Now, interesting point. Let's repeat this measurement 100 times. If I repeat this measurement 100 times, you'll observe this very interesting thing. Practically, you'll get a distribution of the switching points. What does it mean? It means that because of the process happening in this material, which means between 2 points, you have kind of filaments forming for conduction, which is a nucleation process. I have a stochastic device. Stochastic device is highly sensitive, but it's stochastic. It's a probabilistic device, a bit like neurona. So if you look at the distribution, it's a bimodal distribution. Stochasticity, as Suman data show here, it's really dictated by the nucleation process in the VO2. So you can really look at this if you want to learn more about stochasticity. Look at nucleation processes in this paper. Sorry. But it's very endurant. You can repeat that up to 10 to 9 times. The device will continue to operate, but it will remain stochastic, right? Now, the interesting point is like I can now imagine making devices that are extremely sensitive to everything in your environment, but they are stochastic. And I have to take stochasticity into account. I can make a completely new class of electronics that is highly sensitive to everything, like all type of waves. But I have to think about the fact that it is stochastic in the way I process this information. So this is a very simple example. We are going just to publish this very, very soon, in which we build an oscillator. We took a VO2 type of two-terminal device. We loaded it with a transistor to make an oscillator, and we loaded also the output with a capacitor to tune the frequency of oscillation. Now, what you see here is how to make an unstable oscillation with that. This is the characteristic of VO2. You put them in the same IV plane. This is the hysteresis I showed you before. If I repeat it 100 times, I have this stochasticity. And then I do the operation point by intersecting with the output characteristic of my transistor. And now when this current tends to grow, being in series with the transistor, you limit the current. So the transistor will tell this device, no, you cannot go up. And this will create an oscillation here. And now the interesting point is that, okay, I build an oscillator, and what? Let's expose this oscillator to gigahertz radiation. Very interestingly, this device is very sensitive to the power I apply on it, right? And you see this very beautiful device. If I do a concentrator now, concentrating on the oscillation, on the VO2 device of this oscillation, okay, I'm a bit tight with my time, sorry. I can make a power detector. I can make practically a stochastic oscillator highly sensitive to the power. This is one example of what we can do with this type of technology, right? And I will bring now, and I will try to go very quickly through that, another domain that is eager of new type of sensor, biosensing. In biosensing, we'd like to enlarge the application of the edge in the field of wearables, of implantable, of organ on chip, because we want to sense specific personalized biomarker on people. And all the feature that I mentioned for edge AI apply here. There are people like John Rogers that show you can make electronic stamps you can put on the people that will be used only for limited time to generate this type of data, right? Another domain in which we try to use these devices is, for instance, to sense particular biomarkers in a non-invasive way in biofluid. And as the blood is not necessarily a way to sense non-invasively, we are thinking of a fluid that is produced by the largest organ we have, which is the skin. And we find about 300 biomarkers in the sweat that is produced by the skin. And for many of them, you will have some correlation with the one in blood. For some of them, you will not have, but many of them will remain relevant for a medical condition. If you are looking at hydration, if you are looking at heart cardiovascular disease, if you are looking on stress, for instance, by measuring cortisol, the hormone of stress, if you are looking, for instance, of inflammation marker, like the one we are looking now, particularly in cytokine storm in COVID-19 patient, interleukin, IL-6, not yet confirmed, but they are in this fluid. Can we sense this and monitor a patient continuously if this is validated, right? So making such a technology can be built based on devices that we have traditionally done in silicon, like making silicon tiny sensor based on SOI, FinFET, as I described before, on which we integrate on the top layers that are serving the collection, right? This is the microfluidic that is integrated 3D on top of a chip that will let you collect, for instance, sweat. This sweat will be channeled to a reference electrode and then to your devices, the sensor, and then it will be pumped up by microfluidic pumps using capillary forces. This is zero energy microfluidics, right? Because it's using capillary forces. I want to show you one chip we made in EPFL. This is the full device. We show IDM 2017, this chip. It's working. We can measure 4 types of electrolytes in real time. Practically, sensor responds in less than 10 seconds. And it can be a sensor you will put in a patch or in a wristband in the future to measure your hydration level, right? This is the sensor. You can look in ACS Sensor 2019 where you're integrating sodium, potassium, calcium, and the pH sensor. And we make this in back end of the line with dedicated membrane for the 3 sodium, potassium, calcium specific sensors that are also not only highly sensitive, but they are highly selective. You see here the response only to sodium and the response to the other analytes is flat. So we make sensor in which we extend the gate. Okay, we extend the gate of this device to sense these multiple analytes. And last example I want to give you here is something very recent. We make such a sensor able to sense the hormone of stress in sweat. This is something we'll report this year in IDM. We make this device with a fluidic channel integrated in an extended gate FET. On the electrode, we brought an aptamer graphene sandwich. Why is that? Because we can make this aptamer very specific to the cortisol in sweat. And the graphene is letting you to sense that within the Debye length. And very beautifully, we built a unified model that is able to be predictive. So we are able to calibrate and put it in a system and have a model that is, based on few points. We calibrate the sensor, we can take a measurement, and we can tell you what is the concentration of your cortisol within a minute. Let me skip this, and I will go to the last part, 3 minutes, and I will finish. Why we want to do this and to sense this type of analytes for humans at the edge. Today we are building all kinds of artificial objects, the cars, the planes, the energy system based on a digital model on a computer. But keep in mind, digital twin that is called the twin on digital domain of this object is not about the design, but it's also about predicting what will happen with this object during his lifetime. The aging, the maintenance, the crash of the car, everything is part of a digital twin, which brings me to this idea. Can we bring in the future digital twin of our organs, of their interaction at the end of all humans? Because if you do that, the fantastic thing you can do is that measuring very tiny changes will let you to predict the trajectory of a disease with high probability, which means you can avoid the costly and difficult phase of a disease. And for the people that are now online, I want to tell you that this is an opportunity also for business, because now we are paying worldwide, right? It's 7.2 trillion, the cost of diagnosis. This is the value of being sick. We are paying because we are sick. No idea what is the value of not being sick. But if I will take, let's say, a comparison between the not being sick and have the technology deploy and use such a system and pay an insurance for not being sick, I may consider that, because it's the value of having a quality of life. So this is where I think we can make a difference with this type of system, exactly as we detect the trajectory of a storm. This is the same way by using sensor big data model computation healthcare forecast, right? And this is what the digital twin will do. Will shorten the distance between the medical knowledge creation and medical knowledge application by putting together this in a single type of environment, which is the digital twin, is the missing link for breaking barrier. And what it needs the hardware to build a physical avatar. It needs all the devices to collect this data, hardware, wearable, implantable, exposome sensor, body on chip, and it needs the software, the big data, the Internet of Health, and AI. And you can put it in the pocket of a person or on the desktop of a medical doctor. And the last slide I have is this one. We are starting now in Europe such a big project to build a digital twin at the edge with 2 big hospitals in Charité in Berlin and in Bern in Switzerland, to have a model that is based on data collected at the entrance point in the hospital to predict the trajectory of a COVID-19 patient. Is he or she be a high-risk patient? And we put a monitor on them, and we are looking at some key biomarkers, and especially on the cardiovascular implication. Sorry, I took more time, but I'm concluding now. There are high expectations from novel technologies to solve this type of problem, human-grade challenges, climate, energy, health. I hope I convince you edge AI data generator is something is happening. Functional oxide, bio-inspired sensor, wearable, implantables that benefit from electronics in a different way are the future. And then last but not least, when you think about that, think system level. Think it in a technology system data analytic interaction, not standalone technology or standalone system or standalone data analytics. Thank you for your patience. I will stop here. Thank you.
So thank you, Professor Ionescu. This is really informative and interesting talk. And the points mentioned by you are very important. So, but the interest of time, I think I'll take one question. So, are there any questions from the participants? So I not see, but I have a question. So basically, we need very energy efficient devices. So what kind of devices you foresee you will have in next 5 to 10 years? I mean, to use in these kind of applications, because you need energy efficient devices.
Mm-hmm. So just as a comment on this point of view, the most important part here is not to think only energy efficient devices, but to think energy efficient systems. Because just let me give you an example. Everyone is, and I am working on that as well, everyone is saying today, let's do steep slope devices, reduce the voltage operation to 0.2 volt from 7.8 volt, then I would gain at least a factor of 10, maybe if I reduce 3 times this 3 power 2. But you know very well that the switch is just a part in the system. The data is computed, then is moved on the bus, then is stored in the memory. So finally, what's the contribution of the switch is 15-20%. So think system level. Of course, when you think system level, you are going to think what type of computation device, what type of memory device, what type of architecture I should use. So for me, it's more important now to think how a device can serve the system level. Second, if you go to the device, of course, you have to be a bit more open in the future to have the role of new materials. There is a lot of revolutionary progress that can be done with material system. And here, of course, you have to think also broad, but let's say realistic. You have to choose material in which you can probably generate more intelligent function with low energy consumption than just to mimic a binary switch. So I will keep it for the sake of time short, but this is a bit the type of answer I think we have to reflect on in the future.
Yeah. So thank you, Professor Ionescu, and from the conference organizing team, I want to thank you again for willing to give an invited talk in this conference.
Thank
so
you so
now I'll move because we have another presentation. So I'll move to the next presenter. So I'll request. Okay, so I'll request Ranjit Sasikumar to connect and start your presentation. So Ranjit,
Okay.
are you there?
Yes, thank you, sir. I'm there. Am I audible to you?
Yeah, you are audible. Your voice is a little bit breaking. But you are audible. So
Okay.
yeah.
Now I will start share my screen.
Yes, please.
Now, is my screen visible?
Yes, Ranjit. Your screen is very well visible.
Okay. Now I think my screen is visible and I'm audible also.
So Ranjit, your voice is a little bit breaking. So I don't know whether this is from my side or any other. So can you please fix your microphone a bit? Then we could start.
Okay. Good evening, everyone. I hope I am audible. And I am presenting a paper on modeling of the dynamics of switching in electrochemical metallization based membristors. here is the outline of my presentation. I will be talking about my motivation behind working in resistive switching devices. I will talk about some of the electrochemical metallization based membristors with low switching voltages. Then I will talk about our contribution mainly on the modeling the dynamic switching characteristics in ECM based membristors. Then I will discuss about how to calculate the switching energy during the switching operation, and I will conclude my discussion by analyzing our simulation results. So modern devices requires huge amount of memory, like cloud-based devices and IoT-based devices require huge amount of memory. That means these devices requires devices having high scalable elements. So current flash memories cannot keep pace with the sustained reductions in the dimensions because of the physical limit in the oxide thickness. As you can see, as we reduce the switch, size of the transistor, there is a possibility of gate leakage. So resistive random access memory is a promising candidate for the next generation non-volatile memory because of its high scalability. So resistive random access memories use resistive switching devices whose resistance depends on the history of operation. This comes under the broad category of memristors. The essential idea here is to obtain a hysteresis in the IV characteristics as shown in the figure. So the main purpose of our work is to analyze the transport in these kind of resistive switching devices. Coming to the type of resistive switching devices, there are two types of resistive switching device. First one is called balance change memory, where the resistive switching is due to the oxygen vacancy migration inside the switching layer, and these type of device have relatively high switching voltages. The second type of memory is called electrochemical metallization cell, where one of the electrode is an active electrode, and resistive switching device in this particular device is due to filament formation or dissolutions inside the switching layer. Metallic filaments are formed due to the redox reaction at the switching electrode metal interface. We can have a look on some of the recently reported ECM resistors. There are two types of switching layer. First one is come with the oxide switching layer. Here is an example of oxide switching layer with a tungsten oxide as the switching layer of thickness around 20 nanometer, and this device have a relatively high switching voltage. If you see the switching voltage, it is around 2 volt. And if you consider this device, this particular device has a very low inter-electrode distance of around 1 nanometer. We will come this later. We will come in detail later to this particular device. And if you see this particular device, this has a lower switching voltage. Coming to another type of switching element is called transition metal dichalcogenide switching layers. Here is an example where we are using a monolayer MOS2 in lateral direction as the switching layer, and this particular device also having a relatively high switching voltages. Now, if you consider this particular device, it uses a double layer MOS2 where the thickness of the double layer MOS2 is about 1.26 nanometer, and these particular device have very low switching voltage. Encapsulating, we can say that as the effective switching layer thickness decreases, the switching voltage decreases. So before moving forward, we can have a qualitative explanation of the IV characteristics in electrochemical metallization cell. This is the IV characteristics of a particular electrochemical metallization cell in linear cell. And if we consider the same in the log scale, it looks something like this. If you are applying a positive voltage across the device, what happens is at the active electrode, there is oxidation of the oxidation of atom happens, and that metal ions will be moving towards the inert electrode, and this particular inert electrode, it reduces and it nucleates and start to form a filament inside above the inert electrode. As you further increase the voltage, what happens is the filament is growing inside the switching layer, and the ion current is also increasing, which is evident in the log scale. You can see here. Now, if you further increase the voltage, what happens is the filament grows inside the switching layer. There is a possibility of high tunneling due to low distance between the filament and the top electrode. At that particular point, there is a sudden change in the current, and that voltage is known as set voltage. And if you reverse the bias polarity, what happens is dissolution happens inside the switching layer, and the filament is dissolving. As you increasing the bias of the voltage, magnitude of the voltage, what happens at a particular voltage, the filament is completely or almost completely dissolve. At that particular point, the device switch back from its low resistance state to high resistance state, and that voltage is known as reset voltage. Now, what is the importance of dynamic switching in electrochemical metallization cell? See, if you are configuring this dynamic resistive switching device as a RAM cell in a crossbar architecture, if you consider one of the element will be this RAM device or memristor, and this type of static measurement is used is done for the static IV characteristics, where the measurement is done using slowly varying input. But in the real scenario, if you consider the read-write pulse of a crossbar architecture, it will be in the seconds or in seconds of nanosecond. So it is to simulate, or the dynamic measurements are important for read and write operations for the crossbar architecture memories. And this can be also used for calculating the switching energy estimations. So encapsulating dynamic measurements are important for switching delay and switching energy calculation. Coming back to the previous device, which I have mentioned, this is the top view and this is the side view of that particular device. This is the entire structure of that particular device. And if you see, there is a V groove in this structure, which essentially reduces the inter-electrode distance to a very small quantity, 1 nanometer. And if you consider the entire structure, the device will be the thickness of the top and effective thickness of top and inner electrode will be around 10 nanometer, and this is the entire device structure. And in this particular device, if you apply a short duration pulse of 20 nanosecond, what happens is the device switch from its high resistance state to low resistance state after a delay of 7.5 nanosecond. Now, similarly, if we are applying a reset pulse, if you see the reset voltage which we are applying is very small, since the voltage is very small, it takes a longer duration to switch back from its low resistance state to high resistance state. So our aim is to model the dynamic switching characteristics and to calculate the switching energy during the set process. Modeling the dynamics of switching characteristics in ECM based device. In a particular device, we have interface of switching layer and metal. At any device, there will be two interfaces. First one is the active electrode switching layer interface, and the second one is the filament switching layer interface. At equilibrium, the potential difference across this interface is psi equilibrium, and every quantity of electrochemical metallization is explained in terms of a quantity called over potential eta, which is nothing but the difference in equilibrium and non-equilibrium potential. And at any interface, there are two processes. First one is an anodic process by which a metal atom is converted to metal ion, and second one is a cathodic process by which a metal ion is converted to metal atom. At equilibrium, these two processes are equal. And when eta is positive, this anodic process is dominating, and when eta is negative, the cathodic process is dominating. So we can encapsulate like this. At any interface, there are both anodic and cathodic process, which process is dominating, that is decided by the bias supply. So there is an expression for the flux due to the ionic processes. It is called Butler-Volmer expression, which has two terms. First one is for the anodic component, and the second one is for the cathodic component. Now, coming to the modeling of transport in ECM device, this is the device structure. We can explain using the equivalent circuit. Every experimental system has a series resistance or connection resistance in series, or the top electrode has a finite resistance. At this electrical interface, there will be an over potential eta AC, and ionic current through that interface is explained as a function of that over potential. And these ions are moving under the influence of an electric field, therefore there will be a series resistance. At this particular interface, there will be another over potential eta filament, and the ionic current at that interface is represented as a function of that over potential. Apart from this ionic path, there will be a tunnel current path, which is in parallel to this ionic current path as a function of the gap x. Now, therefore, this is a filament, the finite filament resistance, and bottom electrode have the resistance RPT. Now, this is the circuit diagram showing all the biases, and The simulation procedure is like this: define the growth rate, growth of the filament using the Faraday's law. Define the ionic current using the Butler-Warner equation, and find. See, if you equate these two ionic currents are equal. If you equate these two, you can represent all the potential in terms of eta AC. Now, there the calculate the currents using the relevant tunnel model, apply KVL if the device is not in current compliance. If the device is in current compliance, use KCL and solve the equation. These are the equations: Faraday's law, Butler-Warner equation for ionic current, and equating over potentially all the potential are represented using eta filament, the dominant tunnel model, relevant tunnel model. Then applying KVL in the inner loop and outer loop, you will get these two equations. And if you are applying a KCL, the total current will be divided as the ionic current and the tunnel current. And this is Faraday's law. If the device is not in current compliance, solve these two equations simultaneously. And if the device is in current compliance, solve these two equations simultaneously. Encapsulating all the points I have discussed here, we can say that eta filament and gap X are the unknowns and solve them simultaneously. This is the entire takeaway message from this particular model. So we have we have model using Verilog and simulated this using the cadence spectra environment, and we have created a circuit symbol using the schematic editor, and we have put a series resistance which is consistent with the experimentally used series resistance, and we have using a piecewise linear voltage source for defining the set and reset voltages. We are monitoring the cell and applied voltage. This is the simulation procedure. Coming to the simulation result, this is the pulse they have applied for the experimental procedure of 20 nanosecond duration. The rise time is about 0.5. Simulation also use the same kind of input signal. The current reaches after 7.5 nanosecond only. The current is shooting up. That means the simulation is also capturing the set process, but we are not able to capture the exponential decay after the end of the set pulse. That we will be working on it. And now this is the reset pulse. We have applied a very low magnitude negative pulse, and pulse has to be applied for a long duration. And this is the experimentally observed the current characteristics. At this particular point, the current is switching from its switching to zero. Simulation is also capturing that switching delay is around 40 microsecond, and this is the reset operation in magnetized form. So simulation also captures the reset process. Now coming to the switching energy estimation using the cell voltage.
So can you please, participants, can you please switch your microphone off, because this is just disturbing the talk.
Okay. Sir, can I continue?
Yeah, please.
Yeah. This is the top. This is the top. See, we are considering the cell voltage, and we are considering the current through the cell. It is I cell. So now, we are calculating the instantaneous power by multiplying the current at instantaneous current and instantaneous voltage. This is the power waveform, and we are integrating that to get the switching energy. And the pulse is applied for a 20 nanosecond duration, and the switching energy for that particular duration is about 18.91 femtojoules, which is consistent with the experimentally observed the switching energy. So the simulation is able to capture the switching energy during the set process. So this is my summary. I have modeled using the electrochemical metallization process. The simulations captures the set process. The simulation captures the reset process, and the simulation can be used for estimating the switching energy during the set process. And in summary, this switching delay during the set and reset process is consistent with the experimental data. So this type of model can be used for simulating the dynamics of set and reset operations. And this type of model can be used for switching energy estimation during the set operation. And since it is doing the dynamic characterization, these type of models can be used in a system level applications like crossbar architecture. I would like to thank Dr. Stephen Menzel and Dr. Aravind Ajay for their useful input, and I will like to thank IIT Palakkad for providing the cadence tools. Thank you. Thank you for listening me.
Yeah, so thank you, Ranjit. It was a very nice presentation. Well in time. So, are there any questions from the audience? Because I don't see any questions in the chat box. But I have a few questions. So basically, you have modeled the whole phenomena. So is this a compact model or it's an analytical model? Because I didn't get a feel of it during the presentation. Huh.
It is not fully analytical model. We are here these etas at the switching electrode interface and the filament switching layer interface are unknowns. Also, the dynamically changing gap x is as the filament grows, the gap x is also changing. So this equation has to be solved numerically.
Okay.
Simultaneously, we have to see these two equations. If the device is not in current compliance, these two equations has to be solved in simultaneously. And
So
if the device
how are you solving this numerical equations using Verilog?
Yeah.
So you are doing it in Verilog model. I mean, using.
Yeah, actually, we have done this model in both MATLAB and in Verilog because we switched to Verilog. Cadence. Why? Because for a system level application, we need Cadence, and in Cadence there are integrating functions are there. Verilog A functions are there for doing the numerical integration.
Okay. Okay. So how many? I mean, how much time does it take to solve this?
This
Let's say getting the transient response. So how much time it takes?
In Cadence, it will take 10 to 15 seconds.
Okay.
Cadence is faster.
So you have only compared it one of the papers, right? So basically the papers from this Julie group. So is your model, can we use any other experimental results?
Yes,
Have you
yes.
checked
Actually,
that?
similar. Yeah, yes, yes. Actually, I have mentioned two devices here. First one, two devices with low switching energy, switching voltages. Yeah.
Okay.
Come here. Actually, we have. This is the paper or this is the experimental data I have described here, where it has a dynamic characteristic. Actually, we have modeled this paper also. Actually, we have simulated the static IV characteristics, and there is variability in static IV characteristics of this particular model. And that one we have simulated using the same approach, and that is published in IEEE Nanotechnology Conference.
Okay. Okay. So thank you, Ranjit. It was a nice presentation and very nice results.
Okay.
So I think yours is the last presentation in the evening session. So we have now the plenary session going on. You could attend there, and I think we should close the session. So I would like to thank all the participants and all the speakers for this session. So now I'll close the session. Okay. Thank you.
Thank you, sir. Thank you.
Hello.
Hello, everybody. I am calling just Sunil sir has joined or no? So I am calling just Sunil sir. Okay, fine. Sir, Sunil sir is coming just a minute after. So we can wait for 1 minute.
Sure, the previous session is over.
No, sir, it was not over. We have just put the time in the email 7:15. So sir is also arriving. It will take, I think, 6 minutes and we will be over. Yes, sir.
Okay. No,
Yes.
I don't see that previous meeting going on. Is the previous meeting going on?
Yes, sir, it is going on, I think. Sir was telling me that it was going on. Yes, sir.
I don't see that here in hall 5.
Sir,
No,
in
sir,
the hall,
here it is not happening. It is happening in hall 1.
Then how are we bothered? We can चलिए ठीक है. Okay.
Yes, sir. Yes, sir. Yes, sir.
चलो ठीक.
अच्छा टॉक खत्म हो गया उनका?
No, sir, it is happening in hall 1 basically.
अरे अच्छा अच्छा, so okay.
Hall 5 is empty now. It is vacant.
Okay,
Yes,
okay.
sir.
Yeah, perfect. Okay, so now Professor Ananjan, shall we start?
I'm not very sure. What are we supposed to do if hall 1 has a meeting and if say 3-4 people there, they want to attend this one also.
Okay.
I think
Yeah.
that is just one more poster. I don't think there's much point. Maybe I think we should just go ahead or not. What is the Vikas? What is the schedule
sir.
of that other meeting?
Sir, I think it is up to 7:30. We Shakti, can you tell me?
it's
I
up
think
to
it is 7:30.
it's up
Yeah,
to
I looked at
7:30.
that. 7:30.
So should we wait 10 minutes or should we just
I
carry
think,
on
sir,
now?
people will not join, I think, after 7:30, so we can continue. Yes.
I think we should continue.
Yes, sir.
Sunil, let us finish off.
Okay.
We have several people here. I think
Yeah.
many people are here already, including
Yes.
several of the other presenters. So we can continue, I guess.
Okay,
Right?
fine. Yeah, sure. So, okay, Mamta, you can basically
Yes, sir.
share your poster.
Yes, sir.
Please go ahead.
So, Mamta is a PhD student at IIT Delhi. And yeah, just
Yes, sir.
get started.
Yes, sir. Hello, everyone. I am Mamta, and today I am presenting my poster on surface morphology of steppers on MgO single crystal substrate for Josephson junction devices. Basically, high temperature superconductor junctions are used for terahertz detection due to their energy gap, which lies in the terahertz frequency range. So, the requirement of substrate for terahertz detection is low frequency losses and good lattice match between the substrate and thin films. So MgO substrate satisfies both these requirements. Hence, for obtaining a good quality device, step angle and surface morphology plays a crucial role. So here we are presenting the fabrication of step edge on MgO substrate by two methods. First one is wet chemical etching method and other one is dry etching method. Firstly, half portion of the substrate was coated with photoresist by using maskless lithography. Next, for wet chemical etching, the PR coated substrate was put in a mixture of phosphoric acid plus sulfuric acid taken in volumetric ratio of 20:1 1 for a time of 8 minutes to obtain a step height of around 220 nanometer. And then another substrate, another PR coated substrate. Next, the argon iron milling is used for the dry etching. Basically, here the substrate was placed here, and we have used ion beam energy 400 electron volt, and beam current was 30 ampere, and etching time was, in this case, was 40 minutes for getting a step of height around 500 nanometer. Then we have characterized the fabricated step edge by using AFM and SEM facilities. So here in the AFM image, we can see that the step edge created by the ion beam milling technique is much more sharp and smooth in comparison to the step edge fabricated by the wet chemical etching process. This is looking bit rougher. And also the AFM images of the unetched and etched portion of the MgO substrates in case of ion beam milling are revealing that there is very small increase in the roughness of the substrate of the unetched and etched portion. While in case of wet chemical etching, there is a huge increase in the roughness of the substrate of both unetched and etched portion. So the increase in the roughness of the MgO substrate for both unetched and etched portion can be possibly due to the used DI water during the wet chemical etching process, because MgO substrate is hygroscopic in nature, so its exposure to the moisture or water can deteriorate the surface quality of this substrate. Hence, in conclusion, we can conclude that wet chemical etching method, although wet chemical etching method is fast and cost effective in comparison to the iron milling method, but still for the device applications, it is less appropriate, and iron beam milling method is much more preferred for fabrication of step edge. Thank you, sir.
Thank you, Mamta.
Thank you, sir.
So, is there a question?
Yes, looks so.
Yeah, there is some echo from somewhere.
Oh, okay.
Hello, Sunil sir.
Yeah. Is there a question?
Sir, no, sir. I am not asking any question. It's
Okay.
because basically one particular Rohit, I think from ICEE team, has called me just a few minutes before, and he was saying that one more student, Megha, is actually has not she has not plenty of time. The time not was available for her presentation. Basically, her presentation was in device modeling. So he's saying that can we arrange for that poster presentation for this time in hall 5, because
Okay.
I have just
Yeah, we are done.
I have just told him basically that you should contact the convener of that particular session, and he or she will arrive, and then Mega will also arrive, and then we can continue maybe.
No. Yeah. So they can do whatever they want to do. Our session is going to get over now.
Yes, sir.
Mamta, you just, you unshared your poster. I had a question.
Yes, sir. 1 second, sir. Yes, sir.
Yeah, so this MgO single crystal.
Yes, sir.
Right. So you are trying to etch it. So because of etching, some does the crystal get change in the sense that the superconducting temperature
Yes, sir.
Is there anything, it gets modified because of all this process?
No, sir. Actually, if we are depositing thin film on a substrate which is etched by the ion beam milling process, then there is not much difference in the TC value, sir.
How much is it for this crystal?
For this, we have obtained around 87 Kelvin, sir.
Okay. Okay.
Yes, sir.
And after the etching process, also did you measure it?
No, sir. After this, we don't have measured actually.
Okay. Okay.
Yes, sir.
Fine.
Yes, sir.
So thank you, Mamta. And
Yes, sir.
now you can unshare it.
Yes, sir.
Yeah, I can see that there are still, few people here, few participants who presented their posters today. So thanks to all the participants for participating actively and joining us in this conference. So thank you very much. So now I think with this, Professor Ananjan, you would like to add something and then we call it off.
Yeah. That's all. I think we are happy that the participants were so patient and managed to present their work so quickly. I'm sure some of you may be presenting for the first, or you may not have presented many before, so it will be a good experience for you to do your presentations, and you should learn how to present the core material quickly. So I hope you had a beneficial experience, and thank you very much for your participation.
Yeah. So thank you. Bye bye, and see you sometime again in future. Okay. Bye bye.
Bye.
So I'm sending Professor Anandan your link, MS Team link.
Yes.
Okay.
Hello, is Namrata Shetty is basically the volunteer for that session?
No, sir, Megayam.
So yeah, but there is one more name, Namrata Shetty.
Yeah, she's my friend.
Okay, she's your friend. Okay, fine. So maybe Akansha will come, and I think if some convener is also there, then your presentation will be in good area. But I think convener will join, then it will be good. Yeah.
Sure, sir.
One Nagesh.
Yeah, he's also my friend.
So three of you are friends. Okay, fine. So Akansha will join. I think we can wait for her only. Yeah.
Okay. So shall I share the screen? If any technical error present, you can share at least. We can check with that.
You can just share. We just check what is the. I think we will just check it.
Okay, so
And
share.
Mahesh is also there. Is Mahesh volunteer? Hello,
I have no idea about him.
Mahesh. Are you listening to me? Okay. He's not giving any reply. I think Pragya will come. Pragya or Akansha will come. Then we will. You just share your screen. We just check it. Mahesh, are you listening to me?
Yes, sir, I'm listening.
So you are volunteer or you are just a visitor?
I'm just visitor.
Okay. So Pragya or Akansha will come. We will just check it. Yeah, your screen can be seen. Uh, you just make it zoom and then let's wait for Pragya or Akansha. But what will happen now? There will be no convener because I think convener is not present this time, and we have to do with the presence of only volunteers. There is no other way. So let's wait for Pragya and then we will continue. Mega, your presentation is coming in not coming in full screen mode, and it is basically it is showing cut portion. Now it is full, but it is very small.
Yeah, because
You
I'm
just zoom in.
in mobile.
You just zoom in. No, Pragya is also there. Pragya. Basically, Pragya is there. So Pragya, uh, will there be any convener? Pragya, are you listening to me? Now it can be seen. Yeah. Pragya. Oh, he's
Sir,
not.
sir, I'm here.
Okay, fine. You are volunteer. Is there convener also?
No, sir, conveyor is not here, sir.
Okay,
Right
so
now.
fine. We can just listen to her presentation,
Yes, sir.
and yeah. Mega, you can continue. Basically, you should zoom in and then tell us about your presentation. Yeah, fine. Go ahead. Yeah.
So my poster is basically on the topic effect of nanocone anti-reflective coatings on organic light emitting diode to enhance the light extraction efficiency. You know, to start with the introduction, I would like to introduce OLED. OLED is nothing but organic light emitting diode, which works on the principle of electroluminescence. Electroluminescence in the sense recombination of holes and electrons in order to provide light energy. OLED uses organic materials to provide that light energy, whereas LEDs uses some backlight. That is major advantage. When it comes to the disadvantage of OLED, there are certain losses called as surface plasmon losses, substrate losses, and waveguide losses. Now, my poster deals with the substrate losses, that is to reduce the substrate losses by introduction of nanocone anti-reflecting coatings. As depicted in figure 1, we are using nanocone anti-reflective coating above the glass substrate in order to reduce the total internal reflection occurring due to the due to the rigid glass surface. That is, the light, whatever the emitted, will be trapped within the device due to the glass substrate. In order to
Excuse
reduce,
me, Mega. Excuse me, Mega. One
yeah.
second. You just zoom in your poster so that we can see clear picture because it is coming in very small. Yeah, now you can zoom in portion by portion and you can just use hand tool to just shift the portion and you can just zoom one portion. So it will be easy to see your figure also. Yeah. Yeah,
Yeah.
yeah. Now this is the way. Yeah, thank you. Yeah.
So, as depicted in figure 1, we are uploading the nanocone anti-reflecting coating just above the glass substrate in order to reduce the total internal reflection occurring due to the rigid glass surface. That is, light will get trapped within the within the device. In order to avoid that and also to enhance the light efficiency, we are using nanocone anti-reflecting coating, and that nanocone model structure is depicted in figure 2. And we are modeling and simulating the OLED as well as nanocone structure using FDDT numerical software. And this is the one which shows the modeling of figure 3 is the one which shows the modeling of OLED structure by conducting the layer of nanocone ARC, which is simulated using numerical software. And the nanocone material which is used is Teflon AF 2900, which with the refractive index of 1.22, which is lesser than the refractive index of glass and and greater than the refractive index of air, so that the total internal reflection is avoided. And when it comes to the results and discussion, as it is shown in the figure 4, when we put the nanocone anti-reflecting coating, the light enhancement is being depicted in figure 5, whereas in the absence of anti-reflecting coating, figure 4 is the one which depicts that the intensity, far field intensity, is around 1.01 into the 10 raised to the power minus 5. Whereas after been uploading with the nanocone anti-reflecting coating, the light efficiency has been increased by 1.54 into 10 to the power minus 5. This is the result which is observed in numerical software. And when it comes to the figure 6 and 7, this shows the usage of the various wavelengths in order to particularly choose a perfect wavelength on which the light efficiency or the intensity of the light will be high. As depicted in figure 6, around 540 to 560 nanometer wavelength, the intensity is very good. So we are choosing the wavelength to be 540. We can use 560 also for further rounds. And when it comes to the figure 7, it shows the intensity level of the conventional OLED when compared to the nanocone based OLED. Nanocone based OLED has a very high intensity when compared to the conventional OLED. And when it comes to the figure 8, it is the one which shows the dipole versus wavelength. In the sense, when conventional OLED dipole power is very less when compared to the nanocone based OLED because because of the coatings which we apply, so that it improves the recombination power, which also increases the intensity. That is nothing but recombination of holes and electron increases, thereby increasing the light efficiency and the enhanced light output we get. And when it comes to the conclusion, as I already mentioned, on application of nanocone anti-reflecting coatings, the light efficiency is been enhanced to 1.54 into 10 to the power minus 5 volts per meter. Before in conventional OLEDs, it was just 1.01 into 10 to the power minus 5. So I would like to conclude that using nanocone anti-reflecting agent, we can enhance the light output. Thank you.
Yeah, thank you very much, Megha. Guys, if you have any question, you can just ask Megha, and then we will end this meeting basically. So if you have any question, you can just ask Megha. Pragya, you are wanting to ask something?
No, sir. If you want to ask anything, then you can ask, and I can convey to the.
Okay, fine. I was just going through, and I have just listened that Megha is using Teflon. Are you using Teflon in your device also?
In this in model OLED structure.
Yes, yes. If there is any Teflon coating also there.
In this, I have not modeled it. So basically, when it comes to the reality part, I should just buy the Teflon and put in it. In this.
Okay, so what will be the use of Teflon in the device?
For
basically.
nanocone anti-reflecting coating, that is the material
Okay. So which frequency are you using basically? Which frequency are you dealing with?
540 nanometer.
540 nanometer. Okay, fine. So you are just creating the anti-reflecting coating with the help of Teflon also. Okay, fine. Thank you very much, Megha.
Thank you so much, sir.
Okay. So let's Pragya, you just convey to the ICC host basically the students present there. So that all the presenters, you can just confirm that Megha has also given her presentation, and let's end this meeting. Thank you very much, guys, for attending this meeting.
Thank you, sir.
Okay, bye. Take care. Okay, bye.
नहीं अच्छा लग रहा है अभी हम खा रहे हैं इतना सारा ना खा पहले खा तो रुको हो गया खत्म क्या टाइम पे आते नहीं हैं लोग फिर बाद में करवाओ मेरा चाहिए थोड़ा सा ऑर्डर ले लीजिएगा किसी का कॉन्फ्रेंस है पोस्टर प्रेजेंट करना था तो 3:30 से 5 का टाइम था उस समय आया नहीं कोई धीरज प्रज्ञा बोल रहा हूँ अच्छा ये एक उसमें डिवाइस मॉडलिंग और सिमुलेशन वाले पोस्टर में एक लड़की थी जिसको हमने अपसेंट अभी किया था मेघा एम करके होगी मतलब क्या प्रॉब्लम आ रही है तो उसका अभी करवा दिया हम लोगों ने टेराहर्ट्ज के उसमें तो अंकुर सर ने अलाउ कर दिया था कन्वेयर ने अच्छा तो वो मिस कर गई थी क्योंकि उसको हॉल 2 का मिल गया था जबकि हॉल 4 में हो रहा था तो हॉल 2 में दे दिया नहीं तो उसने टेराहर्ट्ज वाले में दिया है अभी हॉल 5 में था ना टेराहर्ट्ज वाला तो उसी में उसने दिया है तो उसको बस प्रेजेंट मार्क कर देना है ठीक है वो मैं कल कर हाँ हाँ हाँ, मैं तो मैंने कहा आपको कन्वर्ट मेघा एम करके। हाँ मैं आपको देख के लिस्ट बता देता हूँ। मैं मैसेज कर दूंगा। ठीक है दीदी। ओके ठीक 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 ओके ओके। ना 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 ले लेंगे पहले ही ज्यादा दे दी।
पानी निकाल दो अभी थोड़ा सा। सही बना ना।
मसाले थोड़ा सा हमको लग रहा है ना, जो धनिया वनिया है उसको धूप लगा दो, जो डिब्बे में रखा हुआ। हमको लग रहा है उसी से कड़वाहट आ रही है, जैसे कुछ भी बनाओ तो नहीं ठीक बन रहा।
आगे देखो आगे वाली कौन सी कुर्ते में बना रखा
मैंने जीवन पसंद वो जो है ना